All right. Hello, everyone. Let's get started. So, good morning, everyone, both in-person and online audience. Welcome to the workshop on symmetries in robot learning at RSS 2023. My name is Wang, and I'm a PhD student at Northeastern University. Oops, sorry about that. So on behalf of all the organizers, I would like to thank everyone joining us both in person and remotely. And I'm really looking forward to our discussion today. So why do we want to discuss symmetries in robot learning? Traditionally, roboticists have leveraged all kinds of geometric or physical structures to make challenging problems easier. So out of all the structures, I think symmetry is one of the most obvious and fundamental one. So many works have tried to leverage symmetry in robotics before. So on the slide, there's a paper by Saylor et al. At IJR 2012 who tried to use symmetry in planning. So the figure is showing that when you rotate the car in the scene, it's actually the same as keeping the car unmoved but rotating the camera. So if a plan is generated for the left scenario, it should automatically generalize to the middle case by applying rotation on the plan trajectory. So this is very nice as it significantly reduces the problem space. Can we also use a similar idea in robot learning? So the answer is yes, and folks have done that already in the past. So on the left, I have an example of the transporter network by Zeng et al., who will be one of our speakers today, where they implemented the translational and rotational symmetry in pick and place manipulation problems. On the right, there's another example from the neural descriptor field paper by Symmetries et al., where they use a method that can generalize to different SE3 object rotations. By using the symmetric structure in the problems, we can dramatically improve the learning efficiency. In the meantime, there's a new field in the machine learning community called IQ-driven learning or geometric deep learning, where people have studied how to encoding the problem symmetry in the neural network architecture directly to improve sample efficiency and generalization. IQ-driven learning has been very successful in many domains, including computer vision, molecular representation, trajectory prediction, pulse estimation, and so on. So one question to ask here is that, can we use such a method in robot learning? So the purpose of this workshop today is bring together researchers from both robotics and geometric deep learning to discuss how should we make use of symmetries in robot learning. So we would like the robotic researchers to share their experience in leveraging symmetries in robot learning of geometric deep learning from other fields that might inspire new approaches in robotics. Together, we would like to shape the vision of the field of symmetric robot learning. So today, we have the great honor to invite a distinguished lineup of speakers. We will have Dr. Andy Zeng from Google, Professor Wang from Peking University, Professor Hao Su from UCSD, and Professor Maani Ghaffari from University of Michigan to tell us about their experience in using symmetries in robot learning from different perspectives. At the meantime, I'm also very excited to invite two experts in geometric deep learning, Professor Tess Smidt from MIT and Professor Erik Bekkers from UVA, to share their perspective of geometric deep learning. So here's a schedule of our workshop today. You can also check out the workshop website or scan the QR code to find the detailed schedule. So before we start, I would like to mention that the workshop is going to be recorded. So if there's anything that you think shouldn't be made public, please let me know and I will delete it from the recording.
Thanks.
Okay.
Is it muted?
So let's start. So our first speaker is Professor Tess Smidt from MIT. Tess Smidt is an assistant professor of electrical engineering and computer science at MIT. Her research focuses on machine learning that incorporates physical and geometric constraints. So Professor Smidt has done many great works in geometric deep learning, including the very famous tensor field network and the E3N PyTorch library. So today she will be telling us about intuition for data types and interactions, including symmetry equivalent neural networks. So please take it away.
Speaker, and then lunchtime for 2 hours. So
all right, thank you for the introduction, Dan.
And then after that, a few more.
Oh, I might need to have you unshare your screen so I can share mine.
Talks and invited talks.
It's exciting to be here. I know very little about robotics,
we had quite an interesting,
I am very excited to learn from you.
Some of them
so
were
I
focused
thought today what I would do is I would share
some of them more
again some intuition for some of the
that
types of interactions that you'll find in symmetry equivariant neural networks, and I'm going to stick specifically to 3D symmetries, so 3D rotations, translation, and inversion. And just to give you a flavor, the types of interactions that go on inside these neural networks. So first I want to start off with sort of one of the many motivations for using symmetry in neural networks. So if we are dealing with data that originates from a physical system, one way that we describe physical systems is using coordinate systems. So for example, this could be my origin, and this is my X, Y, and Z direction, but I could also use this other coordinate system, which has a different origin and a different X, Y, and Z direction. So let's say I have this physical system, it has a robotic arm, it has this teddy bear. I could use either of these coordinate systems are perfectly valid ways of describing the same physical system. And importantly, I can always actually change between these two descriptions. Numerically, they will look different, but they really mean the same thing. I can change between these two coordinate systems using the symmetries of 3D space. So translating my coordinate system, rotating my coordinate system, and even possibly inverting my coordinate system. We typically use right-handed coordinate systems, but you know, for some reason, someone chose a left-handed one. That's also a perfectly valid way to describe things. Okay, so what does this have to do with machine learning? Well, if I give a machine learning model, a traditional machine learning model, these two different descriptions of these systems, so description 1 and description 2, it's going to see these systems as completely different. Numerically, they're not the same. Why should it think that they're the same? However, it'd be really nice if we had methods that recognize, okay, given that I have 3D space and it has these symmetries of translation, rotation, and inversion, it'd be nice to have a method that kind of groks that from out of the box, so it understands it just from the get-go. And so we can build these symmetries into neural networks. So in the case of Euclidean symmetry, so also known as E3, it's the group E3, same thing as rotations, translation, and inversion. We can then have a model that even without training, understands that the descriptions of the physical system from coordinate system 1 and coordinate system 2 are the same thing, just described differently. So this is one of the motivations for doing this, is that having a model that actually understands this without training. Okay, so waiting for these to load. So equivariant neural networks, or Euclidean symmetry equivariant neural networks, E3 and Ns, differ from traditional networks in the following 3 ways. Part of it is sort of what type of data that these models take as input, have as hidden representations, and give as output. We actually have to define how our data transforms according to our symmetries. Furthermore, this then impacts how things interact inside the model. Suddenly, the types of interactions become much more rich and much more well-defined. And then last but not least, I want to talk about how we actually go about featurizing geometry in these models, because one of the reasons why we might be interested in using these models is to describe geometric data, so data that's actually in 3D space. It might be decorated by a variety of features, but a lot of the times we're very interested in the geometry itself. Okay, so let's get started. So when we have data from a physical system, different types of data behave differently under group action. And group action is just the fancy term for what happens to this data if I apply these operations, these symmetries of my system. So what happens when I rotate it? What happens when I translate it? What happens when I invert it or apply a mirror operation? So, and in this case, I'm going to drop off translation for now. And I'm just going to focus on rotations and inversion because that's the part that I think is the trickiest. So this is also known as the three-dimensional orthogonal group. So just rotations and inversion. So it turns out any type of data, any inputs that you could give me, any learned representation that a model might learn, any outputs that you might want, any of these types of data can be broken up into simple components that have two properties. They have a definite angular frequency, which basically tells you if I rotate my coordinate system, how quickly does this data change? Does it change at the same rate as the rotation? Does it change at double the rate? It turns out that these angular frequencies must be a positive integer. And then there's parity, which is basically, does this piece of data, if I invert my coordinate system, if I apply a mirror operation, does it flip sign or does it stay the same? Does it look the same if I invert my coordinate system, go from right-handed to left-handed, or does it not? And so these are only two features that you need to know in order to basically know how this data acts. So let's make this a little bit more concrete. So here are some examples. Let's start with things that have zero angular frequency. These are pieces of data that you apply rotation, it doesn't change this piece of data. So this is probably the most common or most familiar example, which is a scalar. So you might use a scalar to define a classification label. Let's say I want to make a network that can identify different animals such as rabbits. So the fact that this is a rabbit doesn't change if I rotate the rabbit. It also doesn't change if I mirror the rabbit. It's still a rabbit. It might look a little different, but it's still the same rabbit. Here's one that is maybe less intuitive. And this is the notion of you have a scalar, but it behaves the opposite under inversion. And this would be the difference between saying, okay, not only do I want to classify that this is a hand, I want to classify that this is a right hand. Now, if I change my coordinate system, or if I invert this physical system, now I'll get a left hand. And so this is called a pseudoscalar. So the fact that it's a hand doesn't change under rotation, but whether it's a left or a right hand will change under a mirror operation or inversion. Okay, let's go one step further. Now let's talk about things that have the same rate of change, the same angular frequency as a rotation of your coordinate system. So the most familiar of these types of data are going to be vectors, which you might use to describe, for example, 3D coordinates. If I rotate my coordinate system, that coordinate changes at the same rate. There's this other thing called a pseudo vector, and it is actually the same type of object that a rotation axis transforms under. And this at first may seem unintuitive, may seem like, well, aren't rotation axes also vectors? And I think hopefully this is a helpful example for why that is. So one way to define a rotation axis is to take a cross product. So let's say, okay, I want the rotation axis that is perpendicular to the plane defined by X and Y. So I take X cross Y and I get Z. Now let's invert X and Y and do the same thing. So if I take minus X cross minus Y, I still get Z. And so this is very much still like a vector, it still points in a given direction. But if I invert my coordinate system, if I go from X, Y, Z to minus X, minus Y, minus Z, this quantity remains unchanged. And so it's actually a distinct object. So we could continue. There's an infinite number of these objects, but I think just these two examples already kind of give you a flavor for why these objects are distinct and also why they might be a little intuitive and unintuitive at times. So these distinct angular frequency parity objects are called, in the language of group representation theory, they're called irreducible representations, or IREPs. And the reason why these IREPs are special is that they are distinct vector spaces that don't interact, they don't mix when I apply the elements of my symmetry group. So for example, if I take a random element of O3, so a random rotation, a random mirror, any operation, I've just chosen a smattering here, what you'll notice is that, and let's say that this element is acting on a vector space of one scalar, so the rabbit example, one pseudoscalar, the hands example, a vector, your normal coordinate, and a pseudovector, a rotation axis. What you'll notice is that this matrix is what we call block diagonal, and that these different blocks are not talking to each other. And so this is what it sort of means for something to be an irrep, is that it's kind of existing in its own vector space and it's not talking to anything else. And I think this is a super powerful result from representation theory, because no matter how advanced your machine learning algorithm is, if your inputs and outputs and your hidden dimensions behave predictably under rotation, I can provably decompose your data into these irreps. Provably. So it's a very powerful result. Okay, so many equivariant methods actually only use scalars and vectors. This isn't necessarily problematic, but it's important to note that it's not the only thing that you can do, that there's actually a lot of other data types that you could use to represent your system. So by choosing to only use scalars and vectors, you are inherently limiting the expressivity of your model. And this is not necessarily bad, just you need to be aware of it. It can also help with the computational efficiency for reasons that I'll show a little bit later. So let's talk about interacting data. So let's just start with scalars and vectors. Let's say, you know what, I only care about scalars and vectors because those are the things that are most familiar. Those are the things that show up in my data. And let's just go about multiplying those. So it's really easy to multiply scalars. You take a scalar times a scalar, and you get another scalar. Good to go. Now let's take a vector times a scalar, and all it will do is scale the vector. So it can't change the direction of the vector, but it can change the size of the vector. So we're good there. So we're still with just scalars and vectors. But now let's take two vectors. The most general way to multiply two vectors is to take their outer product, which produces a 3x3 matrix. This is a more complicated object. It's not a scalar. It's not a vector. It doesn't have a distinct angular frequency. It can be decomposed into multiple irreps. So you may have also seen this symbol is used for a tensor product or outer product. So I'm going to put it here. But really, this 3x3 matrix has three objects hiding inside of it. We have the trace of the matrix, which is equivalent to taking the dot product of these two vectors. Then we have the anti-symmetric components of this matrix, which transform in the same way as our pseudo vector, so our rotation axis. Last but not least, but definitely least intuitive, is a symmetric traceless component of the matrix, which transforms as something with angular frequency 2 and is even under parity. If you want kind of a geometric picture in your head, you can think of a double-headed ray. So take a vector and attach another vector in the opposite direction. This is something that if I rotate it by 180 degrees, it looks the same. And if I invert it, it looks the same. And so that gives you a sense for what this part of the matrix is capturing. Okay, so why is this important? So even if you say, I only care about scalars and vectors because that's what's in my data, what I'm telling you here is even if that is the case, I can easily take your vectors and generate higher order irreps that are perhaps less common. So you can generate pseudo vectors and L equals 2 objects just from a single interaction of your two vectors. As you can imagine, so neural networks are composed of many sequences of similar operations. And so if I take now these objects and multiply them times vectors, I can create even higher order or more complex objects. So all of these different irreps that may seem kind of unintuitive at first are completely accessible as long as you have vectors. Furthermore, so another way of saying this is that if I have a model and I choose to say, I only want scalars and vectors in my internal representation, what you are implicitly doing is you are throwing out this information. So again, that can be okay, but it's important to know that you're doing that. Yet another way of saying this is that if you only use vectors and scalars inside your model, provably these are the only 3 types of multiplication operations that you have in your model. You can only have scalar-scalar interactions, vectors being multiplied by scalars, and dot products. Those are the 3 interactions that you can have. Okay, so why might you want to limit operations? Maybe not just to scalars and vectors, but maybe we don't want to do the most general thing. So the most general tensor product does not scale favorably. And the reason for this is that it preserves dimension. So in the case of my two vectors, I had a 3-dimensional vector space and a 3-dimensional vector space, and what I got was a 9-dimensional object. Now, you could imagine that if I have very large objects, let's say 100-dimensional space, 100-dimensional space, this starts to get large very quickly. So the most general tensor product is very expensive. So you might not want to do that, but there are other options. So in order to maintain equivariance, so in order for your model to act predictably under rotations, translations, and inversion, you can only throw out entire irreps from this tensor product. So again, going back to this example, I can't just decide to throw out these numbers or throw out these numbers. What I have to do is I have to specifically throw out either, this scalar, this cross product, or this symmetric traceless part. I have to throw out the whole thing. And the reason for that is that if I only keep part of those numbers and I apply rotation, my data is going to rotate out of the dimensions that I've kept. So it's important that you throw out only entire irreps. So decomposing this most general outer product into the distinct irreps it generates allows you to prune the interactions and make this tensor product more tractable. So instead of going from n times m to this larger vector space, you can actually make intelligent choices about which parts of the vector space you want to keep around. And you can do this, before you run the model. This is part of the model design. So for example, we could say, you know what, I only want to keep around any data that has, that produces L equal to or less than 1. And so maybe I'll leave this out, but I will still keep my pseudo vector. So these are the types of options you have in an equivariant model. All right, we're doing time, good. Let's talk about featurizing geometry. So the typical input to, in this case, a 3D Euclidean symmetry equivariant neural network, or an E3NN, is geometry and features on that geometry. So here's an example of 2 point masses. I've got my little coordinate system. These point masses are located at the following coordinates, and they have the following features. They have maybe a point mass, they have velocity vectors and acceleration vectors. So I don't stop here. I have to categorize my features by how they transform under rotation and parity as irreps. So I have one scalar, one vector, and another vector. So this is the information I need to give to my model. So the question is, what do we do with the geometry? So typically the way that we interact our features and our geometry is that we use convolution operations, or something that looks like a convolution operation. And so for these types of models, our equivariant convolutional filters are based on the following form. If I have a single filter, so in a 2D image case, you would have like a little pixel grid. In this case, we may have points in 3D space. So instead of a fixed grid, we have actually just a function that you query. So let's say I have my convolution center, I have my nearest neighbors, and here I put atoms. This was something from another talk because I deal a lot with atoms. So I have a relative distance vector, and that's what's going to go into my filter function. And all of my filter functions will be built of many filters, and it will be built from learned radial functions. So this is where all the learned parameters go, and spherical harmonics, which are functions that look like this. They are the same functions that we use for actually hydrogen orbitals, but that's more of a consequence of math, not a consequence of physics. So in order to interact your inputs with the filter, you do one of these tensor products. So what I'd like to do in these next slides is give you an intuition for why you use spherical harmonics, and also what happens when you use more spherical harmonics in your filter, because this is also an option, like up to how many spherical harmonics do you include in your filter. Importantly, the spherical harmonics are very special functions when we think about 3D rotations and inversion, because they actually transform as specific irreps. So if I have these spherical harmonics, they have angular frequency L, and their parity matches whether, if it's an even L, it doesn't flip sign under inversion, and if it's an odd L, it does flip sign. So we have the 0th spherical harmonic is the same as a scalar. The L equals 1 spherical harmonics actually are directly proportional to XYZ, so they transform in the same way as a vector. And then we have our higher order ones, again, flip-flopping parity as you go to higher L. So we use spherical harmonic projections as kind of part of convolutions, and also as in a lot of other fields, we actually just use them as very useful descriptors for describing local geometry. So I'm going to take this example where I have an octahedron, and I'm going to try and describe this local environment of this center point right here. So we have 6 relative distance vectors, r sub ij. And what I'm going to do is I'm basically going to take its Fourier transform, is one way of thinking about this, but I'm basically going to compute this projection onto spherical harmonics. I'm going to take this vector, I'm going to stick it into these spherical harmonics, and then I'm going to attach it to another spherical harmonic. This is basically the same thing as a Fourier transform. If I'm using real spherical harmonics, but if they were complex spherical harmonics, I'd attach a little dagger to it or a complex conjugate. And so if I perform the projection of this point, which is effectively a delta function, if I take this projection up to some L max, I'm going to get a blob. If I increased the maximum L I use, this eventually would become a peak, a very sharp peak. But I'm going to stick with L equals 6. Some people might think, well, why can't I just use the coordinates as is? You can. And actually, the L equals 1 spherical harmonics are basically using that relative distance coordinate as is. So that's already included, but you have the freedom to go to higher L. And this will become more clear in the next slide why. So, okay, so I've projected this one point. I can do the same for the other 5 neighbors. And now let's say I want to now describe this entire environment, not just these individual points. Well, what's really nice is that each of these descriptions, each of these coefficients are just vectors. And so if I want to describe this combined environment, I just sum them. And this is what that function will look like. And so this is now a projection of this entire local environment onto spherical harmonics. Why is this useful? Well, I can have a variable number of neighbors, but that's inconvenient because it's a variable length, and neural networks have a real hard time with variable length objects. So I've just converted my variable number object into a fixed length vector of fixed number of coefficients of spherical harmonics. And this allows me to describe a distribution of neighbors. Let's make this a little bit more concrete. Here are the actual coefficients. So here are the 6 single point coefficients. And then what I did is I summed them to create the signal for the vector for the octahedron. And the thing I really want to point out here is this. These individual points have coefficients in each of the L's, in L equals 1, L equals 2. One way to think about this is that if I take a peaked signal and I take its Fourier transform, I get all frequencies. However, I've just added together peaks that are in a very symmetric configuration, and this has resulted in cancellations. So I don't actually get zeros for L equals 1, L equals 2, and L equals 3. And this is very common. This is a typical signature of high symmetry objects, is that lower harmonics cancel. So if I was only using up to L equals 1 features, I wouldn't be able to tell the difference between a sphere and an octahedron or a tetrahedron or several other slightly higher symmetry objects. So this is also something to be aware of, is that by limiting what features you use in your model, you might be kind of killing its sensitivity to certain types of situations. So you might say, okay, well, I'm working in the real world and nothing that I'm working with is as symmetric as an octahedron. Excellent point. However, these types of features are actually quite robust to noise. So what I'm going to do is I'm going to take the no noise octahedron and I'm going to perturb the locations of its neighbors with increasing standard deviations, and I'm going to plot the spherical harmonic projection of those configurations. So here's 0 noise to a standard deviation of 0.1. The length of the neighbors is 1. So that's a 10% error you can think of on these positions. And what you'll notice is that these coefficients don't change much. Part of that is because your higher frequency L's are the ones that are going to be sensitive to these distortions, not your lower frequency L's. And so even though this really does not look like an octahedron, it's quite distorted, you'll notice that the L equals 1, L equals 2, L equals 3 components are still very faint. So something to take away from this is that this is a pretty smooth distortion where it looks smooth in this feature space, and that symmetry is not binary. you still get cancellations, even if things are not quite symmetric. And I think this is a significant thing to keep in mind when constructing these networks. Okay, so I've only got a couple more points. So you might ask, what LMAX should you use? Like, what types of features should you have in your model? Well, we do find that basically having at least L equals 1, so at least having vectors, is better than not having vectors. So if you're only having scalars, what we find is that equivariant, so L equals 1 or greater, and invariant methods. So equivariant methods are more accurate, and they are also more data efficient than if you just use scalars. So the way that we measure data efficiency is we make a plot of the log error. So we have a trained model, and we measure the error of this model on a test set, and we have the number of training examples that it was shown. And what this is showing is the accuracy goes down with the more data we train it with. However, equivariant models learn more quickly than an invariant model. So I don't need to show it as much data for it to become as accurate as an invariant model. And it's learning much more drastically. So this is a power law. So if I show a equivariant model more data, the amount it's going to learn is much greater than that of an invariant network. So this is very helpful. This is very useful. Furthermore, for many tasks, so a lot of my work is in the domain of atomistic systems, so molecules, crystals, proteins, and we do things like use these models to predict quantum mechanically accurate molecular dynamics data. We find that higher order interactions improve data efficiency and accuracy. So basically, the higher L that you go, the better it gets. Now, it also gets more computationally expensive. So your mileage may vary, and you'll have to balance your computational efficiency with the expressivity of your model. But at least you can go in armed with the knowledge that all these interactions and all these different types of data, all these data types, higher L's and parity and things, these are all options available to you, and you can make an informed decision about what's best for you. So with that, I'm going to go ahead and leave these takeaways, and I'm very happy to take any questions that you have.
All right, thank you very much, Professor Smidt, for the brilliant talk. So do we have any question from the audience, both online or here?
Sure. Yeah, probably for the online folks.
Yeah, great talk. So what is the trade-off actually between sort of the I guess training efficiency and computational efficiency? So let's say I'm working robotics. I have a real-time task. I need to learn something that has some symmetries. Maybe I'm manipulating an object, and I've described that object through like the point mass example, which is great.
Yeah.
And I have like maybe 10 hertz that I need to compute something really. I'm being very generous here.
Yeah. So you have something that has like a real time need.
Yeah. Yeah. Exactly.
Yeah. So great question. I can't give you a clean answer because it will depend on your use case.
Fair.
It'll depend on how big of a model you even need to learn your task. Like,
sure.
If you can get away with a small model, you can actually go to fairly high L. There's some nuance too with like, in these interactions, in these tensor products, not only can you prune based on L, you can actually like say, I'm only going to take L equals 2 times L equals 1 objects and anything that comes out of that. So you can be very choosy.
Okay.
So it gets a little bit in the weeds. I would say you start off simple.
Okay.
You start putting in some more complex operations. Make sure that the model's training well with them. There's some nuance there. And then you make an informed decision from there. So I definitely can't tell you, but I can definitely say that you should kind of start simple, make sure it's training,
sure.
and then go up from there, and then make the judgment call as to whether the accuracy versus computational efficiency trade-off is worth it for you.
Okay.
Another thing I'll add is that we haven't actually. I don't think we've done enough to optimize the operations of these models. So I think the hope is I've got a master's student working specifically on this. So hopefully we'll have some faster kernels out there for these types of operations.
Cool, thank you. To follow up, actually, one other question is, so as output, do you also get uncertainty? So even if you're doing error, that might not necessarily mean that in evaluation you'll have high accuracy. So you might have some trade-off there. Is there work that you've done where you actually have this sort of explicit, like, hey, this is how much uncertainty you're getting, probably, given the evaluation set?
Yeah, so uncertainty from neural networks is a very rich subfield that I'm not a part of.
Okay.
So I have not done work, but there's a lot of people who've done some really excellent work. One thing I will say, though, is that having equivariance versus not having equivariance, first of all, provable guarantees that your model's not going to do something crazy when you rotate your example.
So
that's great. So you won't have any problems there. So provable guarantee that it's going to do the same thing. Additionally, kind of what I showed with the spherical harmonic features, you have a certain guarantee of smoothness because of how these things are built.
Right.
That also seems to, this is still kind of an open question, but it seems to guarantee certain, that they generalize well. These models tend to generalize well or generalize better than invariant or non-equivariant models.
Assuming the system you have is smooth as well. So if it's non-smooth,
yeah. So if you're gonna have like shocks in your system, I think lots of things are gonna struggle. I think learning's gonna struggle with that generally. But
dynamic
yeah, so you have certain guarantees, but as far as like quantifiable uncertainties, I would say that's like a different subfield. But there is a lot of literature in that direction, but I don't have much to say on it.
All right. Thank you so much.
Yeah, thanks for the question. Or I guess up to Zeng, whether we have time.
Hi, thank you for the great talk. I was wondering how the process of selecting the order of the external products actually goes. Is it based on the physics of the system that you're trying to represent? Like, for example, I hope I'm not saying something stupid, but I think in robotics, the higher order external products that we have are only cross products between three-dimensional vectors and three-dimensional vectors. So will that be a considerable reason, reasoning line to say, like, we should truncate our models to have only operations on this order, or?
Yeah, I think like a lot of things with neural networks, because effectively you're designing a model that will fit some function, and that function has to be optimized. So I think just trying things out is really the best approach. I think sometimes you can try and reason about, oh, this should matter, and really I always encourage people to just test it out. Like, you can start with a hypothesis, but make sure you test it out. So as far as like figuring out what things to leave on, leave out, right now most of the argument we make is usually just computational efficiency. That's the primary bottleneck.
Perfect. Thank you.
Yeah, thanks for the question.
One more question. So it looks like you're mostly considering IREPs of O3.
I have a follow-up question.
Do IREPs of E3 come into play?
Yeah, so it's a great question. So the IREPs of translation are really interesting. They don't. They come up a lot in physics, actually,
as you said,
especially
if you
solid-state
incorporate
physics.
prediction model in the
The
RTT
typical way we deal with translation when kind of dealing with physical systems is we use relative distances. And so we're not truly dealing with the translation group. We're not dealing with the fact that we actually have chosen an origin, and then we want equivariance under that. Like, one way to think about it is like, I do a Fourier transform, like a normal Fourier transform, but my Fourier transform is kind of ambiguous up to a phase. So that phase factor typically isn't used in neural networks. You could have some, but it usually comes up when in sort of this frequency space or this transform space, and most neural networks don't use it. So usually we just use relative distance vectors, but there are applications in physics where it does matter. And in that case, you actually do use the IREPs of translation.
Because E3 is not a direct product, so it doesn't just separate out so neatly.
Yeah, it's not neat because you basically get these composite operations of like screw axes and glide planes. These models will still be even if you're just doing relative distance vectors, it will still be sensitive to like screw axes and glide planes. But it is true that they're not completely treating those composite interactions faithfully, but and it's an interesting question if there's a better way to do that would impact training. But so far, mostly dealing with the rotation group has kept us busy enough so far, but it's a great question.
Thank you.
Yeah.
All right, thank you so much for the great question, and let's thank Professor Smidt again for the great talk. Okay, so next, our next speaker, Professor Hao Su is an assistant professor of computer science at UCSD. He works in algorithms to model, understand, and interact with the physical world. His interests span computer vision, machine learning, computer graphics, and robotics. So Professor Su has developed widely used datasets and softwares, such as ImageNet, ShapeNet, PointNet, PartNet, Sapien, and ManyScale, you name it. It is my great pleasure to invite Professor Su to give a talk on learning generalizable policies by 3D reinforcement learning. So please.
I didn't clear about the how you track. It means the low level control in this one. So
it's good, right? Hello? Okay. Okay. Thank you very much for the invitation. I'm very glad to be here and present some of the recent works from our lab. Somehow I really enjoyed the talk just now, which is a very mathematics and symmetry centered talk. Now for the rest of my talk, it will be a little bit different kind of flavor. So this is more of some empirical results, which will will be more explaining how the neural networks are applied to reinforced learning. But hopefully those kind of results still inspires you of how to apply those kind of symmetry results in the reinforced learning systems. Okay, particularly I'm going to talk about learning generalizable policies by 3D reinforcement learning. Here the 3D basically means 3D data is input. Okay. So by general skills, what we mean is we would like to have a kind of, for example, navigation or manipulation policies, which are robot policies, that'll be very robust. Against the object geometry variation, initial position variation, physical variation, so on and so forth, kind of variations. And obviously, this is the motivation for us to think of symmetry, right? Okay. Yeah. Most of the reinforcement learning work so far are basically based upon input from the pixel space. Now, if you rethink about where shall the representations live, there might be a question that interaction actually take place in 3D space, and therefore it might potentially be a better representation to consider most 3D native representations. For example, the grass pose prediction, which is actually not really such a trial and error learning, which is more of a supervised learning paradigm that originally started from depth maps based representation. But gradually
that you were
it moves to
the obstacle
3D input.
I guess in all of your simulations.
So that also reminds us for the visual RL, which was recently quite hot. What would happen if you also think about 3D input?
Cars that were moving in the other
there are a few such kind of works in the past few years. Some even got the best paper awards, but in robotic conferences. But I guess there are still a lot of fundamental questions. In terms of building the strong baselines and exploring the basis of it. In particular, I would like to ask a question. Can 3D point cloud practically provide a more efficient and effective representation in RL compared to 2D pixels? I'd like to start from a minimalistic motivating example. For empirical people, reinforcement learning people, they like the kind of curves. Think of a game that in a 3D space, there are two, there's a green sphere. The green sphere will move towards the red sphere. Every step, there's kind of a delta movement. And then there's a reward, this is the dense reward. It's the L2 distance between the centers of the two balls. Okay, now this is a very simple example. And you can, for example, train PPO or SCC, the kind of reinforced learning algorithm you like. Okay, and here the tricky part is the representation of the input. Look at the top right corner. You can think of, for example, using RGB only input, or also adding the depth map of the scene, or you can consider using a point cloud of the scene as input. Okay, so bottom right shows the training curve of different kind of methods, and a lot of information. But if I distill it, these are the three major observations. Look at the dashed line. Look at the green lines. The green lines. The green line is the learning curve for only using RGB input. So basically, we want to move the sphere to a target position. Only looking at RGB, you don't tell like the depths. And therefore, we find that the training is super inefficient. Okay, basically it cannot achieve the task. If you will add like the depth information, it might be able to solve the problem, which you look at the blue line. But here you have to use very strong data augmentation. Now, if you consider like point cloud-based representation, even without any kind of a data augmentation, it's actually being able to learn faster, and in the end also converges better. Somehow, because like 3D native representation might allow us to like learn kind of environment representations better, and I will explain more. Okay, there are more results. The more realistic experiments, which is in the simulator. That's the Maani robot simulation platform development lab. We're constantly set up like you were doing the mobile manipulation. For example, a mobile moves the chair, and hold the chair and push it to the target location. And the input for the robot are 3 egocentric cameras, which form a panoramic view. Okay, and this camera is mounted at the head of the robot. So if you check the results, you observe similar trends as the minimalist example. That like looking at the four tasks, open a door of a cabinet, or pull out the door cabinet, or push a chair, or like moving a bucket with a ball in it. Compare the performance of different kinds of input representations, you still observe that the point cloud performs better than RGB-D or RGB data. Somehow, by analysis, we find that it's because like in the 3D representation, 3D native representation, it's easier to handle like the relative relationships like between gripper and handle, which is a kind of agent-object relationship, and then also object-object relationship. For example, we're pushing the chair towards a goal. Okay, so the RGB-D only input is not that efficient. I'm going to first show some major empirical observation and then give more in-depth analysis. Well, if you will consider, these are the set of counterexamples. Consider the task of DM control. Okay, they are basically only 2D games, only 2D games. There's like basically objects moving in a 2D space without really, the depth is not having any real effects. We find that in this kind of setup, of course, you can still like represent the agent and the objects as kind of a point cloud, but the point cloud RL here does not really show the advantage over image RL. That will mean like, it's not just like you are using point cloud is better. It has to be like, there must be some kind of 3D reasoning. Now, further observation is, if in a game, there are certain kind of relationship reasoning that is important. Like for example, in the reacher task and the ball in cup catch, like for the reacher, the end of robot arm needs to approach a particular point that needs relationship reasoning. In this kind of a case, among those kind of point cloud based results, which is like look at the red curve, it's performing like more efficiently compared with those that do not need a strong relationship reasoning. Somehow it's because like point cloud gives you the coordinate points, which is a kind of arithmetic representation of the input, closer to the like compared with 2 pixels, that's easier for computations to be made.
Great.
Okay, so these are some of the high-level results. And let's look a bit deeper into like some of the design factors of the backbone network. Now, if you just care about like mathematics, this might not be that interesting. If you really want to push the 3D deep learning work, these are perhaps a very useful results for you.
I think we have our first presenter online.
Okay, so in terms of like applying the point cloud representation in reinforcement learning, this is actually pretty tricky.
We can.
Okay, so perhaps you know, like RL tuning is always tricky. And there's a big design space. Like the backbone architecture choice, like the kind of data augmentation, which essentially is related with the kind of symmetries of the data. And with certain post-processing, or like you will how process the temporal information. I will focus just on the 2. because this is more relevant to this workshop. Okay, so we'd like to apply a bit of an ablation study on the neural network architecture to process the point cloud. So first of all, to be clear, let me give you a bit more details about like what is the input. We think like the scene is represented as a point cloud, and then you need to write down the coordinate. Here we're choosing the robot base frame, and later we'll show that it's actually not the best frame. Considering symmetry, there's a better frame representation choice. Okay, then we think like every point, we also add RGB information and also a binary mask. There's whether this point belongs to a certain kind of target object or part of the target object. Okay, this is kind of like the point cloud augmented kind of a point cloud representation. And we tested, basically compare two kinds of architectures. One is point net, and the other is sparse convnet. By point net, if you work in the field of point cloud perception, you might have heard of it. It's kind of a classical work, which was my PhD time work. That you will first process each point independently, and then use max pooling to aggregate information and then have certain kind of post-processing that gives you the permutation invariance. And then for the sparse convnet, is basically kind of a volumetric network that you decompose the space into cells and then record the occupancy of the cells. And you apply the 3D convolution. Now, in order to reduce time complexity, you consider like exploring the sparsity. And both approaches actually apply layer norm. Especially I want to mention for the point net architecture, the layer norms are applied at second and third layers, which is actually very tricky because the layer norm is actually encouraging a certain kind of symmetry. They tried, if you apply this layer norm to the first layer, which makes basically the method rotation invariant and translation invariant, it actually greatly, you can't train. Okay, so adding the symmetries in our setup is actually much more trickier in a supervised learning setup. Okay, but I'm not saying that it's bad, though some smart ways to add it, which I'll explain later. Okay, so let's try to compare the performance from two types of networks. Here are the basic observations. Look at the curves. These are on the Maani scale task I just point out. First, compare the colors. Like the red curves corresponds to point net performance, and the orange curve is the sparse convnet results. It's pretty obvious that the point net is actually performing better than sparse convnet, the point 1. And the point 2 is the sparse convnet, which is kind of a convolutional neural network that is like it itself has certain kind of translational invariance, will be boosted very much with some data augmentation. The data augmentation are looking at compare the solid curves and the dashed curves. Okay, the data augmentation includes both translation and rotation. Okay, so basically the sparse convnet, which is like a type of convolutional neural network, is very strong kind of data augmentation to be able to address some of its limitations to conquer like the symmetry issues. Point net itself has some advantage. To be a bit more concrete, in a setup of like a manipulation research, we think perhaps two types of point net might be worth thinking about. The one is like, which was already reported in the original point net paper, that's for the semantic understanding task, that is very robust to corruption and occlusion. The left are the two curves. Now the left is like when you are reducing the number of points in the point cloud, throwing out a portion of the point cloud, what is the perception performance change? You see, like if you're using the volumetric network, it's kind of like sparse convnet, and the performance drops very fast. So that's like occupancy plus convolution. That's not quite a kind of approach giving you strong like robustness to missing points. Whereas point itself is better. On the right is like if there are certain points missing in a structured way, like caused by self-occlusion or occlusion, it's still able to robustly perform segmentation tasks, for example. Okay, a second experiment is conducted particularly for reinforced learning. Here we're studying if you are using like point net with kind of a point cloud network as the policy of value networks, how robust the value function prediction can be. We did a kind of a perturbation experiment that we consider like translating the entire point cloud and check the change of Q value. Now, if it is quite a good network that respects the symmetry, then the Q value should not change. Now, if not, the Q value here in terms of relative sense might change a lot. Look at the two plots. Left is the sensitivity analysis plot of the point net, which we see x-axis is the amount of perturbation, and y-axis is like the relative change of the Q value that's kind of stable. I would say like this result has only to apply to the point net with the layer normalization. Original point net is batch normalization. We can't use it. It has to be the layer normalization. So here, layer normalization helps to improve the imbalance, but at the same time, preserve the sensitivity, like preserve the discriminative power at a reasonable balance. The right-hand side is the sensitivity analysis result of sparse ConvNet. There are 4 bars, each bar, 4 color bars, each corresponds a kind of environment. But basically what you see is like, they are much, much higher. Like the Q value for the sparse ConvNet without sufficient data augmentation is very bad. Okay. So we kind of now understand like, okay, some of the symmetries, some of the invariance is important, but at the same time, it has to be sensitive to or discriminative enough. So next, I'm going to introduce a kind of a recent work from my lab, which was published in Coral, that actually take care of choosing a coordinate frame for representing point cloud that will increase the robustness, but not sacrificing its expressive power. Okay.
Can everybody on Zoom see
so recall the typical architecture of a reinforced learning. There is usually an actor-critic kind of architecture. For the actor and the critique networks, both can be represented by your 3D networks, for example, like point net or sparse ConvNet. Okay.
So the question becomes,
but what is tricky is a problem people don't quite think too much is, now you have a point cloud as input. In which coordinate frame will you represent this point cloud? In fact, our study shows that the choice of a coordinate frame matters very much for the performance or the learning curve of the reinforced learning.
Above or below the lake.
Okay.
And these observations,
so
these sketches,
this was already known at the time when people were doing supervised learning. Like for example, this was the work, 2018 work, that's called first-time point nets and the early work for autonomous driving. And so there, people try to apply a number of transformations of the coordinate frame in order to obtain high-quality results.
And so we choose to model the
so if we come to the robot learning, in fact, this choice of coordinate frame is actually still very important. But there are just a lot of choices, potential choices. Like you may represent point cloud in a world frame. You may represent it in a robot base frame.
So what actions you can take.
Which means like there's a mobile robot, you add a kind of frame at the base of the robot. And then you can consider like an effective frame representation of point cloud, which means like at the end of gripper, you add a kind of frame to represent the world. And then you can also consider the detect objects first, and then add a kind of frame at the target part to be interacted with. Okay. So this kind of a choice of frame is implicitly assuming a kind of a symmetry of the target you're representing. Now, first to show some empirical results. The empirical results is like you consider training RL with each copy of the point cloud under different frame choices. In general, you find that the effective frame representation of the point cloud or the target part of frame representation, they will outperform maybe the default choice like the world frame or like the robot base frame. Most of the case that is true. Okay, and this observation is quite consistent whether you're using like point net or sparse ConvNet or any kind of 3D backbone networks. And if you think more, you find like I mean, it's actually very intuitive why this could be true. It's just like people might have overlooked this factor, that the choice of frame is imply a kind of alignment among the point clouds across time frames. For example, in any effector frame,
collecting the reward from the target likelihood distribution.
The advantage is if you have to reason about like the relative relationships between the gripper and, for example, the handle of the door, right? Well, initially, this is a binary relationship reasoning task, but if you will actually normalize the point cloud by choosing the end effector frame as the origin and decide this kind of orientation, you just need to do the pose of the handle as estimation. So that's reducing a binary estimation problem to the unit estimation problem. Okay, the amount of training data you need is actually much reduced. So here's an example that the choice of the frame actually is changing, or it's like intrinsically leveraging the symmetry.
This is the behavior that we expect with this approach.
Now, if you have a robot that is moving, that has two grippers, there might be more design choices, right? Like left hand gripper and the right hand, both of the grippers each have this own frame. Okay, you have the scene. Which frame you should choose? Now, perhaps for the maneuvers of the left hand, you choose the left hand frame. For the actions to be performed by the right hand, you choose like the right hand frame. So that's tricky. So there are further work that we consider, like there's work that's called frame minor. In aspers kind of mixture of aspers that give me the number of potential frames. Each of the frame give a representation of point cloud and make a prediction of action to take, and then in some way mingle them together. You could consider using like mixture and aspert, which is linear combination of the decisions or features. You can also think of like transformers, which you do like self-attention. But in general, you find that by being aware of the frame choice, now you can perform better than a single frame. If you do certain kind of visualization, for the sake of time, I don't have the time to show it. We find that, for example, in the mobile manipulation task, in the navigation phase, the point cloud represented by the robot base frame gets more attention, and when the manipulation starts, the end effector frame will dominate. Okay, so I think like this is also interesting and intuitive. And very lastly, I want to emphasize one of the additional advantages of point cloud, which actually not quite much, or 3D native representation, which is not quite much related with symmetry. Okay, think of this kind of a Bekkers manipulation task. You have 5-finger hands. Actually, here is a 4-finger hands to grasp and manipulate objects. Okay. So, when you're trying to do this, one of the significant issues is like there will be like the occlusions of the point cloud caused by the object. Like you have occlusions to the hand of the gripper caused by the object to be grasped. Okay. But for the robot, we know its own state, which is the proprioception information, that would allow us to easily hallucinate where the grippers are, which is like how humans perform, right? You know where your hands are when you are manipulating. So 3D native representation in the 3D space, and therefore editing is very easy. So you can just add the occluded points back, okay, and that will just make the learning easy. Now you consider 2D RL that's in the pixel space. How can you do this kind of hallucination? I don't see a very intuitive way at least. Okay, so that's an advantage. You consider 3D native representation that gives you this kind of advantage, and also it makes us to like removing points. Like in order to improve your robustness, right, you need certain kind of attention, and you need like to attend to the area that includes the object of interest. Now, if you're using 3D representation in 3D native space, cropping out the areas that's not interest to you, like the background, is very easy. But on 2D images, because of perspective projection, this gets tricky. Okay, finally, I'd like to show some videos, right? Now for the blue points and the original points, the red points are like those hallucinated points.
So here's problem statement. Let's say agent I and J
additionally,
estimating on common
not sure better audience here cares about the question. I'm going to say like for the 3D point cloud representation, this is quite geometric and there's no appearance information that is like causing a lot of troubles, and therefore the same to real domain gap can be small. The video on the left is actually from simulation, the right is from the real world, but in fact they don't look that different. They don't look that different for the networks. And then,
for example,
yeah, there are some results that shows the generalizability to unseen objects. Okay, so to summarize, we see like for tasks that require strong 3D relationship reasoning, 3D RL can be better than 2D RL theoretically. And then this is actually quite important for manipulation tasks, because manipulation a lot of times is about the relationship between the gripper and the object to be manipulated. And thirdly, when you are considering like networks for reinforced learning, some of the concerns are actually very different for the 2D case. I forgot to mention like in a detection task or recognition task, in fact, the sparse COMNet usually outperforms PointNet nowadays. I mean, if you tune it carefully, the sparse COMNet is actually stronger network. Whereas in reinforced learning, what we care about is not really whether they are strong enough. More is about like the robustness and fast learnability. Now it's easier to consider certain kind of like symmetry or invariance properties, even if the network may not be the strongest in terms of final recognition performance. By plugging in reinforced learning framework, it's better to resist the noises and like a lot of the corruptions in the learning process. That actually is a better phenomenon. So I think that this is actually the opportunity for those symmetry aware networks to be applied. If you find, you're always beaten by the leaderboard, on the leaderboard of recognition tasks. Okay, in the end, I also want to deliver a message like compares to 2D pixels, the 3D native representation, in fact, has a lot of unique ways to think of, especially in the reinforced learning setup. People are perhaps quite used to like just feeding the input to some network. But here, there are interesting ways, like changing the coordinate frame, like consider shape completion. I think like they are important, and for humans reasoning process, we sometimes implicitly use this kind of tricks to simplify the problem. Okay, so my conclusion is 3D RL as a new direction of the robot learning actually has a lot of potential. And thank you very much for listening.
In this paper, we propose a fault-tolerant Bayesian data fusion algorithm using agent reliability.
For the great talk. So, any question from the audience?
Was conducted to verify its performance, and it is shown that proposed algorithm has robustness to inaccurate data and can give much less conservative fusion results.
Thanks for a great talk, Hao. In geometric robotics, to get away for the effect of this change of coordinates, a lot of times we use body frame coordinates, and that's basically Lie group framework. The conjugation will make it agnostic or equivariant to what frame we're observing the problem, which I'll talk about it more in the next talk. So I wonder if it's one thing to make it agnostic, but I wonder in the supervised learning setup that you have, do you gain anything by having different frames and labeled data?
Right.
Beyond, being.
Yes. Actually, I would say like being agnostic a lot of times is very tricky. Like for example, if you particularly know you're doing recognition, you're just recognizing the semantic category. Being agnostic, being invariant is a good thing, because no matter how you change it, the fundamental, the semantic class does not change. But in RL, one of the points is to consider emergence concept. Some of the intermediate representations that are a bit implicit. And therefore, just making it agnostic a lot of times actually doing bad things. Yeah, it's not just a semantic information. So we find that it's actually a more trickier problem. There has to be a chance for it to be aware of the frame. Yeah. So like, for example, for the works presented by Tess, I mean, if you know the decomposition representation, you perhaps would feed the factors after the decomposition to the network. And then it might be able to leverage the part invariant or equivariant or very sensitive to transformations and discover some new concepts. That might be interesting.
To highlight this challenge, we consider a simplified model of the air-to-air compound maneuver.
Hi, thank you for the great talk. I have a quick question about these point representations as opposed to other volumetric representations. So with point clouds, you are processing the points that you actually see, but oftentimes because of occlusions or other reasons, there's kind of free space that isn't being accounted for. Do you think that these point-based representations are like somehow implicitly reasoning about occluded or kind of empty space? Or do you think there's like other architectures that we might want to combine with things like PointNet or sparse convnet in order to like handle that?
Yeah, that's actually a very interesting question. I think first of all, it's implicitly dealing with those kind of empty spaces. Because if you really check how the PointNet works internally, you find that it's actually learning some kind of, at least it is like learning some kind of a partitioning of the space. It's just like in volume representation, you are partitioning space in a quite a regular way, right? Like axis aligned way. Whereas a PointNet is implicit learning to use some curved planes to cut its space. Yeah, and then it actually does reason about the occupancy. I mean, although the network is simple, if you look at its behavior internally, it learns some of the very tricky ways.
Okay, thank you.
Hi, very interesting talk. I have a follow-up from Maani's question. What is changing here in the framework when you say that you have data, you're changing the frame? It's just the data that you're feeding, the stuff that is changing, or is something that you change also at the reward level?
The reward is unchanged. What's changed is only like the XYZ coordinate.
Okay, so, but do you think that maybe if you change the reward, you can get like also advantages like this? Because for example, you define that you want to get closer to the handle, and you change the reward. The reward may be simply defined as the distance between the hand and the handle, right?
That's a good question. Now, first of all, at high level, changing the reward is much trickier than changing the input representation. Because the reward, if you check like the RL theory, right, usually they assume it's something between 0 and 1. Even the magnitude will affect the learning rate very much. Okay, so it's not recommended to change the reward. And second, you mentioned about distance. I agree, and a lot of times it's actually learning the distance. But there are also like the factors that's not only captured by distance, like for the relative position between the gripper and the handle, right? I mean, it's in at least there are 6 degrees of freedom, right? I mean, considering like the pose of the object to be manipulated, 6-degree freedom, and distance is just 1 degree freedom.
Yeah.
So the point is, I think the entire symmetry of feature design faces question. You think that you're smart, you're designing certain kind of representations, but you're also omitting something, something very important. So there is a balance between the two. Yeah. Okay. So I think, practically, this is something that people have to think about.
At the post-session.
Thank you.
Thank you.
All right. Let's thank the speaker again.
Thank you, Sujong. Our next presenter is Symmet.
Yeah, so if some have more questions, we can try to ask more questions during the panel discussion session later on. Okay, so the next we'll have our first oral presentation. Is robotic manipulation learning with equivariant descriptor fields, generative modeling by equivariance, durability, and locality. The presenter is Hyunwoo from Yonsei University.
So, hello everyone, I'm Hyunwoo from Yonsei University, and I'm very excited to introduce our recent work, Equivalent Descriptor Fields. So equivalent descriptor fields, or EDFs, are SC3 equivalent models for end-to-end visual robotic manipulation learning. So it was originally published as a conference paper at ICLR 2023, and in this workshop paper, we aim to deliver the key insights of EDFs. Especially, we focus on the 4 design principles of EDFs. It is bioequivalence, generative modeling, steerability, and locality. So in equivalent robotic manipulations, we impose the equivalence to the end effector pose such that it follows the transformation of the target object. So the advantage of it is the data efficiency, generalizability, and robustness. Transporter networks are one of the most famous methods that exploit SC2 equivalence in robotic manipulations. They are highly data efficient for planar tests, and they can be end-to-end trained directly from test demonstrations. However, their efficiency is limited to planar tests and cannot be extended to highly spatial 6-degree of freedom tests because they do not have the full SC3 equivalence. Neural descriptor fields, or NDFs, exploit the SC3 equivalence, so they are very efficient for 6-degree of freedom manipulation tests, and they can also generalize to previously unseen object instances in arbitrary poses. But they cannot be end-to-end trained directly from test demonstrations, but they require pre-training with massive amount of data that are specific to the target object category. They also require object segmentation pipelines. To this end, we propose equivalent descriptor fields, or EDFs, to combine the advantages of these 2 models. So EDFs have the advantages of transporter networks, that they can be end-to-end trained directly from test demonstrations without requiring no pre-training or no object segmentations. It also has the advantages of the neural descriptor field in that it achieves the fusion data efficiency and the generalizability of neural descriptor fields for highly spatial 6-degree of freedom manipulation tests. So let's see the video. This is the demonstration, the test demonstration, and we only provide the object instances in upright poses. And now the model has to generalize to previously unseen object instances in unseen object pose. So as you can see, we only demonstrate the upright poses, but it has to generalize to object in lying pose. And it also has a visual distractor, and the object instance is previously unseen. And as you can see, the robot can generalize to pick and place previously unseen objects in previously unseen poses. So we'd like to introduce the 4 design principles of EDFs to achieve this data efficiency and generalizability without any prior knowledges. So it is the bioequivalence, generative modeling, steerability, and locality. Before moving on to the principles, we'd like to first define our problem. So we'll explain our problem formulation with the example of mug pick and place task. So the input is the observation of the scene and the observation of the grasp. And the model has to infer the end effector pose where the grasped object should be placed in the scene. So what we need to learn is the policy distribution that outputs the gripper pose G. We do not differentiate picking from placing tasks because picking task is essentially about placing the gripper to the scene in our case. And we use point cloud observations in practice, so the observation looks like this. And we assume that the objects are rigid bodies and they are static, and we also assume high quality observations. So the first principles of EDF is the bioequivalence. It means that our method is equivalent to how the object is grasped and also where it should be placed in the scene. So the first type of equivalence is the scene equivalence. Consider the following observation of the scene and the following gripper pose demonstration G. Now assume that the model is given with a previously unseen object pose like this, where the delta G means the transformation from the original demonstrated pose of the object. And now the model has to generalize to pick the mug by transforming the gripper according to the same transformation as the target object. So the transformation of the scene results in the same transformation as the end effector. So it looks like this in the equations. As you can see, delta G, the transformation comes to the left side of the end effector pose G, so we call it the left equivariance. Another type of equivariance is the grasp equivariance. Consider the following task demonstration. During the inference time, the robot may make mistake and the grasp may be in a slightly different pose from the demonstrated ones. This results in different observation of the grasp, but still the model has to be able to generalize to place the object in the same way as the demonstrated one. To achieve this, the robot the end effector has to be moving in the opposite direction to compensate for the changes in the transformation of the grasp. So it comes with the inverse of the transformation delta G. So the changes in the grasp result in the changes in the contravariant changes in the gripper pose. In equation, it looks like this. And as you can see, the transformation delta G's inverse comes to the right side of the equation, so we call it the right equivariance. So basically, we combine two the right equivariance condition and the left equivariance condition to obtain the biequivariance equation. As a result of biequivariance, the relative pose between the object and the placement target is invariant. Biequivariance reduces the complexity of the task by making the model to only focus on the relative pose between the grasped object and the placement target. So it is reducing the observation space. It is reducing the complexity of the task. So our model is highly data efficient and generalizable. But how do we model the biequivariant policy distribution? The first thing to consider is that equivariant manipulation policies cannot be deterministic. This is because of the symmetry of the manipulation task, which do not allow determinism. Consider the following task demonstration. Now let's rotate it by 180 degrees. Then it will look like this. The problem is that the observation is rotation symmetric. So the mug looks the same even if you rotate it by 180 degrees. So essentially, you have the same input, but two different output, which is a contradiction in case of deterministic policies. So we'd better use probabilistic policies. Another reason is that, another thing to consider is that human demonstrations are stochastic and multimodal. For example, human may pick a mug, sometimes by its rim, and sometimes by its handle. And learning this diverse behavior is important because it gives you another chance when the first option fails. So for example, picking the mug by the rim fails due to the collision, and maybe the robot can utilize another strategy of picking the mug by the handle. So it is very important to learn diverse behaviors from human. And generative modeling is required to accurately learn such stochastic and multimodal behaviors. So as you can see in the figure, generative models are better at learning those behaviors than MSE methods or minimum scared error methods or discretization methods. So EDFs use the energy-based models for the generative modeling, where E is the energy function, and we call it the Boltzmann distribution. And it allows end-to-end training with maximum log likelihood learning. And what we need for this policy to be biequivariant is the biequivariance of the energy function. So the energy should satisfy this condition. So how do we build such a biequivariant energy function? We propose using equivariant descriptor fields. So equivariant descriptor fields are essentially a SE3 equivalent neural fields with SO3 steerable descriptors as their field values. So for an input point cloud, the generated EDF looks like this. These descriptors can be steered according to the rotation R by the matrix DR, which is the representation of the SO3 group. We call it the representation. And so as you can see, if the input is rotated, then the output descriptors are steered according to the rotation matrix DR. The representation of the rotation matrix, dr. So according to the representation theory of the SO3 group, EDFs can be decomposed into the irreducible subspaces. And each irreducible subspaces has its own type or spin. And so it is a non-negative integer, and it represents the angular frequency, as Professor Tess Smidt said. So each type L or spin L subspace is independently steered by the Wigner, what's called the Wigner D matrix of degree L. So type L descriptors are 2L plus one-dimensional vectors, and type 0 descriptors are one-dimensional scalar that does not change by the rotation. So we represent it as colors because, for example, you cannot turn a red apple into green by just rotating it. So colors do not change by rotations. On the other hand, type 1 descriptors are transformed like a positional vector. So they are three-dimensional vectors, and we represent them as arrows. And there are also type 2, type 3 descriptors, which are 5-dimensional, 7-dimensional, and more descriptors. And as you get into higher descriptors, it means you have more higher angular frequency, means much more accurate angular precision. So we exploit this steerability of EDFs to exploit the EDFs to construct the bi-equivalent energy function. So let's break down this equation. First, query EDF is generated from the observation of the grasp like this. And we also draw query points from the observation of the grasp in an equivalent manner. And the query EDF assigns query descriptors to each query point. And these query points are matched with the key EDF, which is generated from the observation of the scene. So essentially, the query descriptors are transformed according to the end-effector pose, and these steered descriptors are compared with the key descriptors. If they are well aligned, it means low error, means it has low energy, which results in higher probability. So the third principle of EDF is the steerability. Using steerable descriptors is essential in achieving data-efficient and generalizable learning. Prior work like NDF or transport networks only use rotation invariant scalars, which are type 0 descriptors. So, but the problem with type 0 descriptors are that they cannot represent the orientation by themselves. So the orientation information must be spatially distributed, and this reduces the model's robustness to out-of-distribution geometries. On the other hand, rotation equivalent higher type descriptors can represent the orientations by themselves. Actually, they are very proficient at representing orientations. So this orientational sensitivity of higher type descriptors allow effective representation of orientational information of local geometries. The fourth principle of EDF is the locality. EDFs were designed to respect the locality of manipulation tasks, which is an important inductive bias. Many recent works have highlighted the importance of imposing locality for equivalent methods. Locality improves the generalizability and robustness by helping the model to learn shared local geometries. So another reason for imposing locality is that they remove the necessity of object segmentation pipelines. The problem with the bi-equivalence equation is that it is only guaranteed for the global equivalence, meaning that the target object and the whole scene should transform in the same way, the same transformation. But in practice, this does not happen. Actually, only the target object would be transformed, and the scene would remain the same. So there is an ambiguity as to whether to follow the transformation of the scene or transformation of the target object. The model has to learn to follow only the transformation of the target object. So locality bias can help the model to decide where to focus its attention on. Actually, transport networks already exploit the locality bias by using convolutional neural networks. So they can be used with no object segmentations. So we follow the same approach, and since we are a point cloud model, we use spatial convolution-based equivalent networks like tensor field networks or SE3 transformers. It is compared, we cannot use non-local networks like vector neurons because they rely on global operations, so they do not have the locality, and so they must be used with object segmentations. So here is the experimental result of our method. As you can see, our method can achieve more than 95% success rate for the 3 object instances, even if the target object is even if previously unseen instances of the target object is given with a previously unseen pose with previously unseen distracting object. And we only use 10 demonstrations from scratch, no pre-training, no prior knowledge. Still, this success rate is achievable. So ETF is still an experimental model, so it has some limitations. So the first thing is that they are very slow in training and a little bit slow in inference time. Especially, it is very slow at training. It takes 10 hours for learning, only 10 demonstrations. So this is somewhat ridiculous. And it also cannot infer the trajectory level inference. So it requires additional motion planning algorithms. And lastly, it cannot be used in the presence of severe occlusions. So future works should address this problem. Actually, we are working on the first 2 problems. So we are currently trying to put diffusion models to EDF. So it's much faster at training, and it is slightly faster in inference time, and it can also infer trajectory level inference with guided diffusion. So here is a video of our new work. I think the video is stuck. Yeah. In the way, but yeah. I think I have some technical issues now, but yeah. So this work is not yet published, but we expect to publish it soon. So please stay tuned to our new work. And thank you for the listening.
All right, thanks a lot for the great talk. We are a little bit behind schedule, so we will defer the questions for only to the poster session. So now we will have the coffee break plus poster session, and I will see you guys in 20 minutes, 30 minutes. All right, everyone. So let's start. So next we will have Professor Maani Ghaffari to give a talk. So Professor Maani Ghaffari is an assistant professor in naval architecture and marine engineering and robotics at University of Michigan in Ann Arbor. His research interest lies in the theory and applications of robotics and autonomous systems. Recently, Professor Ghaffari has published many papers in using Lie groups in control problems, and his convex geometric motion planning on Lie groups via momentum relaxation just achieved the best paper finalist at RSS 2023. Today, I'm very happy to welcome Professor Ghaffari as a speaker, and his talk is titled A Tour of Recent Symmetry Preserving Methods for Mobile Robots. So please take it away, Professor Ghaffari.
Thank you for a very kind introduction and for being here, and the previous speakers who set up the stage for me, because they did a really great job. I think the microphone, is it good now? All right, so my work is also centered around symmetry, but for the first half of the talk, I'm going to tell you about more traditional way in robotics to look at symmetry for control and estimation problems. And then I'll move to learning before you leave the room and talk about deep learning and interesting problems. And the problem that we focus on is to bridge this gap and unify over coming years these basically two areas. But the foundations of them are very similar. So first of all, robotics plays a unique role because it connects AI to the real world. That makes it very easy to pick problems that we need to work on in geometric deep learning and artificial intelligence. Otherwise, the landscape is vast and we're not going to be able to make contribution to condensed matter. So we're going to focus on a robot. Problems are physical in real world. And we want to ideally run them in real time. Efficiency is important. So geometric methods traditionally provide performance guarantee like LQR, Kalman filter for linear systems theory basically that we have, and some other optimization methods. Generally exploiting symmetry means, although not maybe on the surface, but in general means that for things that are similar, we end up calculating less, and that's good. If we do it wisely, we can save computation. For example, we can recognize the same image no matter the orientation. So for continuous symmetries of the space, if I'm wrong, please stand up and point out to the better framework, and that will open a whole new world to me. But I think the best tool we have in math to study the continuous symmetry of spaces is Lie group, action of Lie group on a homogeneous space in a smooth manifold. This is already very general, rich framework. It's more specialized than Riemannian geometry, but it's a right framework with a lot of structure to work on. For example, SE3 that came up a lot here. So this is the landscape we're going to focus. One interesting problem is robot state estimation. The problem is that the robot is moving. So I'm going to talk about mobile robots. These are not about manipulators or stationary robots. The robot is running, doing all sorts of things. We want to know where it is and how fast it's going. We need to know it in real time because this feedback is important for the controller. The controller is not going to be able to stabilize the robot if we don't have good and correct velocity feedback. Typically, we have a world frame, there's a body frame, we want to track and know where we are, and then we want to localize in the world. So this is already, we can tell that this is a rigid body transformation. We rely on sensing. There is no sensor that directly gives this basically measurement. We cannot directly measure it. So one interesting work in symmetry preserving observer is the invariant extended Kalman filter. What it's telling you is that on matrix Lie group, it's possible to exploit the symmetry of tangent spaces such that no matter in a deterministic case and when there is no noise and bias in the system, no matter what frame of reference we look at the problem, we get the same result. So it does not matter what frame of reference we look into it. The propagation and composition of these poses are exact, and the error will not change just because we change the view frame that we are viewing the problem. This is really the intuition behind it. It sounds specific, but it actually works on IMU contact and encoder data on this legged robot, for example. The tangible result is that we can lift the problem, for example, to Lie algebra. The linearization is constant for this rigid body system, independent of the state estimate. So this is the extension of Kalman filter to matrix Lie groups. For example, we can implement a version of this filter on a legged robot, a Cassie bipedal robot walking on the campus of University of Michigan. We use the output of this filter, which is tracking, it's just dead reckoning. And then we compensate the motion of a rotating LiDAR and put them for 10 seconds here in a common frame. This is not a map, it's just motion compensated point clouds. As the robot walks, although the image is very shaky, you see the point cloud is very stable. So it's not just beautiful math, it makes a difference on real robot. Now this is very, again, specialized but tangible because we can exploit symmetry and do algebra. We can discretize this, we can implement it on a digital computer on a robot. This is extremely important for the robotic system, and it works in real time. It's invariant to the building, so there will be a bunch of other buildings. Still works. Gonna go. The do all of that is very interesting. That the theoretical part of the filter was proved by Barou and Bonnabel in France. We looked into the dual problem. which is the optimal control on matrix Lie group. Generally, there's a trajectory. We have the reconstruction equation of the group that just describes the kinematic systems for evolving the rigid body, or generally any matrix Lie group element. And we have the equation of motion from geometric mechanics in the Lie algebra, tangent space of the identity. That's called Euler-Poincare equation. The beauty of the Euler-Poincare equation is that it describes the evolution of time evolution of the twist in the body frame, only the tangents to the identity, without integrating the actual pose on the group. It decouples them into two set of systems and equation. If we need pose, we can integrate, but it turns out that not necessarily we need to do that. On top of that, one thing that we did is that the previous work, they were looking into this basically candidate for Lyapunov function. They were defining it in the group, and it was always radially bounded. You cannot prove exponential stability if the basically proposal function is radially bounded. We moved to the Lie algebra, then we get exponentially unbounded Lyapunov function, and again, using a symmetry of tangent spaces, we can prove, I'm not going to details, happy to talk with you offline. We can prove that for any system, kinematic system, evolving on matrix Lie group, we can get global convergence for a tracking controller. Unconstrained problem. If it's constrained, we have to estimate the basin of attraction. This is a dual of that invariant here, because again, linearization will be constant. We can show that the error will converge to zero, or the identity, tracking error. And when we lift the problem to the tangent space and linearize, we still linearize the dynamics, the Euler-Poincare equations, but for the kinematic systems, you can prove nice results that it's convergent. Again, what's the tangible result? On the robot, we run MPC, we don't run LQR, because we have constraints for actuations, for safety, for friction, and all of that. It's a constraint optimization problem. And we do it in a receding horizon manner, so that's why you see a lot of MPC on the robot. This will give us a convex MPC for a rigid body system and a robotic platform. We can grab an off-the-shelf QP solver and we can run it in real time. And it works, if not better, as good as nonlinear MPCs we see. If you solve the exact problem, probably you can improve, but that's not going to be real time, right? This is a great advantage that we can do QP on the robot. Plus, it handles rotation and translation simultaneously. We do not decouple this space into translation and rotation. We get the top row, we get exponential convergence for both of them to a particular configurations that we want to move. Again, the stability is for kinematic system. We can have a linear feedback style system in the Lie algebra that will stabilize the system into drive the error to the identity using just a standard Lyapunov function. The opportunity is that there's room to do control barrier function in the Lie algebra. We talk about a set as equilibrium dynamically changes as opposed to a point. So getting closer to the topic of this workshop. So those are more geometric, purely geometric traditional work in robotics that exploit symmetry. I'm going to talk about kernel method. Hopefully you won't leave, only a few slides. Then I'm going to switch to deep learning. So I spent a lot of time in my PhD working on kernel methods. Then I came from Australia to the US. Then I realized nobody uses kernel methods. But Australia was too far. It took me a long time to realize that deep learning was the right tool. So you can think about it like this. We have a Hilbert space of functions, and we can do a kernel density estimation of any function if you have data points. Basically, if you pick a positive definite kernel and you make them your data points, and then you can do a kernel density estimation, and you can construct a data-driven, basically non-parametric representation of your data as a function. But the problem is that in perception, I have points, I have color, I have semantic labels, and a bunch of other things that I might have. I want to have a unified model. I don't want to regularize and define different model for different works. So what we did that we generalized the labels, the coefficients of this kernel density estimation into a tensor product space, which this can be exactly a layer of neural network. When you learn your features, you have a tensor field, and you learn all these features. If they're invariant, They're perfect labels because they don't change with the point. And then you have a geometric part that is equivariant. For example, this kernel is equivariant if we have SE3 transformation. So we get equivariant function based on the kernel methods that models color in the point cloud or camera, semantic labels coming out of a neural network, and depth. So what happens is that when we do point cloud registration, instead of thinking about points and thinking about how I match these points to regress my pose and track, we think about aligning the functions. And this is precisely maximizing the cross correlation or convolution between two functions. So you can see that it's really converging into as if it's a layer of a neural network. That's not done exactly from this point of view, and we know that, but it's possible to do it. And this gives you a superior performance if you tune the hyperparameters right, because it's a kernel method, because it's agnostic to the density of the point cloud, the sparsity, noise. Virtually, the input noise has no effect on the output because it's in the function space. It's extremely robust to outliers. You get nice results by just frame-to-frame accumulation and highway, which is a very high-speed scenario. All right, then it took us a few years when finally we moved to deep learning framework. So 3D perception or scene understanding, that's the central problem in robotics. With all the geometric problem in control and planning, still the perception is the challenge because the robot will act up to its perception in the environment. Object manipulation, indoor navigation, autonomous driving. So these are central problem, but the challenges are safety and resource sensitivity of these platforms. You cannot just use any algorithm for these methods. And that motivates predictable behavior, as Tess mentioned in her talk, that we want the input-output to be predictable. Otherwise, we're not going to be able to analyze the error. So no matter how big is the network, if we have this symmetry and equivariance, we can have a predictable behavior. And efficiency is also important. For example, we have, under various environmental changes, you have all these, change of views in the data set. So large deep learning models are very good at handling, adding prior information, different entities, different observations, and this is great. We like to keep it that way. We don't want to go back to, the previous era. But at the same time, can we just learn once for different observation? And the answer is symmetry. So if we bake in the symmetry using geometry into the network, while it's still keeping it big, and we can handle some of the, not necessarily geometric part, like the emergent, capability that Hao mentioned, and that's very important. I think the mix of these two will potentially be what we need as a minimal setup on a robot. Not everything, but as a minimum setting. So equivariance, you are expert by now based on the previous talks. The function basically commutes this a transformation, right? If it's invariant, you can basically extract the features, no matter what's the transformation. And if it's equivariant, if you extract edges, for example, it moves with the shift in the image. And the convolution, for example, is translation equivariant. In this case, you see the rotation SO2 equivariance, where the features are rotating as the image is rotating. If it's invariant, it will stay the same. So this is a very predictable way of analyzing the output. So that's good. That's what we want. This is easy, but as it gets complicated and goes to higher dimensions, we can only analyze it mathematically. So we want to preserve this structure. One particular problem we looked into is point cloud registration. So PointNet came up earlier. That's one way to learn representation, and it's great. There are challenges of sparsity and noise that makes it difficult to solve the problem in practice. Vector neuron was a version of PointNet that was equivariant. That was a very interesting work. So we can have a SO3 equivariant encoder that takes the input point cloud in the level of object, not as big as the scene. You can rotate it. We get a set of features that are rotated the same as the input. Now, you might not read this in the literature, but what these features are really are, these are left invariant vector fields, right? These are vectors that are in the Lie algebra of SO3, and it works for SO3. In fact, it works for any matrix Lie group that has an adjoint invariant inner product. It does not work for SE3 theoretically because it doesn't have that property. So this is like a special version of vector neuron is a special version of convolution. So it's a sort of differential version of that in the Lie algebra. It works for semi-simple Lie algebras. So 3 is a common example of that we see in the literature. So we thought that once we have these equivariant features, we work a lot on registration. The obvious idea for us is to, well, grab these features and try to recover the transformation by registering these features. Instead of aligning the points in the input space, let's solve the registration in the feature space. Because of this permutation invariant property of the point net, if it's the same object and we rotate it, the features are in one-to-one correspondence already. So that makes the feature space correspondence free. And interestingly, now the problem can be mapped to the original Horn's problem solution to point cloud registration. You have two set of points, features, vectors, one-to-one correspondences, find the relative, say, rotation and translation. So we solved Horn's method in feature space. This was a core paper. It sounds obvious, but it wasn't done. I think there are a lot of opportunities like this that there are obvious things that you just need to look at it carefully. It sounds trivial, and people get upset when you do this type of work because they feel they missed out. It's too simple. But I think this is the level of work that makes a difference on the robot. Moving on. It works without initialization, right? So we can do global registration. Partial overlap is extremely challenging. So there are still a lot of challenges to address. But it doesn't handle translation. The point clouds, they must be centralized. It's typical in the literature to call translation invariant to be equivariant. But the fact is, for regression problem, that's not good enough. It must be equivariant. If it's invariant, the translation information is lost. So group convolution is a general solution to this problem. If we run the convolution on the group, we can solve the problem. But that will blow up the size of the integral to be extremely large. Plus, exact integration is usually not possible. Sampling, it makes it extremely inefficient. So one good solution for that is to look into quotient spaces. We can show that theoretically there's an equivalent convolution, which is exactly capturing that group convolution in the quotient space. Here, G divided by H. H is a quotient space. So the kernel of convolution will be in the quotient space. So we work in a lower dimensional space. For example, instead of SE3 being as a set, SO3 times R3, we can grab the quotient space of SO3 divided by SO2. That will give us the sphere, 2 sphere. Then we work with a 2 sphere times R3, 5-dimensional space instead of 6-dimensional space. So that might not look much, but that makes a huge difference computationally. So basically, the roll about the same axis is lost at this point, right? We're not going to be able to recover rotation about the same axis once we move to the, and you have this commutative diagram that you can go to the quotient space and then discretize, or you can discretize and then go to the quotient space. So the discretization here is very important. There are many discretizations for the sphere, but the symmetric one that is the finest one is this polyhedron that you see with these symmetric vertices. Because we can also save computation by designing symmetric kernels that share weights for symmetric vertices on this polyhedron. So what do we gain here? So we discretize the convolution, right? If you want to do a summation, for every translation, we have to do 60 rotations, right? When we go to the quotient space, for every translation, now we have to do 12 rotations. Now you have a huge network and you want to train it, it makes a big difference in memory and runtime. What about recovering the rotation? it turns out that you can recover the rotation because if you paint these vertices with different unique colors, the permutation of this 12th possible rotation is unique. So by looking at it, we can supervise a layer based on the permutation and just recover the whole 3D rotation. So that's not a problem. So this is the message here. We go to the Gaussian space, we gain efficiency, and then we look at the permutation. If it's carefully designed and symmetric and we can have unique permutations, then we can recover the full transformation. It's very promising. Up to the discretization, this is for coarse, obviously, representation. But it's good enough that makes 5 times more memory efficient in inference and runtime. And this is, at this point, based on previous experiment of running real-time neural networks on Jetstone and the robot, I think this network has the potential to become real-time after optimization, not before that. So this is a SE3 equivariance. We handle rotation and translation. Of course, it's only for point cloud. It's nice to have it for images as well. Now we grab this. Now we have SE3 equivariant encoder. The sky is the limit. Let's do place recognition. Grab the point clouds, look at it from different angles, learn the SE3 equivariant descriptors, aggregate them to aggregate locally SE3 invariant descriptors, build a global descriptor. And then we can do place recognition. There's always equivariance, and then we can get invariant after that, right? You don't want to have invariant first. I think this came up in Hao's talk as well, because then the information is lost. In the end, we get an invariant layer. Now, for the same point cloud, no matter how it rotates and translates, you get 100% accuracy. No mistake by the network. Very boring, right? Nobody wants to see this. Then they'll ask you, what's left then? Yeah, people hate you if you solve a problem. To leave something for other people. Okay, we didn't solve the problem. Same point cloud, right? So robot moves is never the same point cloud or overlap. And if you move very fast, it makes it hard because the overlap might be small, less than 30%. It's extremely difficult. But it's still very promising that the state of the art of that year, Minlock 3D from CVPR, and Kitty data set, there is a sequence A, the car is coming from the opposite view of the road. It breaks down completely. You get 3% for top one classification accuracy. This is unacceptable, obviously, for changing the side of the road and then having a breakdown on the autonomous system. Without training, these are without training. If you train, data augmentation can solve this problem, but we can't augment data from the whole world, right? We need a structure. You still get 60% accuracy. The drop is really significant compared to what we lost in the state of the art. So these are signs that we should invest and spend more resources to develop these algorithms into something more realistic for robotics. These are more or less proof of concept results on data sets. So my message is that I think we're lucky to have the robot. That's good. That will constrain our problems in the real world. And we're lucky to have geometric learning and scientists. They do the hard part of giving us some of the algorithms, but we really need to translate and bridge the gap. They're not directly applicable a lot of times. And usually generalization and efficiency in terms of robotics in mind, they're not their primary concern when they develop the algorithms. We need efficient generalizable algorithms, and symmetry is one of the dimensions that we need to maintain. Sparsity is another one, historically in Islam. But also we can't ignore this large scale computational model. So what I'd like to look into in coming years is that connecting this last part of the talk to those initial works. I think we can do all the filtering, all the optimal control, all the optimization in those representation spaces that are predictable. It's very clear that it's possible. It's just a matter of how to do it and having mature frameworks to look into it. Basically, you can bring in probabilistic robotics into the representation space. That would be the ideal. Okay, so this is the last slide. Did I use more time or? Thank you. One great question.
Sorry, I didn't do a very good job planning my route, so maybe you guys could help me with that.
We lost half the time.
Sorry. So thank you for the talk. I had a question about the part on group convolution. So I can certainly understand the motivation for if you're doing a group convolution, you're discretizing your operations, why you would prefer to go with the quotient space. So that makes sense to me. I think I missed the motivation for using group convolution, so using filters that are like a filter bank that's rotated versus using a Fourier basis like spherical harmonics, where you don't do the discretization. Is there a specific reason why the group convolution picture is favorable over steerable filters?
Now that's a great question, because if we're looking at the sphere, anybody, expert in physics, they can tell you that just use the spherical harmonics, right? I think that's possible, and I don't know if it'll make a difference. You probably know better if it makes it better. But the motivation behind it, why we looked into convolution, because we are interested in other Lie groups, and this is just one example. If we just focus and specialize it to spherical harmonics, I think that will be too narrow for generalizing it to other Lie groups.
Okay.
It might not end up being a sphere. For example, one group that I'm interested to look into is a special linear system. Now, we might end up having the sphere. You could be right.
Yeah, I think you have different basis functions for that one, but you'd have, I think.
But
you'd
a
have
question for
something.
you might know. Does it matter? Mathematically, aren't they equivalent? So it's
the two different groups, or
if we use the spherical harmonics.
Or spherical harmonics
basis.
versus So I think group convolution in the limit of infinite filters would be equivalent to using spherical harmonics, but it's kind of the difference between working in real space versus working in Fourier space. That's my understanding. But obviously, I think also, but when it comes down to the practicality of it, of which one's easier to optimize with gradients, that's a whole nother can of worms, but yeah.
For anyone in the room, if someone smart shows up asking questions, ask them a question.
No, but thanks for answering my question.
That's a very valid point. I don't have a good answer, but I think we're interested in a general group-based convolution, and maybe we thought this is, maybe it's more general, maybe it's not. Maybe we always have that module of a spherical harmonics.
No, I think generalizing it is not obvious as in the Fourier basis, but it might be doable. So it'd be fun to chat more about it later. Thank you.
Thank you.
Do you have Professor Robert Platt online moderating this session? So Rob, can you? Yeah.
Hello. Yes, okay, there they are. Okay, hold on. Wow, you guys look really good with that screen behind you. You guys look. Yeah. Yeah, I guess I don't. So I mean, I guess I didn't think a whole lot in advance about how I was going to moderate this thing. But I guess the obvious thing that pops into my mind is to ask Tess. So obviously, I mean, it's so first of all, it seems clear that there's a tiny bit of a disconnect between where where kind of the symmetric geometric deep learning community is, and robotics thinking. So I guess maybe I could ask Tess about where in robotics we see the greatest potential for low-hanging fruit.
Okay, I'm not sure I'm going to be able to answer this, since I think whatever the lowest hanging fruit for robotics. So to me, the robotics is very complicated. Everything you guys do is amazing. I mean, the fact that you're able to make robots actually do reasonable things and have control guarantees about it is just amazing to me. So I don't know if I have much to say about it. I think, things that I've seen maybe that are adjacent to robotics, like I've seen, the recent work with vector neurons, and I think there is a lot of low-hanging fruit as far as, we have the general mathematics for equivariant models, but vector neurons is actually relatively simple in interactions, but it's surprisingly effective for 3D data. And I think it's a fantastic model. It's basically just using scalar interactions and dot products and things, but it has very good efficiency. I think it's not the full story. So I think starting off with even just some of these equivariant methods that do at least use things like dot products and things like that are a good place to start. And then adding on the additional mathematical complexity of other interactions kind of as you go. And then again, this notion of kind of experimenting with seeing what interactions help your use case and what computational efficiency you're willing to tolerate in your use case. I think is a good place to start. So just know that the tensor products are there, but you don't necessarily have to start off with them. I'm not sure if that's a satisfying answer, but it's what I got. Okay.
I'm gonna side with Tess. I can give you a reason because I can teach probably vector neuron in my classes. I don't think I can ever teach tensor field networks in my classes. I'm not going to put all the blames on the students. It's also me figuring out how to teach it and knowing that field. But it's possible to probably add it to the curriculum, but then maybe some people are interested, they can do research and learn more advanced topics. So I think in that sense, there's a lot of value into that, its simplicity. And the opportunity here, I think it's general. In my talk, I mentioned we can generalize it to semi-simple Lie algebras, that the inner product will be adjoint invariant, right? The problem I faced is that, so I've had that for several years. So it was not published because the problem is how we need an equivariant lift of the data to the Lie algebra of that semi-simple group. And that's not always easy. For 2D point clouds, it's easy. You do nearest neighbor cross product. Features are in the Lie algebra. Basically, you have the Lie bracket to generate all the generators, right? If you generalize what they do in the paper, that's what it is. But that doesn't necessarily work, for example, on images or other data. So that doesn't look sexy, so tell somebody to come and work on this initialization layer of neural network. It sounds like a data science job. But it needs to be an equivariant lift. And I think that's extremely important. And in Rob Mahoney's work, when he generalized this invariant filter to equivariant framework, he has a formal definition and proof for an equivariant lift, but that's only for filters, right? When I saw that, then I could draw an analogy that maybe we can have a data-driven equivariant lift. If we want to work with representation, we don't have to analytically design it. So from vector neuron and in its defense, I think we can go as far as I saw.
Maybe a follow-up comment. Yeah, so I think the types of models that do these kind of lifting operations into the Lie group, to be honest, I think I don't fully understand those methods because there are many, we were talking about this at the coffee break, there's many different ways to look at representation theory and how it relates to your system. And so the lift operations into the Lie group is one way of viewing the representation theory. And then perhaps coming from a physics background, I think a lot about the vector space that my objects live in. And so I'm kind of stuck in this vector space picture of like, what are my different vector spaces and how do they transform? And there's probably a beautiful way to relate the two, but I don't know. And hopefully we'll figure that out through more coffee breaks. So that's kind of, different ways of thinking about it. But I would say even when people say equivariance, it can mean many different things to different people. And for me, I'm usually thinking about these irreducible representations, and I don't actually think about the elements of the symmetry itself. I'm always just thinking about these vector spaces.
Okay. Well, I was going to ask how I was going to ask So from your talk, I remember you did a number of experiments about reference frames and their effect on learning. So right, I mean, there it strikes me that like there's, I don't know, how do you think there's opportunities there to use some model like some symmetric model like this?
Okay. Okay. It's actually a bit tricky to answer that question. But actually, I've been thinking about the symmetry equivariant problem for quite a while, like after we reinvent the point net. And then we have been thinking about those kind of idea of symmetry or equivariance. How could it be beneficial to like reinforce learning setup? It's a bit unfortunate that so far I haven't found like any existing approaches that really fit the framework. For example, vector neuron, we also tried it in reinforcement learning as policy value. No, it doesn't work actually. That's a tricky part. Yeah. So it's like, in fact, the signal that you are predicting is very important when you are considering whether it needs to be equivariant or invariant. And like think about the human's ability. I mean, when we're able to recognize faces, but you put the face upside down, we can't recognize it, which means like humans are not really invariant. Yeah. So like the natural evolution comes to a solution that's not really equivariant or invariant. That makes me feel very puzzled and think about like perhaps, I mean, like this is a very important topic of symmetry, but there are actually some of the tricky aspects. Yeah, so when I think about it, I mean, perhaps there are some simpler ways, not as fundamental as we have been discussing by the mathematical theory, but more approaching to the engineering level. And then we've been thinking about what are the possibilities, and somehow changing the coordinate frame is a kind of very obvious way to achieve the symmetry. Yeah, I would say it's not that beautiful, but actually one obvious way. So, but actually I'm still pretty interested in whether there are more fundamental and theoretically solid ways, to really inject this kind of symmetry. I mean, in the last part of my talk, when I was answering questions, I talked about like emergence concepts, right? Nowadays, when people are talking about the kind of AGI, right, whether it's a language model setup or it's in reinforcement learning setup, people talk about the emergence concepts. For perception, for understanding the world, we need those kind of emergence ability. But then how would the symmetry be plugged here? That's a question that's been puzzling me quite a lot.
Yeah. One thing that so we've been looking for applications of symmetry and in our group, and one thing that strikes me is that it's not super helpful in a lot of computer vision tasks because we already have an enormous pile of computer vision data, and maybe there's not a lot of benefit to biasing the model further. So I guess I view the symmetric models as adding bias to the model, and if there's already a giant pile of data, maybe it's not super helpful, and maybe it's not super helpful for language models, but it does strike me that it's helpful for robotics because of the data poor. I mean, I don't know. It depends depends who you are. Like maybe if you're Amazon, it's not helpful because you have a lot of data. You don't need it. It's helpful anytime you need. You want to bias your model in order to improve efficiency.
Yeah, and also I want to point a little bit about like the data augmentation approaches. Like usually when people compare with those equivariant methods, they'll compare with the baseline model without data augmentation. But usually with data augmentation, it can be very strong. So that is also a question. Like for symmetry learning community, how do you view this kind of data augmented? I mean, like one is like, reinforcing like the fast learnability is important. There's no time for you to do the data augmentation. And data augmentation is using some of the capacity of the model, but the symmetry ones, they are intrinsically, there might be some kind of advantage representation power.
Yeah, so this is not an application in robotics, but at least from, so I work a lot in atomistic modeling. So basically trying to predict complex quantum mechanical properties of atomic systems. And we find that, so of course we get the the benefits of not having to do data augmentation. But even if you compare against data augmentation, the equivariant models are just, they are more accurate in our settings. It's very hard to augment. Part of this is because properties of atomistic systems change a lot when you start distorting things. It's very sensitive. And it's also kind of intractable to show, because, if we talk about configuration spaces, we have, you have n atoms, and n could be anywhere from 5 to 100 million. So it can be a large configuration space. And so we find that the equivariance allows the models to generalize a lot better. So if you look at even invariant versus equivariant or symmetry, or even for models that are not symmetry preserving, the equivariant model tends to behave better when we actually start using it to do molecular dynamics. The molecules are less likely to explode when they're not supposed to. Now, it'd be great if I had like a better way of quantifying that to convey that, but I think it's still kind of early days, because we're finally getting to the point where we can start playing with these models and really putting them to the test. But this is something that we're noticing, is that they tend to generalize better and they're more robust, and that they just seem to have more of the properties that we want. So whether that's going to play out in other settings, I think is to be determined. I always leave it up to, we suspect, but we cannot prove until we see it in an actual model. So I do suspect that there's some advantages. Another comment, though, this is kind of more of a fun fact about coordinate systems. So yeah, coordinate systems are so interesting because they specifically break all symmetries. Like, they're literally designed to break all symmetries, and so it's really fascinating. And even myself, I am very not equivariant because I always orient myself to north. I can't do left and right, which you think that's actually more equivariant, but but I always align to north. And coordinate systems are exceedingly helpful because they remove all ambiguities and they make things more computationally efficient. Like, most algorithms that we use break symmetry. There are very few algorithms that preserve symmetry, and I suspect that there's actually probably a lovely information theory way of approaching this as to why that is. But yeah, symmetry in algorithms is actually like very much against how we typically teach computer science, and it's super fascinating. Side note.
So yeah, and then how, with regard to your question, so we did a bunch of work with 2D steerable convolutions, like with reinforcement learning, with other stuff, and I guess I generally think about 3 different approaches to symmetry. There's the canonicalization approach, which is what you were talking about, where you put everything in particular reference frames. There's a data augmentation approach, and then there's the symmetric model approach. In our, so we do data augmentation with everything. In our work, the symmetric models always outperform, but in a very significant way. Now that's with 2D steerable convolutions, and it's maybe not the same for vector neurons. I don't know, but I do know that in the 2D setting, it seemed clear.
Okay, that's actually great to hear. I think like the results that I have, if you have a positive result, I think that's true. Even negative result, it's possible that the experiment is not fully correct.
Rob, I can share some less sophisticated thought in the level of intuition that, well, I thought about it that if I'm going to make this my career and campaign, symmetry and stuff like that, to get tenure, I need to be convinced that's the life I'm going to live. Because from physics, you see SE3, the symmetry group of the space, but that's not everything for the perception and what we see. The hierarchy comes to mind when the equivariance is information on the course level, because it's always tasks that are suffering from this course level prior data augmentation. They gain huge benefits. Suddenly, we get several order of magnitude improvement sometimes. So on the course level, I think equivariance is information. But as we zoom in, fine registration was an example of it. That might not be necessary, because if you have good initialization, probably we don't need equivariance. That's again, local solver, global solver perspective in optimization. So that hierarchy, which ironically you do have hierarchical reinforcement learning, that might play a role. I don't know, but I thought that I'm going to focus on the course level. If it comes to that, I have to defend myself.
Okay, actually, it relates to a bit of this. Sorry to interrupt. Relates to a bit of discussion related about like spherical harmonics, right? I guess it's like a Fourier basis and the learned basis. This kind of a question has been quite a while in like the dictionary learning for like image compression, right? That kind of stuff, like convolution. But somehow it seems like the learned filters, they are the basis, and they would be able to focus on a particular frequency, right? Whereas for spherical harmonics, like they are manually designed, right? They have the perfect orthogonality, very good properties, but on the other hand, it loses the ability to focus on certain spectrum. Yes, exactly as what you said. Sometimes maybe like you're learning kind of a symmetry, focusing on a particular spectrum, whereas for the rest of the part, you don't need the symmetry. You don't need to care about that, right? You need to break the symmetry, or I don't know, some kind of way. Yeah.
It's sort of again, another perspective is mixed integer program, right? So if we know the region, we can again solve the problem globally. The hard part is the combinatorial part when we have to to solve which region. Yes. So the equivariance can bootstrap again some insights from the registration problem. I don't know how far this will generalize, but it seems to be a repeating pattern, like you said again. Different.
So but before we wrap up, I wanted to get Hyunwoo's perspective on so your thoughts on like where.
Sorry.
Yeah, I mean on whatever, but I mean on where you think like the biggest opportunity is in robotics.
Yeah, I think we should also consider using spherical harmonics or some continuous symmetries because sometimes I found that discretization methods are not accurate enough to do very precise manipulations. So we can maybe try the spherical harmonics or any other continuous symmetry methods to obtain the precision in manipulation. So we may combine those methods. So as said before, we can use the discrete symmetries for the coarse level, and we can use some continuous methods for the fine tuning. So I think we should combine those methods. So.
All right. Well, it sounds like you should talk to Tess later then. It's lunchtime, right? Not for me.
Yeah, it's about lunchtime. So that concludes our morning sessions. I want to thank the speakers again for the very great discussion. All right, everyone, welcome back. Let's start our afternoon sessions. So we will have Dr. Andy Zeng to give a talk first. So Dr. Andy Zeng is a research scientist at Google DeepMind, and his research interest lies in robot learning. So Andy is my role model in research. I started following Andy's work when I was still a master's student, and a lot of my own work is actually inspired by your work. So Andy's work, Andy is also one of the pioneers who used symmetries in robot learning. So for example, his method of predicting manipulation affordances using fully convolutional network make use of the translational symmetry of the network, and also makes use of the rotational symmetry by rotating the observations. So recently, Andy has focused on using language models in robotics. And today, it is my great pleasure to invite Andy to give a talk titled From Patterns Among Word to Actions. So Andy, please.
Thank you so much for the introduction. Yeah, so today I'm going to talk about patterns among words to actions. I think the title will become a little bit clearer as we progress through the talk. But yeah, excited to share some interesting thoughts when I think about the future, I'm most excited for one where robots are around us and operating in human-centered spaces, helping us with everyday tasks. And part of this vision, I think, is building robots that can move around and manipulate various objects in the world. And this is a pretty challenging problem. I and my team and I, we work a lot on manipulation, getting robots to pick stuff up, put them down, push them around, and do all of this with machine learning. And part of the story here is that when we do have these deep learning algorithms, traditionally they're very data hungry, but we do know that symmetries exist very much so inside the physical world that we live in. And the question is, for many of the problems that we're tackling in manipulation, can we leverage these symmetries? So TossingBot was kind of looking at the observation that when you're throwing objects, the way in which they fly through the air may change depending on the geometry and the physics. But in general, they all share this baseline of ballistic equations of projectile motion. And so you can kind of bring that redundancy down just by including that inside of your model architecture. With transporter nets, you're doing a forward in space type reasoning for pick and place tasks. And part of this is incorporating a shape prior. So as you're picking up objects, you're taking a crop around them and then shifting this crop around. So almost doing like a sliding window type approach to keep some of the shape priors that exist. And then in PalmSayCan, this is using large language models to instruct robots on what to do. And part of this is trying to deal with the fact that there's a lot of multimodality or redundancies in language. There are multiple different ways to say the same thing. And how can you use language models to kind of help you funnel that into a very consistent plan? Types of things that we've been looking at recently. I think that for many of us, especially for symmetries and robot learning, I think what we are looking for, at least a portion of us, is data efficiency, so that our models, with whatever limited capacity that they have, can focus on generalizing the more important stuff. And I think that this is generally an important thing, particularly in developing, more and more complex algorithms. For example, if you had a geocentric model of the solar system, you would often get something that looks quite complex. But then in the transition into a heliocentric model where the planets in the solar system rotate around the sun, you just have so much more simplicity that is baked into this model. And it is after this transition that much more of the sort of breakthroughs in this area started to come after this a transition into a simpler model. So just like how the simplification of a representation could enable the capacity to focus on the more important stuff, I think our models could benefit from symmetries as well. So I think that there are various different ways to imbue data efficiency. There's data augmentation, symmetries in the architecture. You've heard from other folks on how we can be doing this. But I think one specific thing that I wanted to share with you all today is potentially a third way to capture some data efficiency in our systems. And today I'm going to talk about in-context pattern completion with large language models. Very excited to talk about this. This is also involving a work that we haven't released yet in the public, but it's coming out on arXiv later this week. So we're really excited to share with you all some early results here on this front. Some background: over the past year, we've been very excited about using large language models in different spots of reasoning. So this includes robot planning, visual common sense, and robot programming. This has led to a body of work, including PalmSayCan Socratic models, inner monologue, and CODIS policies. And one thing that we realized in doing these projects was realizing that language models, they also store and compress linguistic knowledge into reusable patterns. In particular, the number of tokens that you're passing into these models far surpass the number of parameters that they contain. And so they must be doing some version of compression. And I think that these reusable patterns that are contained in there may actually include some symmetries that we can use for some of the problems that we're tackling in manipulation. I wanted to give some background. So what is Socratic models in SayCan? This is one way in which you can use the foundation models, the visual language models and large language models today for various reasoning tasks, and in particular under the premise of language as robot middleware. So specifically, a pipeline might be if you have a tabletop surface and you're trying to pick and place various objects on this tabletop, you might take a visual language model or an object detector and detect the objects in the scene. Then you can construct a linguistic description of what's inside the scene. And then also take a human input, which is your task description, move all the blocks to different corners. and then ask a large language model to do the planning. So it'll give you a step-by-step plan. A little bit of context for how this works. If you just go into your off-the-shelf large language model and ask things like steps for a mobile robot to fetch a Coke can from the refrigerator in the kitchen, the language model will generate a semblance of a reasonable plan. Step 1, locate the refrigerator in the kitchen, use sensors to detect the presence of the Coke can, move the robot towards the refrigerator, etc. So this is a pretty good plan, and really the only thing left to do is to ground each of these steps to actual sensors or actual actions that the robot can take. And that's essentially what this pipeline is going for, which is once we have each of these steps in a plan, we can pass them to language condition policies. In this particular case, we're passing them to Clipport, which is a language condition pick and place model. So that's in the context of Socratic models and PaLM-seq, and you can also extend this language model for planning into the full expression of code. So specifically, these language models, they are often also pre-trained on GitHub data. And what that allows you to do is that you can phrase some of your language in and actions out type problems into a format that these models can ingest. So for example, if we have some particular instruction, if you see an orange, move backwards. And then we're going to give it an example of robot APIs that it can use. So if detect object orange, robot.set velocity, x equals negative 0.1, y equals to 0, and z equals to 0. And we can give it a new instruction that it hasn't seen before. Move left until you see the apple. And it will generate some code that follows the similar structure in which you've provided as input. And there's a lot of subtle small things going on here. One is that it's swapping, for example, orange to an apple according to instruction. You're also changing the if statement to a while statement. So that's an interesting logic structure change. And also it's assigning a canonical coordinate frame. So instead of moving backwards, you're now moving to the left, and this follows some particular right-hand coordinate. And then we can also say, do it again, but faster to the left or to the right and with a banana. And it will generate a following plan following the similar structure, but then flipping the y velocity to the non-negative, and then increasing the values too. So a little bit semblance of this low-level common sense in trying to pick up the speed. And then, of course, you can say, tell me why you stopped moving. And it will give you a print statement. I stopped moving because I detected a banana. Great. So code as policies is essentially taking this to robots and using these code writing language models to compose existing perception and control APIs. Detect objects could be using some visual language model or an object detector. Control APIs can be a collection of primitives that you defined, like set velocity. And then you can have it do a variety of interesting, at least in this case, various pick and place tasks. If these language models have encountered functions that they haven't seen before, which is highlighted in red, you can ask the language model to yet again define what those functions mean. And so you have this recursively defining undefined functions type system that sort of grows its own code base over time until it can run on a robot. This harkens back to some classic work in robot programming. And so you have this general idea of infinite use of finite means and leveraging the compositional generality of these large language models. So this project was led by Jackie, who's full-time with us now. So part of what powers the ability of language models to write robot code is in part because on GitHub, when you've trained these models, on GitHub, it contains, so some background is that when we write code, we oftentimes write it in the style of chain of thought. We would write a comment and then follow that with potentially some code, and the comment would describe what that code is. And so this is kind of just scaffolding the language to actions type framework into the similar data distribution that you would find, which is why we format it in the style of comments to code. Also, this is powered by in-context learning, which is supervised meta learning. And the way that you can think of how this works is that you have multiple examples of input-output, and you're packing them together sequentially all in the same context buffer that you pass to an autoregressive model to do inference on. So in NLP, this is usually done for example, translation tasks where you have maison, house, chat, cat, chien to dog. This is from French to English. And you have a prompt, and these are X and F of X examples. And ultimately, you want to predict for a new X of query, predict F of X query. And this function is kept consistent across the in-context examples. The F here is being drawn from the same distribution of functions F. And the idea is that if you train this model to be able to learn across multiple functions that are pulled from the same distribution of F, then you have a chance of being capable of generalizing to unseen F or new tasks. So there's this interesting figure where this is a paper from from Kirsch et al. Discussing general purpose in context learning by meta-learning transformers. And they show that if you have an MLP that is trained to be able to learn across different tasks pulled from the same distribution, the amount of generalization is fairly linear. Whereas when you take a transformers at certain scale, they start to generalize to an unbounded number of function Fs. And also at the same time, these seem to apply for non-recurrent autoregressive sequence models. So RNNs and LSTMs are not quite as capable of being able to do in-context learning as much as transformers. Okay, so language models, they can write code, and the fun examples that Jackie has put together here include a variety of different examples of robots doing tasks based on language conditioning, and it's writing things like NumPy and SciPy code to be able to do some spatial reasoning. So one example is like arrange the blocks in a square around the middle, make the square bigger, now move the red block 5 centimeters to the bottom, and it'll write the robot code so that you can do the pick and place. Okay, so that was largely about projects in which we were focusing. So POMC, Socratic models, intermodal Lakota's policies, those are projects that focus mostly on extracting the linguistic patterns that exist in these language models. But I think that there may be more in which we can extract from them. And specifically, I think that today I'd like to talk a little bit about how we can extract non-linguistic patterns from these models, and where they could potentially serve as general pattern machines. So this is work led by Suvir and others, who is a PhD student with Dorsa right now and was also a student researcher with us. And the work is called Large Language Models as General Pattern Machines. The paper will come out later this week, but you can already download the code at Google Research/General Pattern Machines. Some general trends of large language models and robots. We're kind of increasingly, with every single project, building on top of each other and making things more closed loop, moving closer to control, including higher rate actions, more symbolic and less linguistic. So you can think of code as being a little bit more of a symbolic representation of language, and then ultimately more in-context learning. And I think that if we go even further, one potential hypothesis is that we can even try to do some more in-context learning on the level of symbols. And so this was the hypothesis that we had coming into this project. One observation that we had is that language models are surprisingly good at the abstract reasoning corpus. This is a benchmark created by Francois Chollet et al. In 2019. And you can think of this as an IQ test where you have a grid and you're trying to complete the pattern where you have an input grid and an output grid. And given several examples of input-output patterns, given a new input, you want to predict the output grid. So here it's taking these colored patterns and then like spreading them out to the corners. This one's also being spread out to the corners. And here, given this input, you want to spread it out to the corners and predict what the output would be. What makes this benchmark hard is that there's a level of human priors that are needed to solve some of these tasks. So for example, this one here is like an example of a particle bouncing off of a wall, and given this new input, you want to predict how it's going to bounce off the wall. And what's interesting is that if you prompt the language model just in the style of ASCII letters or ASCII numbers, you end up getting state-of-the-art performance on this benchmark. So previously, it's a pretty hard benchmark in the sense that the only ways in which people have come up with how to do it is to manually engineer domain-specific languages and piece them together to be able to do various grid operations in sequence. But it turns out that large language models just right out of the box can do this task quite well, just given the input and output examples in context. So out of the 800 problems, Codex hits 87, Text-DaVinci hits 85. So it's pretty much state of the art. So here's just to give an example, if we copy this into the language model, you can expect the ASCII representation here, 2 maps to a particular color, 3 maps to another color, and the output prediction is going to spread apart the numbers into the corners respectively. So what's interesting about this too is that some of these patterns that live inside of the abstract reasoning corpus, they can get pretty complex. Like for example here, this training and testing example, the training here, the input outputs, I think look at this one here where it has 2 upright T's and an upside down T. Literally what this task is doing some version of counting. So the number of blue dots is equal to the number of upright T's. And then here you have an equal number of upright and upside down T's, so that's just 1 dot on each. And the language model seems to be quite capable of taking in a new testing input and being able to count the number of T's that are existing in this grid representation. Remember, all of this is just represented in the form of numbers, which is pretty insane. You also have another pattern here, which is pretty complex, but I'll leave it to y'all to take a look as well later offline. So all of this is powered by in-context learning, which is the same thing that we've been using to do code as policies, but just in a more symbolic fashion. Previously, this has been used in order to complete language tasks, but what's interesting is that we're finding that they can also complete various arbitrary symbolic patterns. So the ARC is one type of pattern set for which this works, but then you can also simplify it down to even simpler patterns if you want, depending on whatever application you're doing. So for instance, in this problem task, we're going to have 530 as an input, and we're going to have 35 as the output. So you can imagine, for example, I'm just going to draw out the patterns here so that you can see it more clearly. Essentially, we're taking in the first 2 digits, we're swapping the first 2 digits, and then we're removing the third one. So here again, we're swapping the first 2 digits, removing the third one. And so given these new 3 numbers, we're going to be swapping 4 and 8 into 8, 4, and deleting 5. So if we put this back into this representation and we ask the language model to complete it, it will complete the correct 8, 4. And you can also swap out these numbers with whatever arbitrary numbers you need, and it will still complete the pattern. So this is pretty exciting, but what's also interesting too is that even in this completion capability, if you start to remove the space delimited, the spaces that are in between the numbers, this will actually fall apart. And the reason why this doesn't work is because you've effectively taken away the tokenization accurately. Because specifically when these language models are tokenizing it, this particular string sequence, when you separate based on a space, it's going to be taking in the digit 5, space 5 into one token. And then it'll also separate into space 3 into another token. But then when you remove that space, then the language model, at least the tokenization step, is going to combine 530 into one token. And this is actually the reason why you might find that the abstract reasoning corpus, it appears in the NLP benchmarks, but most models appear to struggle, which is that the tokenization scheme, it usually oftentimes destroys the bias that exists inside of the way in which these language models or these benchmarks are built. And so if you just, essentially, if you have this particular input and output problem setting, 86 and 68, they map to different tokens. But then really what we want to do is to separate 8 and 6 into different tokens so that the actual pattern or the bias that exists in the sequence can be captured. And so a simple fix is just to separate it with commas, for instance, and suddenly you can get these language models that can sort of repeat these patterns quite well. And I think that this is probably the reason why we haven't really discovered these capabilities, is because they're kind of hidden inside of the details. So ultimately, you can get these models to complete these arbitrary patterns. And what's even more crazy, to me at least, is that if we take, for example, the initial grid spatial examples that we put in earlier, and then we replace this with arbitrary tokens that like do not necessarily match what the problem was defined in, or just randomly sampled from the vocabulary. I'm actually going to go into the paper and see if I can copy paste the Chinese character that we had used. And then put that here. The language model will also just sort of try to pull the pattern apart together and then try to complete the pattern respectively. So I think this part, is missing a plus sign, but anyways, it's taking the B and the @ sign and the Chinese character and trying to pull it to the corners. And I think this is interesting because if you go into the ARC benchmark and you replace each of the mappings of each individual digit into arbitrary random tokens that you take in from the vocabulary, they can still complete these patterns. And what that suggests is that these models, they have a degree of token invariance. And what they're doing is they're grokking the patterns inside the higher level layers, inside of the self-attention, inside the model. And so these are sort of somewhat stored inside the latent representations. And as it's grokking internet data, it's storing these patterns that it can reuse for future tasks. And I think this is particularly exciting. We also find later on that this also works for soft tokens too. This is continuous embeddings. So instead of trying to random sample tokens from the vocabulary, you can also construct a random arbitrary continuous embedding, use that as a representation of a token, but express your sequence in a fixed vocabulary of continuous embeddings. And you will find that you will also still be able to get some degree of sequence completion, which is through in-context learning. So there's some spatial rearrangement tasks that you can express in this way. One example is that you can take a high-res image, bring it down to a low-res image, and then in-context learn a grasp detector. You can represent your pixels, for example, with a 9-bit palette, and then try to get a language model to complete, or at least predict what would happen next with several input-output examples. And you can get in-context grasp detection, or even in-context forward dynamics modeling. So in this particular work, those capabilities of being able to do transformations, this is falls under one class of capabilities that we explored in the paper, and there are two other interesting capabilities: sequence completion and sequence improvement. In sequence completion, what we find is that these language models are also capable of completing simple function classes. So if you have a sinusoid and you are extrapolating the sinusoid, everything in colored here is essentially the completion of the language models. They can get pretty good at it. So exactly how the problem is expressed is that you can think of it as expressing the function here as just a sequence of numbers and having the language model finish it off. That works quite well, and you can immediately capitalize on that with some robot examples too, or learning from demonstrations. For instance, you can take a scripted demonstration of a robot drawing loops and have it continue to draw loops. You can also have a person in context teach the robot kinesthetically how to sweep a table and then have it continue sweeping on the table. So those are a couple videos here, but in the interest of time, I'm just going to jump ahead a little bit. But ultimately, what those two things in tandem do together, the sequence transformations and sequence extrapolations, is that they ultimately lead to this last capability here, sequence improvement. And the way in which you can think of it is that in context, you pass in multiple trajectories and then prompt the LLM to produce a higher reward trajectory. The idea being that, say that you have some particular policy rollout, save all of the data that you're getting from the policy rollout, represent it in terms of symbols that you have for whatever particular pattern or representation you have for the task, put it in context, have multiple examples of them, and then also label them with rewards. So you might be able to get them from, for example, your environment that you're working with. And at test time, you ask for a higher reward trajectory. So in this case, where, for example, we have some trajectories here, and 98, for example, is the target reward that we want. And then we're getting a state representation from the environment, which is 4450. And then we have an action that we want to predict, which is 0. So this is a closed loop system where in your environment, you're getting your current state and you're asking the language model with next token prediction to predict the next action. And what you end up getting is a system that can end up doing some pretty cool things. For example, here, just by taking in this large array of numbers with no textual data going into the language model, it is capable of discovering stabilizing controller for carpool. And what's going into the language model is literally what you see down here, just arrays of numbers, but then using that to capture, for example, the carpool angle as well as the actions, which can be 1 or 2. But the idea being that we're constantly asking for a higher reward trajectory. And you can think of this as essentially zero-shot decision transformers, but with a large language model. And you can get some pretty, across language models, you can get fairly consistent sequential improvements of the trajectories themselves. And 200 here is the max reward. So we're pretty excited about this. Initially, if you have random starting points, you'll find that the carpool always falls over to the side. So if you plot pull angle over time steps, the darker episodes are essentially the earlier episodes in this optimization process. But then every time you do a rollout, you add that to the language model context buffer, and then you ask for a higher reward. And continually doing this over and over, you start getting policies that can roll out and discover these oscillatory patterns that do the carpool balancing task. This also extends to a clicker setting that we had where we want a robot to push an object, and whenever the robot moves towards the object and maybe does something that we want it to, we give it a clicker signal. And so this is just kind of reminiscent to how clicker dog training works, which is you want to give them a positive signal, and then you're just taking the sum of the clicker signals and passing it to the language model and having it try to reproduce higher clicker signal sum reward trajectories. Eventually you could get the robot to push the chip bag here. A couple takeaways from ultimately from this project is that LLMs, they show a surprising ability to generalize to sequence transformations, complete simple function classes, and iteratively improve sequences with in-context learning. They also demonstrate a degree of token invariance, which hint at their abilities to represent patterns abstractly. These capabilities are generally more salient with scale. And also today, they're a little bit impractical in terms of like high inference costs, a little bit unpredictable. But I think that the way in which they seemingly can provide some of these capabilities may provide new perspectives on language, the role of language pre-training for generalist robot learning models. So specifically, I think there's a wish list of topics that I have for this community here, which is, I think that what I love about this community is the capacity to be able to have the rigor to look into ways in which we can leverage more patterns inside of the applications that we're looking at in robot learning. And some of the questions that I think we really need your help on figuring out are, for example, why, where, and when do these patterns emerge from in-context learning, and why? These transformers, they seem to be capable of grokking these patterns, and we can reuse them for various different tasks. But is this unique to transformers? Do patterns emerge from pre-training in other domains as well? For example, video data. Can this be a mechanism for positive transfer between modalities? For example, if you have tactile data, can you map that into a symbolic representation and then ultimately do some version of pattern completion to do tactile tasks? Could we build a benchmark to evaluate today's models on symmetries? Which symmetries can't be captured with in-context training on internet data? And finally, how can we leverage more of these capabilities in robotics are all open questions. So with that, I'd like to thank all my collaborators. We had a fun time working on this and other projects as well. And thank you all for your time.
Thanks a lot for the great talk. So we have time for a couple of questions, so please. Right, I guess I have a question first. So yeah. I'm a little bit, I'm thinking about the number of tokens that the large language model can, can take in, right? So if you're thinking about like a high resolution image, for example, 256 by 256, and then we have, I guess, a couple of them in sequence, is that gonna be a problem?
Oh yeah, definitely a problem. So today we have at least open source APIs oftentimes 4,096 tokens, with some of the chat models up to 32,000 tokens. Internally, I think we've only been up to 32 tokens as well for some of our own language models. I think that context size is a limitation for the kinds of problems we can express with symbols. But I also think that if we look into the future, NLP people are trying to help us figure out, how to put in 1 million tokens or even more in context. And I'd imagine that 2 years from now, we might be able to have more to work with. So we could sort of ride the progress of what others have been doing in the community as well.
Yeah, thanks.
Hey, Andy. Hey. Nice to see you. This is really, really cool. I really just had a clarification question. You said at the end with the clicker training and with the carpool training, you like ask for a higher reward signal. Is that you literally just ask? I mean, we're living in a weird world now. So how does that actually work?
Yeah, we literally just ask. So in this example here, well, specifically for the carpool example, we would take the maximum reward that we've seen in any trajectory, and we add 20, and then we ask for a trajectory with that reward. That's it.
That's wild. Yeah. Thank you.
Yeah, no problem.
As far as I know, one of the bottleneck in using LLMs for robotic manipulation or other robotic tasks is about the grounding of visual inputs to the language models, and possibly vice versa. And I'm very curious about the capabilities of recent multimodal LLMs. So are they capable of being used alone without visual groundings, or it also these a kind of grounding models together with LLMs? So I'm very curious about their efficiency.
Yeah, that's a good question. I think the thing that I like about today's multimodal visual language models, for example, in our own work, PalmE, we were taking Poly, which is a vision transformer, doing the image reduction into 16 by 16 tokens, and then passing that into a large language model. I think the nice part about having a encoder type architecture is that brings the token representation of the image down to something that's tractable with today's large language models. But I do think that there's a possibility that in the far future, we might not even have that step, where maybe one day we're just feeding in bytes of the pixels as tokens that we're passing into a large transformer. Some of those bytes are pixels, some of those bytes are characters and text. And I think there is a paper recently from Facebook that was discussed, Megabyte, which is discussing that idea. And I think we are going to potentially go into more unified representations, but not in the way in which we have different encoders, but probably just going into the more raw fundamental data representations.
Thank you for the answer.
Thanks.
Thank you so much for the talk. This carpool example looks really interesting, and it's quite counterintuitive to me that these language models are trained only on like text, and it's going to learn some language, but that seems quite different from these control sequence and stuff. Do you have any like intuitions you can provide as to like why this can work?
Yeah, so there's a couple parts to that specifically, and the first one is that the one thing to note is that we're in an online setting here, and so we have a capacity for some random exploration by just increasing the temperature of the language model, and in that case you have the capacity to sort of pop up a little bit and leverage randomness to your advantage there. The specific thing that we've observed over time is that in context learning, it acts a lot like BC. And this is just in part because how the language models have been trained. You have a particular data set and task, you pull all of your examples from that data set, and then you're essentially learning this BC model to do it on these textual tasks. And so when we were doing these things, or the carpool examples, you can do an experiment where you have a fixed set of offline examples and you have the language model try to perturb beyond the distribution of examples that you have. And what we find is that you get trajectories that are within the upper echelon of the existing data set that you have, but they don't quite move beyond that. And so the way that we're thinking about how this cartpole example seems to work is that it's just doing some version of top percent BC. The top percent here being that whenever we're putting in or deciding which trajectories to put in context, we're putting in the trajectories with the highest rewards. And so yeah, I think that it's probably doing a version of BC here, but then it's just surprising that it even works.
So it's not like learning how to improve. It's more like just behavior cloning from the
Yeah, at least that's my interpretation so far. But I think that code is available on the website up here in the GitHub for Google Research General Pattern Machines. I'd invite you to try that out, and I think those are open questions that we would love to get your help on figuring out.
Thank you so much.
Thanks, Andy, again. That's great. Okay, so next we will have our contributed paper sessions. So the first talk is morphological symmetries in robot learning. And the presenter is Daniel from Polytechnic University of Catalonia, please.
Perfecto. Okay. Good day. My name is Daniel Ordóñez, and I will present our workshop paper, Morphological Symmetries in Robot Learning, our summary of our RSS paper, Undiscrete Symmetries of Robotic Systems, a group theoretic and data-driven analysis. So our work studies, morphological symmetries in locomoting systems. So these symmetries are a prevalent characteristic in animal biology, characterized by the duplication and balance distribution of body parts. So what we do is that we study this phenomena from the lens of dynamical systems and group theory in order to characterize it also as a prevalent feature in robotics and computer graphics, and to identify the implications that these symmetries have in learning applications. So we define a morphological symmetry as a capability that some dynamical systems have to imitate rotations, reflections, and translations of space with feasible discrete changes in the state configuration. For instance, all bipedal systems have the capability to imitate reflections of space with feasible state transformations. While all reflections of space are unfeasible transformations, a morphological symmetry is always associated with a state transformation that is feasible. Another example is the capability that some quadruped robots have to imitate 180 degrees rotations with feasible state transformations. Now, for these systems and for the symmetries specifically, both transformations are feasible, meaning that for a given system state, there exists a multiple set of kinematic and dynamic configuration solutions. Now, the reason that we're interested in to study these symmetries is because these symmetries translate from morphology to the system dynamics, optimal control policies, and to all proprioceptive and stereoceptive measurements. The symmetries of dynamics become apparent through the system equivariant equations of motion. Simply put, this implies that any set of motion trajectories originating from symmetric states will remain related by the same symmetry transformation through time. Now, for control systems, equivariant dynamics implies equivariant optimal control policies. As before, this means that any set of optimally controlled trajectories of motion starting from initial symmetric conditions will remain related by the same symmetry transformation through time. The animations don't look that nice, sorry, but trust me. Lastly, morphological symmetries extend to all proprioceptive and stereoceptive measurements. This signifies that for any data measurement that we obtain from our robot or from the environment, we can obtain an additional set of symmetric measurements simply by exploiting the system symmetries. This applies to all relevant measurements in computer graphics, computational biology, and also robotics. Now, our goal is to provide the theoretical abstractions that are required to generalize the concept of a morphological symmetry beyond the trivial reflection symmetry. So among the various systems that we study with our proper formalism, some quadruped robots stand out with a remarkable eightfold symmetry. For these systems, for every system state, there exists 7 different symmetric states, meaning that in practice, if we were to use that augmentation for the systems, for every minute of data recording from the robot operation doing any particular task, we will obtain an additional 7 minutes of recordings of our data simply by exploiting the system symmetries. Now, furthermore, morphological symmetry suggests that any learning task can be seamlessly transferred across all symmetric states of the system. Now, for these quadruped systems, for example, the motion skill of walking forward or recovering from a particular disturbance can be transferred independent of the robot's heading orientation, left-right orientation, or even if the robot is turned upside down. I can show the animations afterwards more nicely. So consider an example of approximating a particular function that maps the state of our system to some relevant geometrical object, such as the feed contact state of our robot. So because the robot has morphological symmetries, every symmetric state of our system is associated with a symmetric context state. Now, a function that maps symmetric inputs to symmetric outputs is known as an equivariant function. In data-driven methods, equivariance is an inductive bias that we want to exploit either through the use of data augmentation or through the use of equivariance constraints in our machine learning models. So if we were to impose equivariance constraints in our machine learning models, such as in this example, a neural network, we will ensure that during all stages of training, the symmetries of the input and the symmetries of the output of our learning problem will get respected, which in practical terms for our example means that if we feed to our model the set of symmetric states, we will obtain as an output the set of symmetric context states. Now, imposing equivariance constraints in machine learning models amount to a reduction in the number of trainable parameters. In our paper, we show that for the case of neural networks and for the case of morphological symmetries, because we are dealing with finite groups, the reduction of parameters is inversely proportional to the number of symmetries of the system. So for example, for the robot solo, it means that we will reduce the number of parameters to 1/8. So for a particular neural architecture that we want. We also show empirical evidence that this reduction of parameters, that means either data augmentation or equivariance constraints, provide enhanced generalization and enhanced sample efficiency, always equivariant models being better than using data augmentation. So I don't have more time, but I want also to present our code repository in which we are planning to create a library. We have already a library of dynamical systems with their morphological symmetries identified for everybody to experiment with, where you can also create equivariant neural networks quite easily.
Okay, so the next talk is Edge Grass Network. Presenter is Xu Peng from Northeastern. Let's jump to the next one. Seems like there's some Zoom issue. So the next talk is including equivariant models for generative graphical inverse kinematics, and the presenter is Oliver from Toronto University. I think he's online. Sorry, 1 second. I don't think we can hear you.
Yeah, I'm online.
Oh yeah, okay, great. So please go ahead.
Sure. All right. Hi everyone, my name is Oliver, and today I'll be presenting my work on Euclidean equivariant models for generative graphical inverse kinematics on behalf of myself and my co-authors. So in this work, we investigate the use of symmetries in learning for inverse kinematics, or the process or problem of finding a joint configuration given some desired and effective pose. So IK for redundant manipulators is typically solved using numerical methods. And these methods tend to be sensitive to initial conditions and typically only output a single solution when in many cases there are infinitely many. On the other hand, learning-based methods to IK can be efficient and can produce multiple solutions in parallel with a single forward pass and no initial conditions. However, unfortunately, they usually only work for a single robot that you use to train on. So in our work, we investigate how can we bypass this limitation of learning-based IK by using a graph-based representation and exploiting spatial symmetries in the learning problem. So we have recently explored a distance geometric description of inverse kinematics for Revolute manipulators. And this representation, which is visualized on the right, allows us to describe configurations of robot manipulators as geometric graphs. So you can represent structure, poses, joint limits, as well as obstacles. And this comes with some nice advantages. One of them being we can use architectures like graph neural networks, which can accept problems of arbitrary robots with different numbers of degrees of freedom. And the graphical formulation enables the use of Euclidean or E3 equivariant functions to exploit the spatial symmetry that's built in robot manipulators. And that allows us to learn accurate IK solutions efficiently. So our method, which we call generative graphical inverse kinematics, or GGIK, is a graph conditional variational autoencoder that either solves or produces good initial guesses for inverse kinematics problems. And we follow the typical training procedure for VAEs using the evidenced lower bound or elbow loss during training. And as a quick overview, we have an encoder in blue, a decoder in yellow that respectfully encode and decode completed graphs G, representing robot solution configurations. And conditioned on partial problem graphs, G tilde, which represents the IK problem definition. So for example, structural information and the goal pose, the prior networking green learns to encode a latent space distribution of graphs near multiple latent encodings, of full graphs or IK solutions. So during inference, what this looks like is a mapping from partial graphs or IK problems to completed graphs, which are solutions, using only the prior and decoder network in this case. And one thing that we observed was that using equivariant layers in our GNN was a crucial component for efficiently training models that converge and output good solutions. So in the ablation study that I'm showing in the table, we compared to 4 other popular GNN layers, and all of them were not able to compete with the equivariant graph neural networks architecture in terms of both accuracy and the evidence lower bound of a test set. So in this case, dashes represent cases where a valid configuration could not be extracted from the network's output. So once trained, we have a single model that can sample multiple solutions in a single batch for multiple different robot architectures. So visualized here, we have 5 different common industrial manipulators. And with a single model, we can get many solutions for a single goal pose because most of them are redundant. And you can see it captures continuous solution sets as well as discrete ones. For example, the UR10. Thank you for listening. And I linked the paper here as well as the code. And if anyone has any questions, please feel free to email me.
Thanks a lot for the great talk. So Xupeng, are you good to present? Sorry. No? Okay. So next talk is point-based correspondence estimation for class alignment and manipulation. So the presenter is Thomas from CMU. Please. Okay. So you want the presenter know? Yeah. Okay. So you can do the and then
Oh, okay, so you have it. Oh, here. Yeah, and then you can just share.
Oh, I didn't know I could. Okay, hi, my name is Thomas Wang, and I am presenting point-based correspondence estimation for cloth alignment and manipulation. This is joint work with Mansi Agarwal and David Helt. So, sorry, one second. Okay, so we address the task of cloth manipulation. Cloth manipulation is challenging because the deformability of cloth results in a much higher configuration space than rigid objects. Furthermore, the space of potential actions on a cloth is large, and the dynamics are complex. But nevertheless, manipulating cloth has applications in a variety of settings, such as home automation, clothing retail, hospice care, and more. So there is a significant body of literature on cloth manipulation, and we focus here on Fabric FlowNet, the work most closely related to our contribution. Fabric FlowNet proposed a bimanual goal-conditioned policy for cloth folding, and it decouples reasoning about the desired cloth motion from reasoning about robot actions. Fabric FlowNet adapts optical flow, a concept typically used to match pixels between an observed cloth image, or sorry, pixels between video frames to the task of matching pixels between an observed cloth image and a goal. So after estimating the dense flow correspondence between the observation and the goal, Fabric FlowNet then predicts the robot pick and place actions to achieve that goal. One of Fabric FlowNet's limitations, however, is that it was not designed to handle cases where the observation and the goal are not aligned. So on aligned observations and goals, Fabric FlowNet performs well, but if you actually rotate or unalign the goals, then Fabric FlowNet ends up performing much worse. So what is the reason for that, and how can we address that problem? So the problem here is that Fabric FlowNet is designed to work for cases where the goals are aligned, and correspondences only contain information about deformation in the cases where there's actual alignment. But in the cases where you have an unaligned goal, the correspondences actually contain information about alignment as well as deformation. And so a potential solution for unaligned goals was introduced in cloth funnels, but their approach provides a locally optimal solution due to using an adaptation of a rigid transformation algorithm for aligning deformable objects. So how can we decouple alignment and deformation information in these per point correspondences? We propose Fabric Flow AlignNet, an approach which asymptotically achieves a global solution for aligning the observation and goal cloths. FFAN differs from Fabric FlowNet in two ways. So first, we estimate 3D flow correspondence as opposed to 2D. And second, we use these 3D correspondences to estimate the rotation transform required to align the goal with the observation. After alignment, FFAN then predicts the action required to manipulate the cloth to the goal, similar to the previous Fabric FlowNet work. So in this talk, I'll focus on the actual alignment procedure. It's very simple. We estimate the rotation matrix for aligning the observation and the goal using a ransack-style algorithm. So first, we sample pairs of points according to the estimated flow correspondences and compute the rotation transform for this sample. And then we warp the goal points according to the proposed rotation and compute the inliers, where inliers are points with flow magnitude less than a threshold. So the rotation transform returned is the one with the maximum number of inliers. We evaluate our method on test sets with fully aligned goals, as well as on goals with varying degrees of rotation separated into easy, medium, and hard categories. And we show the hard categories on the right here, where the rotation range is just like full rotation. And we show that our performance achieves similar performance to Fabric FlowNet on the easy difficulty sets, but performs significantly better on the larger rotations. And when we actually use ground truth correspondences as the oracle comparison, we see the best performance, showing the importance of using accurate correspondences for alignment. So returning to the previous qualitative examples that we saw before, with aligned goals, the performance between the two methods is similar. With unaligned goals, however, we see that Fabric Flow AlignNet outperforms the previous method. So I'd like to thank our collaborators and funding sources for making this work possible. Please stop by our poster and see our paper for additional details. Thank you.
Thanks a lot for the talk. So Xupeng will present the edge graph network. Sorry about the technical issue. Here we are. Sorry about the delay. Hi everybody, my name is Xupeng Zhu from Northeastern University. Today, that's back. Let's try that again. Here we are. Finally solved the bug. Hello everybody, my name is Xupeng Zhu from Northeastern University. Today I'm glad to present our work, Edge Grasp Network, a graph-based SE3 invariant approach to grasp detection. It's a joint work with Haojie Huang, Lian Wang, Robin Waters, and Robert Platt. As we know, the 3D grasp pipelines could be divided into two classes. First is directly mapping from the observation to action space, or second class is sampling actions and evaluate each action. Our method belongs to the second sampling classes. So the sampling including 3 steps. First, we sample a contact point, PC, and then calculate its surface normal, NC. These together determined 4 degrees of freedom. And then we choose the surface normal direction because it could provide the largest friction according to the friction cone theory. And then we sample an approach point and center the gripper toward this point. So the approach point, the surface normal, altogether could define the 6 degree of the grasp pose. We call this tuple an edge. And through the implementation perspective, we will first sample an approach point and then take a local cropping the point cloud that's within a specific radius. So the cropping enabled us to achieve the translational invariance. And then we feed the point cloud to the PointNet++ architecture, obtaining the point-wise features, and then extract the global feature through a MLP layer and the max pooling. Later, we concatenate the global feature with each point-wise feature to form the edge feature. And from the edge feature, we can estimate the grasp quality. We train the entire pipeline end-to-end using binary cross entropy loss, and the dataset contains 3.4 million of grasps generated from the simulator that contained packed scenario as well as the pilot scenario. We have also implemented the SO3 invariant property in the grasp function. Specifically, given an observation and an action and its grasping quality, we apply any random SO3 rotation to the function, the grasp quality should stay the same. We achieve this through 2 options. The first option is data augmentation, and the second option is using equivalent neural network, specifically vector neurons. So the first option, we turn it as edge grasp net, and second option as VN edge grasp net. We also show the loss function. The loss function tells an interesting thing, which is
when we consider the SO3 invariance, it can achieve a better accuracy. And moreover, the equivalent model can converges faster. After we train the model, we have tested it extensively in both household objects as well as the adversarial objects. So our model can achieve more than 90% success rate in the household objects and more than 80% success rate in Berkeley adversarial objects. One concern of the traditional sampling-based method is the time. Our method can parallel multiple grasping pulses, therefore we can infer 2,000 grasps within 10 milliseconds. Lastly, our method can easily control the specific contact location. This also leads to the future direction, which is proposed grasps conditioned on the segmentation mask or language instructions. Our code and video is available online, and thank you, everybody.
All right, thanks, Qifeng. So the next talk is continue reinforcement learning with group symmetries. The presenter is Meng Di from CMU. Please.
And maybe you need to like go back to your you did talk. I don't know how to do it. So if you just share and then present, you won't have to.
Okay. Hi everyone. My name is Meng Di, and I'm from Carnegie Mellon University. And today, my topic is continuation-based RL with group symmetries. And this is a joint work with my collaborators Shiqi, Peide, Xilun, Yongkang, Kentaro, and Ding. So in this work, we are interested in the continual or the lifelong learning setting, which means that our environment is in general non-stationary with changing dynamics model and also reward function over time. So for instance, taking this continual tabletop manipulation setting, as an example, like the robot may have to push slide the plate toward different goal locations, or also like pushing the drawers toward different directions based on the drawer's initial configurations. And also in this paper, we are interested in the task agnostic online continual learning setting, which means that we do not know the task boundaries beforehand, and the robot or the algorithm has to infer the task boundaries on the fly. So in this paper, the main question we are trying to answer is that, like with unknown task definitions, how to learn a stream of tasks with strong sample efficiency and also the generalization capability. So the takeaway message right here in our work is that we model the geometric similarities among tasks, and also we use the unsupervised learning method to detect the task boundaries. So like we already know that the geometric information actually can help generalization, and tasks with reflected configurations can actually easily be solved by some reflecting actions. So in this work, because recall that we are interested in the continual learning setting, so we grow a policy for each task group instead of a single task as previous works. So in each task group, it actually contains equivalent or equivalent tasks under the same group operations. So here's the like the first key component of our work, and we call our work as coppers. So the first key component is the equivalent policy network. So our network actually takes 3 types of information as input, including the bird eye view image of the initial frame at time step 0, and also the bird eye view image of the current frame, and also like some robot state and also auxiliary information at each time step. So both other information will serve as input to the equivalent feature extractor, and the resulting equivalent features will help generate the kind of invariant value network and also the equivalent policy network as prior works. And the second key component of our work is the unsupervised clustering mechanism to detect the task boundaries. So like recall that we are interested in the task agnostic setting. So it becomes more important to know like which task group the current task belongs to. So in our work, we calculate the one Wasserstein distance of the current task to the same task groups based on the equivalent features. And also we reuse the old policy if a relatively smaller distance, and also grow a new policy if the distance is larger than some predefined threshold. So here are some training results in simulation. So we can see that Culver's is actually the blue curve, and it performs similar to the Culver's ground truth, which and the Culver's ground truth actually has the additional information about the ground truth labels of each task, and which can serve as the oracle information, the oracle performance, or all the methods can achieve under our setting. And also we can see that Culver's actually performs much better than other like continual learning and other state-of-art continual learning settings, including 3RL, which use both the recurrent neural network and also the replay buffer, and also Clear, which mainly uses the replay buffer. So here are some visualization videos of our method in simulation. So actually each background color shows one task group, and we in total have like 4 task groups, including like a sliding place and button push, and also close drawer, and also goal reach. And here are some results for the like real world validation, which means that we directly take the policy weight trained from the simulator and deploy in the real world. Oh, sorry, it doesn't seem to. Okay, actually the task groups in the real world are the same as the ones in the simulation. Okay, so that is the overview of our work. So I'm happy to take any questions in the poster session. Thank you.
Thanks a lot for the great talk. The next talk is geometric regularity with robot intrinsic symmetry in reinforcement learning. The presenter is Shen Chao from University of Freiburg, and he's online.
Can you hear me now?
Yes.
Hello. Yeah, great. Thanks. Hello, everyone. My name is Shen Chao Yan from the University of Freiburg, Germany. I will introduce our work, Geometric Regularity with Robot Intrinsic Symmetry in Reinforcement Learning. Actually, I have a code now, and I hope a sudden sneeze won't scare you. Okay. Training neural networks on high-dimensional data is known to be challenging due to the curse of dimensionality. We experience this problem also in deep reinforcement learning for robot control tasks. For robots with more joints, the current reinforcement learning algorithms always generate non-realistic or suboptimal policies. To solve this problem, some researchers introduced periodic gait patterns as shown in the left image. Usually, quadrupedal animals will follow certain gaits for locomotion with different speeds. Others let robot mimic recorded motion from humans or animals as in the right video. Although both approaches can help with the problem, they share an obvious shortcoming. The robot should be similar to some existing creatures, or they execute similar tasks as their movement. We think it is necessary to find another solution without such limitations. It should help bionic robots to learn natural and optimal policies for new and challenging tasks for which we do not have enough data or prior knowledge. Moreover, robots without real-world counterpartners should also benefit from it. We propose multi-agent reinforcement learning with symmetry augmentation. It may seem strange when you hear controlling one robot with multi-agent methods, but I believe it will be natural after my explanation. Now let's have a brief look at single agent and multi-agent reinforcement learning. They use machine learning to control an agent in an environment to achieve the maximum expected reward. For the multi-agent version, more than one agent exists and interact in the environment. Each of them has its own observation, reward, or policy, which could be shared or different. In our method, we first divide single robots into multiple parts according to the symmetry structures. As in the images, the gray joints belong to the central part, while the colored joints to the symmetric part. Each symmetric part will be controlled by an individual agent. The central part will be controlled by all agents together. I'll utilize the locomotion task of this ant robot to explain our method. As all robot parts cooperate to move, they share the same reward defined by the robot movement. Policy sharing is employed because of its following benefits. It enables sharing learned representations among agents, and it reduces optimization space for the whole environment. As a result, the action space dimension is reduced from 8 to only 2 for this ant robot. However, naively sharing policy may hurt learning performance because all limbs will execute the same movement if they are given the same observations. We solve this by discretely rotating the ant robot, including its moving direction around the z-axis of its torso for different agents. In the right image, with the transformations, the corresponding body parts are all rotated to the lower left corner, which is originally the purple one. This transformation turns all agents to be homogeneous. We use multi-agent PPO as training algorithm. This policy network is designed to be equivariant to the robot symmetry, either reflection or rotation. The T operator represents the reflectional or rotational transformation according to the symmetry. The central part of policy output is designed for robots with joints in the torso, such as humanoid robots, the twists, and as the transformation should not change the state value of the optimal policy, the centralized critic network is designed to be invariant with respect to the robot symmetry. We execute experiments for 5 tasks in ISAC-SIEM. We compare our methods with 3 baselines: single agent training with PPO, single agent PPO with extra symmetry loss, where basically we augment training data with symmetry, and multi-agent with naive parameter sharing, where each agent gets the same observation from the robot concatenated with a one-hot agent ID. This is the training curve for all the tasks. Multi-agent with symmetry augmentation significantly outperforms the other baselines, which is the red curve from our method. By comparing the results of baselines, we observe that SASA utilizing augmented symmetric data can learn to solve a few tasks with apparently lower data efficiency. And multi-agent structure itself cannot generate meaningful results at all, which follows the criticism of naively sharing parameters. In the qualitative results of some tasks, we can observe that our method enables the robot to solve them all, while the baseline can only solve the balance beam walking task. Furthermore, robots with MASA generate more natural movement than the baseline. To conclude, we propose a novel architecture to learn single robot control tasks with multi-agent methods. It outperforms the SOTA on-policy reinforcement learning method with a great margin in challenging tasks, and it can also be applied in off-policy, imitation, or model-based learnings. There are limitations for this method, of course. It needs symmetry in the robot, and we also need domain knowledge to define the transformation functions. Thanks for your attention, and please stop by the stop poster to look into our project page for more details.
Thanks, Lao Xuntao. Great talk.
Thank you.
Okay, so the next talk is Geometric Algebra Transformers. Presenter is Johan from Qualcomm AI Research.
Hi there. I'm still waiting for the last presenter to stop sharing the screen so I can share mine.
Sorry for that.
Thank you. All right. Yes, thanks a lot for having me. I wish I could be there with you right now. but I'm happy I can present our work, Geometric Algebra Transformers, work together with my colleagues Pim de Haan, Sönke Behrens, and Taco Cohen. My name is Johann Bremer. We live in a geometric world, and we task our robots with solving problems that often involve geometric data as well. Geometric problems benefit from geometric solutions. In this paper, we present the Geometric Algebra Transformer, or GATA, a new universal architecture for problems with geometric data. GATA is based on 3 principles. GATA represents data, input data, output data, and hidden representations using multivectors from geometric algebra. GATA uses the idea of E3 equivariance when defining the layers of its architecture. And finally, these layers are composed together in a transformer architecture. Let me go through these 3 principles one by one. Geometric algebra, or real Clifford algebra, is an idea from the 19th century that was influential in the development and formalization of quantum mechanics and later impactful in computer graphics, but hasn't really gained much traction in machine learning yet. There's a series of a few recent papers on this, but that's about it. In a nutshell, what it gives us is a 16-dimensional representation that we can use to represent objects in 3-dimensional space that goes beyond the usual representations of geometric deep learning. In particular, it gives us a kind of typing. It represents a point differently from a direction vector. And the kind of a linear movement or rotationary movement representation is different from a point representation as well. A little bit more concretely, there's an established dictionary that allows us to represent common geometric objects like planes and lines and points, or common geometric transformations that you can act on these objects like reflections or translations or rotations in the 16-dimensional space. Finally, in addition to this representation, geometric algebra defines a series of canonical operations, including what they call the geometric product or the wedge product, that allows us to compute new geometric types from existing geometric types. Think of computing the translation vector that connects 2 points. Anyway, of course, the data that a robot observes directly in an environment is not given to us in terms of the 16-dimensional representation. So we envision our architecture to be used in a pipeline as follows. So you have some raw inputs. Think of the pixels of a camera. They are pre-processed with some computer vision pipeline and passed into geometric objects like the position of objects, the velocity with which objects move, and the orientation of objects. We then use the dictionary I just flashed at you to represent these geometric data types in these multivector from geometric algebra, use the architecture that I will show you on the next slides, and finally extract the quantities of interest for a given robotic problem from our pipeline. Okay, now our architecture consists of several layers being a deep learning model, and these layers are based on the principle of E3 equivariance. I know I'm preaching to the choir here, so don't let me really define this, but of course, equivariance is the idea that when inputs are transformed in a particular way, the outputs of a function transform consistently with the inputs. In particular, we design a couple of novel E3 equivariant layers for our architecture, including linear layers for these geometric algebra representations, non-linearities, normalization layers, new geometric layers that allow us to compute these new geometric features from existing geometric features, and a geometric equivariant attention mechanism. We piece these components together in a transformer. So this is a schematic representation of our architecture. And if you look from a distance and squint a little bit, this really looks like a standard transformer based on pre-layer norm normalization layers and so on. And there's a couple of things we could talk about here, maybe just very briefly comment on that the architecture is very flexible with respect to the structure of the input and output data. There can be 1 or multiple token dimensions. Let me also stress that while this looks very similar to established transformers, many components have been generalized here, or all components have been generalized. In particular, the attention block is a generalization of the established scale dot product attention to geometric algebra and equivariance. We include this novel geometric layer that I briefly mentioned. And finally, because we follow this established recipe of attention-based transformers, we find that we can stack many of these blocks quite efficiently without having problems propagating. This defines our data architecture. We tested this on the first few experiments. Let me just quickly show you one of the results here. This is a robotic block stacking problem, purely in simulation and purely based on robotic states. So there's no pixel level data here, introduced in an ICMA paper last year. And we found that our method, GATA, which you can see here in green, at the top not only improves the performance based on the full data set, but drastically improves the sample efficiency compared to equivariant and non-equivariant baselines in the original paper that introduced this paper. We can achieve a state-of-the-art performance when using just 1% of the training data. Now, for full transparency and fairness, I also want to give a quick shout out to some competitive work or some related work that came out concurrently. There's a series of paper by Johannes Brandstetter, David Rowe, and collaborators. In particular, this latest of their series is quite closely related to what I'm presenting here. Please do check it out. It's called Clifford Group Equivariant Neural Networks. But if you're interested in our work, I'd, of course, like to draw your attention also to the longer version of our paper that you can find on the archive at 2305.18415. And I'd be very happy if you find this interesting and have a look. Thank you very much for your attention, and enjoy the rest of the workshop, in particular in person.
Thanks a lot, Johan. Okay, so the next paper is Spatial Generalization of Visual Imitation Learning with Position Environment Regularization. The presenter is Zhao Heng from UC Berkeley.
Okay, hello. I'm Zhao Heng from the UC Berkeley, and this work is done when
Sorry, excuse me. You're showing the presenter view.
Okay. Sorry, can you? Okay. Sorry, wait a minute.
Yeah, no worries.
Yeah. Okay, can you see my screen now? Okay,
yeah,
great. Okay, so I'm Zhao Heng from the UC Berkeley, and this work is done when I'm a student at the Hong Kong University of Science and Technology. And this work is also done with Professor Yang Gao and Professor Qifeng Chen. Okay, so generalization of visual imitation learning is a very challenging problem. And this problem has various aspects. For example, generalization to unseen textures, unseen backgrounds are also very important aspects. But here we study a problem called spatial generalization in those object-centric tasks, such as the robotic manipulation. The problem is, for example, you would like to put a block to a target region, but you only have a limited expert data. So how can you do this when the object setup is different from the training data set? Okay, so the idea is that absolute information like the coordinate should be removed from the representation. For example, we should not rely on the coordinate of the target box or the target region to make the decision. We should rely on those relative relational information, such as the distance and direction for during decision making. But please note that this does not mean the policy does not rely on those absolute information. For example, we would like to the learn feature look like the difference of two coordinates. So this is a relative, the relative direction and the distance. And we would not like their concatenation, such as the concatenation of x1 and x2. Okay, so how can we realize this? Well, a naive realization is that we can pairwisely minimize the mutual information between the feature and the coordinate of each object. But the problem is that this is very inconvenient and even intractable. For example, if you have too many objects in the observation, you have to add up a lot of loss function terms, and that may result in the training difficulties. Also, if you have occlusion problem, for example, in robotic manipulation, you cannot detect an unoccluded object, then you cannot get the position of that object. So the minimization of this loss function becomes intractable. So how can we overcome this problem? Our idea is that we can use a deep learning interpretation method called GradCam. The GradCam can output an activation map of the current policy. We know that the GradCam only can tell you what object the current model is attending to. So you can sample the position of that object and minimize its mutual information with current feature. And we refer you to the paper for the implementation details. And we validate our method on the magical benchmark, and the procedural generalization benchmark. And we test our method on the behavior cloning with Impala as a backbone network. And we train the whole policy network from scratch. And our method is able to outperform the other state-of-the-art regularization baselines by a very large margin. For example, on the warehouse and manipulation problem, we are able to improve by 30%. And on the procedural generalization benchmark, the boost is a bit smaller, but we still can have a 10% improvement. And here are some qualitative results. We compare our method to the dropout, which turns out to be a very strong baseline in the previous experiments. Our method is able to attend to the correct object. Here, note that this red object is a distractor, and the goal of the agent is to pick this green box to the target green region. And you can see that in the dropout, the model will attend to this red object or the target location at the wrong times. But for our method, we consistently ignore this red object and attend to the correct the target objects. And we also extend our experiments to a real-world pick and place problem. And similarly, we train a robotic manipulator to pick up a red block to a target region in the presence of multiple distractor objects. And here we still only compare our method to the dropout, and we can consistently outperform this method by 20 to 30% in the success rate. And yeah, thank you. That's all. And if you have any questions, you can send me an email because I'm presenting remotely. Thank you very much.
All right, thanks a lot, Ghaffari. Okay, so that concludes this section. So next we will have our poster session and coffee break. And I will see you guys in 30 minutes. All right, let's start our next session. So we're gonna have our second oral presentation, progressive learning for physics-informed neural motion planning, and the presenter is Ruiqi. Take it away.
Hi, I'm Ruiqi. I will present our work about progressive learning for physics-informed motion planning. It's a joint work with my advisor, Ahmad Kurish at Purdue University. Motion planning is a central component in robotics research that bridges perception and control, and its objective to use the perception of the given environment and find the path in the environment for a start point and a goal point. And the robot will move along that trajectory using a controller. There are two basic requirements for motion planning. First one is safety. Robot cannot collide with the obstacles. The second one is efficiency. Motion planning should be fast for real-time application. And we propose a physics-informed motion planning method. Okay, sorry. Let me first talk about some related works. One is a traditional method. The first one is sampling-based method that samples collision-free space and build a graph inside space. Then this method extracts path solutions connecting the start and goal point. This kind of method has some probabilistic completeness. However, they are usually slow for high-dimensional problems in the cluttered environment. The second category of method is the search-based method. This kind of method discretizes the space to the grid and use graph search to find a path. This kind of method has some optimal guarantee for the fixed resolution. However, it's hard to extend to higher dimension because of the curse of dimensionality. And both of the methods are slow, so we need some new method. Recently, a neural network, neural motion planning method have become promising tools. Researchers use neural network to learn from XPath passes. XPath passes are often generated using traditional method like RT star. And once trained, this kind of method generates samples or path point more efficiently and achieve like a sub-second result. Another kind of method learn a scalar. It's like a cost-to-go function, and it also comes from the export trajectories. And finally, their path is extracted from the scalar's gradient or negative gradient from gradient design. From sampling-based method and search-based method to neural motion planning method, we can see that motion planning method have become increasingly more efficient in recent years. However, one drawback of current neural motion planning method is they need a large amount of training data. And this year, we propose a new framework called NT-field that views motion planning as solving a partial differential equation. And NT-field does not need export training data, and we generate paths more efficient than current neural motion planning method. NT-field is based on the following K observations. The first one is a grid-based fast marching method, FFM, solves a partial differential equation called the iconal equation. And the solution represents the shortest time from start point to the goal point. And the time is shown in the gray counterline in the figures. The gradient of the arrival time will lead to the blue path solution in the figure. Second, recent physics-informed neural network PIN, it also solves the general PDE by directly minimize the PDE loss, and it does not need ground truth numerical solutions. And an example of such kind of method is called IconNet. It also solves the iconal equation for geography applications. And the NT-field idea is to use PIN to solve the iconal equation for motion planning applications. First, let me briefly talk about the iconal equation. Iconal equation compute arrival times gradient on the start point X and the goal point Y. And the norm of the gradient is the inverse of the speed at the start point and the goal point. And the speed is user-defined. It's related to the obstacle. Consider a robot moving in the space, and it can freely move in the free space, so the speed is constantly high. However, it should stop when it meets obstacle, so we define the speed is low near the obstacle. So in the figure, we show a box obstacle, and the yellow part is the free space, the speed is high, and the blue or dark blue part is the obstacle, and the speed is low. That's how we define the speed. Second, we show some property of the iconal equation, and we use neural network. How do we use neural network to solve it? The first property is the symmetric property. If we exchange start and goal, the iconal equation's solution should be the same. The second one is if the start and goal point is the same point, then the arrival time is directly 0. The final property comes from the motion planning requirement. If we want to make the robot avoid the obstacle, we need some place that have 0 speed. That means from the free space point or any point, if we want to go to a point inside the obstacle, we need infinite time. However, the infinite is not easy to predict it by neural network. So we propose a factorized iconal equations. We use tau to represent it, and it's the distance from the start point to the goal point over the exact speed. By this kind of factorization, our tau is always between 0 and 1, and it's easy for neural network to predict. And we propose a architecture to fit it. Our neural network's input is the start and goal configuration point. So besides 3-dimensional points, it can be like 6-dimensional angular points for manipulators. And then we feed it into a MLP structure and get some features. Note that these MLP structures are same for the start point and the goal point to keep the symmetric property. And then we also use a workspace encoder that use forward kinematic to compute the robot pose and compute its relationship between the obstacle to get another kind of feature, because we want to know if the robot is close to the obstacle or far away from the obstacle. And finally, we use a symmetric operator to combine them together and get one features. We use a minimum and maximum to get this kind of symmetric features. And finally, we get the combination of the whole feature. And Then we put it into another MLP-based structure, and we call it time field generator. Finally, we use our neural network predicts the scalar tau, and we can compute the exact solution by the factorize the equations T. Again, we recall the Icono equation. Our neural network can predict the time from X, the start point X to the goal point Y. And then we can compute by the predicted speed by call the Icono equation. We can compute the gradient of T on start point X and goal point Y, and then compute its norm, and then inverse to get predicted speed X and speed on Y. And our training is based on our speed model. So it's based on the robot obstacle distance. If the robot is in the free space, it has high speed. If it's in the obstacle place, it has low speed. So that's how we get our training data. And we sample a lot of start and goal point in the robot configuration space, and we can compute robot obstacle distance and get speed. It's super fast, and we use 1 minute to compute 1 million training data. It's much faster than previous method because they need to run traditional motion planning method multiple times. And now, since we get the predicted speed from the neural network, and we get the ground truth speed from the speed model, we can train based on some loss between them. And that's our loss data. After we get the trained time and it's correct, we can directly do planning by compute the times gradient. And it's bidirectional and just several step gradient descent step, it can find a valid solution. NT field have some good points because it does not need to require export training data, and it has significantly low computational time because of several step gradient descent. Also, it can directly extend to high dimensional scenario because our structure are mainly MLP based. And this figure shows NT fields in an indoor environment, and the red plot shows the counter line is time field. However, it has some cons. The first one is it has relatively low success rate in complex environment because and it does not scale to the multiple scenarios. The issue is come from the Icono equation's property. The Icono equation is nonlinear and its solution is not smooth. Also, the physics-informed loss, we need to compute the neural network's output gradient based on input. So it's very hard to optimize. So in our current work, we propose a method to learn a better strategy, propose a better strategy to train for the physics-informed loss. It includes a novel progressive speed scheduling strategy and new viscosity-based Icono equations. First, let's see the progressive speed scattering strategy. We find the problem of NT fields is not only because of the Icono equations, but also because of the condition of the equation. We can see the non-smooth and the extreme change of the solution, the counter line. It's not only, it's due to the low speed area, it's changed sharply in the low speed area. So we can also find many sharp features in that place. However, if the environment has no obstacles, it's just the solution is just some circles and counter lines. So it's very easy for neural network to learn. And we can see from the animation, the interpolation from the without speed to low speed zone is continuous. If we gradually decrease the speed in the obstacle area, the interpolation of the time field and speed field are always continuous. So the idea is we first learn the trivial solution for the no speed area. Then we gradually decrease the speed in the obstacle area and get the neural network to learn the final solution with some sharp features. Another idea is viscosity-based Icono equations. The viscosity-based Econo equation comes from the vanishing viscosity method for solving the Hamilton-Jacobi equation. It adds a Laplacian term and makes the nonlinear Econo equation becomes a semi-linear elliptic PDE. It has a smooth and unique solution. And the coefficient of the Laplacian will change the smoothness of the solution as the figure shows. And practically, we use 10 to the power of -3 as the coefficient for the Laplacian to get a similar result with the numerical ground truth. Our framework is similar like an NT-field, but we remove the workspace encoder for simplification, and we add a random Fourier filters to the Z-space encoder. And for symmetric operator and time generator, they are the same thing. We apply the speed scheduling strategy during training, and we apply the viscosity term in the loss function. Now let me show some experiment result. First is some ablation study. We are training our method without the scheduling strategy and without viscosity term on the same neural network, and our method can get the same result as the numerical ground truth, and other method cannot get the correct result. By fixing the training error, currently we can scale into multiple things in one model. The figure and the table show our model, our method in 2 Gibson environment, and our method is the most efficient one as has a similar result with the numerical ground truth. That means our length and safe margin are similar. Also, our method has near 100% success rate, and it's much higher than a previous NT-field method. Like NT-field, our method can directly scale to high-dimensional robot manipulators. In the figure, we show a complex motion planning task in a cabinet. Our method uses 0.07 seconds to find a path, while RT Connect uses about 20 seconds, and NT-field fails for this case. We also demonstrate our method in real-world problems. The video shows our method to make UR5 go deep into the cabinet without collision, and all cases are computed within 0.1 second. About the limitation and future work, our method only considers kinematic constraints, and our next objective is to consider the dynamical motion planning, consider more robot dynamics. And another limitation is our method, although it can encode multiple environment, but we only encode multiple known environment. So another direction is we explore novel environmental encodings and extend our method to novel environment. In conclusion, we propose a progressive learning approach for physics-informed neural motion planning, and it includes a speed scattering strategy and a viscosity-based equation. And it has higher success rate and extend to multiple and real-world scenarios. Thank you for listening.
Okay, thanks a lot, Ruiqi, for the talk. Do we have questions from the audience? I have a question for you. So for your real-world experiments, I wonder, like, what is your so how did you get the let's say the shape of the cabinet? Do you have like the ground truth shape, or did you use any camera?
I use real scan I use real things to get the scan of the cabinet, and it's point cloud based. So our training data is like generated on such kind of point cloud.
Could I ask a question?
Yeah.
Oh, sorry. Should I? Yeah. Okay. So, as far as I understood, the loss function that you are using for training is only considering the norm, right? You are not using the vector of the velocity or the vector of the derivative. You are matching the norm of the derivative of the time or the t function to the one divided by the velocity.
So that's a lost term. So I think.
Yeah. So basically, you are using the norm of the grad T.
Yeah, I use the norm of the gradient of the neural network.
But it calls my attention that even if you are using the norm of the gradient, it's still able to learn a proper direction of the vector.
Yeah, I cannot learn the direction of let me think. So I cannot learn the direction of the gradient. So I only learn the norm of the gradient.
Yeah.
And after it's learned, because my training data include a lot of start and go pairs. So after it's learned, the gradient direction itself is the correct direction. But in my training, I do not include any ground truth direction for it.
Yeah. No, but it's kind of it's impressive that it's able to get it from using the norm.
Yeah, that part is only for the planning part.
Okay, thank you.
Okay, let's thank Ruiqi again. Okay. Professor Bekkers, can you hear me?
Yeah, I can hear you.
Okay, great. Okay, so the next session is a talk by Professor Erik Bekkers. So Professor Erik Bekkers is an assistant professor in geometric deep learning in the machine learning lab of the University of Amsterdam. Professor Bekkers developed medical image analysis algorithms based on the sub-Riemannian geometry in the Lie group SC2 using the same mathematical principles that underlie human visual perception. His current work is on generalization of group convolution neural networks and the improvements of their computational and representation efficiency. So today we are very pleased to have Professor Bekkers as an expert in geometric deep learning to tell us about his experience in the field. And his talk is titled Group Equivalent Deep Learning in Convolutional Form. So please take it away, Professor Bekkers.
Yeah, thank you very much for this introduction. It says here currently that my screen sharing is paused. Is that correct? Like, can you see any of my screen?
Yeah, we can see your slide.
And now if I go to the next slide, you see it? Or it's still stuck at the main screen?
No, yeah, it's still on the first slide.
Okay, let me just, and now I lost my mouse as well. Let me, oh, okay, we're sharing again. Okay, as soon as I do full screen, it stops. So I'm going to do a different sharing mode. All right. Yes, here we are, right?
Yeah, great.
Okay, cool. Yeah, no, thanks again for the introduction. And yeah, thanks for inviting me as well. It was great actually to catch in the last talk. You know, I worked on motion planning as well on ND groups on sub-Riemannian geometry. So this was kind of nice to see. Okay, maybe I should get back to this field of motion planning. Looks pretty exciting. Okay, as for today, yeah, let's just go ahead. So I wanted to talk a bit about group convolutions. And I think in the morning you also saw a talk by Tess, Smidt. You saw other stuff with group equivariance, and quite often it's either fully the regular group convolution of viewpoint, which is pretty common in computer vision, or the steerable or the tensor field network type, which seems maybe at some side unrelated, apart from both being equivariant. But today I'm going to show try to do this a bit more explicitly, like how they are related, and that's via Fourier transforms and the Clebsch-Gordon tensor product. And I want to do this because it actually is very helpful to have this perspective often to see, okay, regular group convolution is a form of template matching, and you can efficiently code this up in a steerable form, or efficiency, that's a relative term, right? Depends on if you have access to certain grids of your groups or spheres or whatever, then it might be more beneficial to do things in the regular domain. So I want to go about explaining this figure today. So let's start off straight with the problem often is, but I guess you don't have to explain that by now, like if you want to work on tasks like, okay, what is the potential energy of this molecule? The AI system typically doesn't know because it doesn't have any sense of geometry, right? So we have to equip it with them. And even if you move to more advanced tasks like motion planning just now or other things that require really understanding of geometry, then it's really, it's going to go bad. So the objective here is this, how to, equip these AI systems with geometry. So that's what we're going to do here today, because once it has an understanding that the things that it's looking at, just like a coordinate, it's not just three scalars, it's just it is a vector, right? So it should be treated as a vector, not just as 3 numbers, which a plain neural network would do. And if you do this, then it might be doing a better job in solving a certain task. So reiterating the main components, invariance is, of course, that, if you transform your input, the output stays the same, which is pretty obvious when you work with molecular properties, that this is so the case. Formally, okay, so I don't have a mouse, but yeah, so formally, we write it like this. We have F is a neural network, for example. T is a transformation parameterized by a group, like a rotation, acting on its input. And if the output stays the same, then we call it invariant. Now, equivariance, that's a more interesting property. Maybe more importantly also, is that if we have, for example, a task in which quantities are not invariant, for example, the forces at the atoms, and if I rotated this molecule, then these forces should rotate accordingly. This is what we call equivariance, right? So there is some known transformation on the output. So again, T, on the input X, and then pull it through a neural network. F gives us a certain output, but it could also first pull the input to the neural network and then apply some transformation afterwards. And okay, this is what you call equivariance. And this is even more important than invariance because it means that information gets preserved in the neural network. It doesn't get lost or destroyed by the neural network. We can still recover like what would have happened if I rotated the stuff. Now, the standard way of dealing with this in many domains is by means of data augmentation, right? So if I have cells and I want to classify them as either healthy or pathological, well, it's one of the two, right? And often you see if you rotate it, it switches class. And this is something which I studied a lot in previous years and my PhD and closely after it, how can we solve this? And we did this via group convolutions. So, but obviously we started with data augmentations and this failed because then you still don't have any guarantee of invariance. You have your neural network, they have to figure out what are all the invariances in your neural network. They need to be robust to these transformations. And this leads to a lot of redundancy in your neural network weights. So you're losing a lot of valuable network capacity on learning stuff that we know very well how to model. So this is somewhat a silly approach in that respect. Back to equivariance, just a less iteration what it is. So if the input translates, for example, the output translates accordingly. This is translation equivariance, and it is the main factor why deep learning became such a big thing in computer vision. Because essentially it means if you're able to pick up a structure somewhere, you can also pick it up somewhere else because the information is just shifted to a different place. Yeah, so, okay, let's wait for the animation to end. All right, so a recap. Why do we care about equivariance? Because it means that no information gets lost when the input is transformed. Right, so it just shifts to different places in your feature maps. With equivariance, we can guarantee stability to certain transformation, and many applications demand this actually. And now what we're going to do with group convolutions, we're going to extend this equivariance beyond translation to rotation, scaling, or whatnot. And this allows you to provide geometric guarantees and has improved weight sharing. And I'm going to go to this point actually in the next section. So, so this field of equivariant deep learning is pretty rich. I should have also put like robotics here. That's something I feel that is not too familiar to me, but seems pretty exciting. But I come from a medical imaging background, And we have physics, where we have obviously very strong geometric priors and constraints of the systems. We have molecular and computational chemistry kind of applications. So those are all problems that really demand equivariance. So you really need it. And then for computer vision, it's mostly used as an inductive bias, right? You want to have some notion of weight sharing. If I want to be able to detect a person over here, I also want to be able to detect it over there under this orientation. And so then equivariance actually contributes to the success in the form of weight sharing, more than actually the equivariance constraints that you have there. Then we have the psychology of vision, which I personally find super nice in the relation to neuroscience. I'm not going to go into that detail today, but also there you have this concept of visual perception of things being built up of small components making whole objects. So you have these part-whole hierarchies, and that is beautifully modeled, I think, with group theory. And finally, we encounter like symmetries in nature, of course, as a very efficient way of, sort of hard coding information systems and utilizing symmetries to maintain large systems like a tree or a plant. So on to regular group convolutions. So yeah, so just want to always start with this, so that we're on the same page. Like a group is really a set of elements together with a group product, which just takes two group elements and spits out a new element in the group, and it has to satisfy these properties. But it's most useful to think of them as transformations, right? Transformations, there are many transformation groups, among which rotor translations. Now, so what does the group product tell you? It tells you that if I have like one group element G and another group element G prime, so one rotor translation parameters with X and a rotation matrix R theta, another one with X prime and R theta prime, the combined action of these group actions give you the one on the right-hand side. And so this is something that you cannot easily model, or you shouldn't model with the vector space or with other structures, because you cannot just add rotations and translations together and still have like a sensible idea of this being a combination of rotor translations. Okay, so that's why we use group theory, because if we work out what is the group product, then we can only work with the left-hand side, like G dot G prime, and keep the equations simple. And from the visual perception viewpoint, here's a smiley face, which I think of being composed of local orientations. For example, the nose pointing in a certain direction, the eyes should be above it in a certain translation, but also orientation. So there's some orientation to it, the mouth below it, and then the contour of the face around it. So you can sort of describe this as a set of group elements. Now, if I want to know what the smiley face looks like in any other point of space, I can also rely on the group theory by just multiplying all this whole set on the left-hand side with G. So I move this entire face to another location in space, and all the points rotate accordingly. So the relative positioning of all these particles, they stay intact. And this is the beauty of group theory, right? If we're able to describe something at the origin, I know perfectly well what it looks like in any other pose in space. So now we're going to translate this to neural networks. And so we don't work with sets of group elements. Actually, sometimes we do with point cloud-based methods. But in computer vision, for example, we tend to think of images as functions on a 2D space. So L2 meaning square integral functions. And for example, now we're interested in the group of rotor translations. What we then need is a way of transforming these images, right? So we need to let the group act on these images, and you typically do that via what you call the left regular representation. So the left regular representation transforms the domain with G inverse. So you see that to the bottom of the slide. And well, then you resample and you get your transformed thing. You do this with another group action, and then you notice you might as well do this at once with the product of these group elements. So representation is just another way of representing the group, but now it's really an operator that transforms things, and it's parameterized by its group elements. So how does this appear in group convolutions? So we have a feature map F and a convolution kernel K, and we're just going to take inner product. So I really like to see this as a template matching viewpoint. where, okay, here it is. So we have on the left-hand side a kernel, we have in the middle a feature map, and now we're going to match this pattern, this kernel, everywhere in our image. And we're going to match it for every translation, right? So we're going to move it, this green box, and whenever it's aligned, I get a high response, so it's bright. I record this at that location, move on to the next pixel, and obviously we do this efficiently with conv2d operators. But you see that convolutions is nothing else as, or correlations is nothing else as just template matching with some core template or the kernel. And since by construction these correlations are defined by this representation of the translation group, so that's this calligraphic L that you see over there. It's a group representation parameterized now by a translation element. And you can then easily show that this diagram commutes, meaning that translations and convolutions commute. But rotations do not necessarily commute with this operation. And that's maybe also now obvious because you see that the correlation operator is defined in terms of the representation of the translation group, here indicated in blue, whereas maybe we're interested in also being equivalent to rotation. So there's some mismatch going on. And you know, and then the easy thing you can do to start building group convolutions is just simply replace this representation of the translation group with that of the rota translation group. Still, the equation looks exactly the same. It's still taking inner products of the kernel with your function. And here's then an efficient thing that's often used for what you call affine groups that can be split in such a way that you first apply a rotation or another subgroup transformation, and then followed by a translation part. And this makes it very convenient to implement. So it looks like this again. So we do template matching. We have this core template, a line detector. We rotate it, test it for every point in space, rotate it, translate it again. And this fills up this feature map, which you see on the right-hand side, but now it has this extra access to it. And this is important. So now it not only records the presence of features locally for each coordinate xy, but fixed at each coordinate xy, we get a whole fiber of responses or how well did this pattern match, right? So we lift the feature maps to a high dimensional space. And now it's also going to get closer to the tensor field viewpoint where you typically think of having at each point a fiber attached of steerable things that rotate also according to rotations. And this rotation looks a bit like this. If I have this input pattern and I do my group convolution, I get the thing on the right-hand side. And if I rotate that thing on the left-hand side and look at the nose, for example, this orange arrow, it has a certain orientation to it, right? And the animation on the bottom right, you see this nose going upward along this orientation fiber, right? Because if I rotate the stuff, it moves along the fiber in a certain way. And because the vertical axis coded for orientation. All right. Yeah, so you can repeat this process. The equations keep looking the same. It's just that now our objects are no longer two-dimensional, but three-dimensional. In this case, SC2. They now function on position orientation space. And the kernels do something like, hey, I want to detect a pattern of a nose over here, an eye over there, at this particular orientation, and there, and you do your template matching. And then you pick up two of these peaks because there were two smiley faces in the original image. And the peaks, they appear in distinct spatial location, but also distinct orientation planes because they have different orientations. Okay, so a summary. For regular group convolutions, it looks something like this. You do your lifting convolution, which decomposes your image into oriented features. In the group convolution layer, they are able to pick up patterns of, well, spatial and locally oriented patterns, like smiley faces being composed out of local orientations. And if you're only interested in the location, like where was the smiley face, regardless of its orientation, you can do a projection, a max pooling, for example, over the orientation fibers. And this is similar like you would have with computer vision. If you want to be invariant to translations, you pool over the entire spatial domain. And this conceptually generalizes to other type of groups like translation and scaling. So now on to steerable group convolutions. Because I still want to make this bridge to tensor field type networks. When I talk about steerable functions, I talk about a collection of functions, like a vector of functions, which if I want to rotate them, for example, I let a group act on its domain. So that's in red, you see G acting on X, the input of Y. This rotation can also be achieved by just keeping the vector of basis functions fixed and only rotate the vector itself with a representation of the group. And this is what you call steerable basis functions. And it looks something like this, right? So if I have, for example, a Gaussian derivative, I can rotate the direction of the derivative by taking a dx, dy, like cosine theta dx plus sine theta dy or minus. And that creates this rotation that you see at the bottom over here. So apparently, there are such classes of functions that I can steer in this way. Yeah, and that's what we're going to do. We're going to expand functions in these kind of bases, such that if you want to rotate a function, we only have to rotate the coefficients of these functions and leave the basis itself intact. And that's what you typically do in these point cloud or graph neural networks. You pre-sample the basis functions, like the edge attributes, and then there's no need to explicitly rotate things around. This is an example which you might be familiar with from Fourier theory, like the circle harmonics. It's a Fourier basis on the ring. So all these sines and cosines, and they can be shifted by multiplying them with a complex number exponential with the same frequency, right? So in this case, the big matrix here is the representation of this, SO2 actually, so the periodic shift group on these steerable vectors. So I'm saying this circle harmonics because we're moving on to spherical harmonics later on. All of this relates to Fourier theory, right? And from that, we also know that these spherical harmonics, circle harmonics form a complete orthonormal basis. So it means any function can be, in principle, be represented in this basis. So that's nice if we do convolutional neural networks. We want to be expressive. Yeah, so we have that property. And together with the property that they're steerable, that if we have a function expressed in such a steerable basis, then we can easily shift, transform it without doing anything of function resampling. We just modify, the weights, the coefficients. Yeah, so this is going to get into a bit detail, but it showed circular harmonics, which are, functions on S1, on the one ring. But we're actually interested now, I'm still in the computer vision case, functions on 2D planes. But obviously SO2 does not act transitively in R2, so we need to do something about this, and we do this by switching to polar coordinates. So we switch the domain, split the domain in a radial part and an angular part. So also our convolution kernels are parameterized then in such a way. Then for the angular part and the radial part, we use circular harmonics and some radial basis functions respectively. And once we do that and we rewrite things, we can show that any such kernel is then represented as a sum of circular harmonics weighted with coefficients that depend on the radius, or that may depend on the radius. And this is the typical form that you see in these spherical or steerable convolutional neural networks. And once you do this, you say, okay, my kernel is expanded in such a circular or spherical harmonic basis. Then it's also automatically steerable, as you see in the bottom of the slide. Yeah, less practical now, like you don't necessarily need explicitly these radial basis functions. It's often a good thing to do, but people pull them also, like if you have a radius parameter, like a coordinate, you can also pull it through a neural network to spit out the weights. So have an MLP parameterize this kernel essentially. Okay, so this is what these circular harmonics in 2D look like. So you have a real and imaginary part. We stack them on top of each other. And this is what the representation matrix then look like, right? It's a block diagonal structure. These blocks are the irreducible representations, and they act on these separate, distinct subparts of the spherical harmonics vector spaces. Okay, I see I'm running out of time a bit, so I'm going to move on to the point. So we're going to revisit lifting convolutions that you saw in the example before. So again, if we now do our lifting convolutions with kernels expanded in these circle harmonics, then we want to rotate, right? We want to template matching, the kernel rotated, match it, rotate it. So if we do that, we can also make use of linearity of this linear basis expansion and move the expansion outside, right? So that's like we can first pre-convolve the image with the basis functions. Let's call that f hat super y, and then do the evaluation. That's on the left-hand side, is rho h w, the coefficients of the kernel. And this is precisely what Freeman and Edelson did in, in the 90s on steerable convolutional network. This f hat essentially contains all directional information locally, in your image data or in your functions. But there's something awkward about this, that if you want to know what was the result of my kernel at this orientation, at that location, in the readout, so it still depends on age over there, I have to evaluate this dot product with W, and typically you want W to describe features. So you want to integrate it in your feature maps. And okay, so I'm doing that here with some tricks, so that the trace trig, like inner product, can be described as the trace of the outer product. And what you then do is that f hat, y, and w are joined together, right? So you can evaluate that, and that's what I would call f hat. So then you see, if I want to evaluate the output of the group convolution, I first need to compute f hat, which was convolved with the basis functions, then take this tensor product with w, which I'm not going to show in this talk, but is essentially a Clebsch-Gordon tensor product in the end, if you do this in the full group convolution setting. And then I can steer this and evaluate. But interestingly, this equation is precisely the form of an inverse Fourier transform. And I know there's a lot of group theory in the background here, but the main point I'm trying to make here, that instead of explicitly doing the rotation of the kernel, do all the matching, we can also do something clever by convolving with spherical harmonic basis functions, and expand with tensor product with W. And what it really means is that I can do this group convolution either directly with the kernels, that gives me the stack of oriented responses that you see at the top, or I convolve with these basis functions and these weights that I have over there, and then I get something like a field of Fourier coefficients. And this is what the stream of tensor field type network does. You typically specify, hey, I want to go up to this many frequencies, and the Clebsch-Gordon tensor product has been worked out and all these operations, and then you obtain these like Fourier type feature fields, which do not explicitly say, okay, what was the feature at this direction or this direction, but you can obtain it by taking this inverse Fourier transform. So in the regular group convolution case, you have at each point like a fiber of orientation responses. And in the steerable case, you have a vector of Fourier coefficients, which were generated by these circle harmonics. And so if I increase the frequency of these circle harmonics, then I can also get more and more detail in your regular group convolution feature maps. Yeah, so that's essentially the point I'm trying to make here, that I didn't show the theorem here, but there's this theorem that says any linear map that is equivariant is a group convolution. And then if you know this, then it's clear that, well, every operator that is indeed equivariant, it looks complicated maybe with Clebsch-Gordon tensor products and whatnot, then it's important to realize it's still some form of group convolution. And for me, this is helpful because I come from this more template matching viewpoint, which is intuitive to me. And for maybe physicist-oriented people, the tensor field network type might be more intuitive. But the difference is either we bake in the rotational structure in the domain of your feature maps, or you do this in the codomain. Yeah, so I guess I have to skip this part. Maybe many of you are already comfortable with message passing. But the point also on point clouds, you want to leverage these symmetries and respect geometric constraints. And so you want to utilize geometry essentially. So if you want to send messages around, you can either utilize the displacement factors, like what is the displacement between two neighboring atoms, for example, or points. But then you're only equivariant to translations. You can then limit it to the distance, but then is kind of restrictive because you no longer know where that information comes from, only from what distance it came. Or you again lift to the group, right? So you could still attach a fiber of grid points to each location. Like you're going to test what was the response for this rotation, this, and this. And you know, have a grid of rotation attached to each vector, at each location, and do your regular group convolutions. And at first sight, this looks kind of inefficient because you need to do these operations for all these grid elements, you know, multiple times, but you can very efficiently code this up. And I came across this paper by Maani, and I'm not sure if you attended this talk earlier today. It was pretty cool. Well, that you can do all of this also very efficiently in the regular convolutional viewpoint. And this is also something that we recently did for SE3 group convolutions for volumetric data. So we have also a library now coming out based on random grids, and which is kind of efficient because we share the same SR3 grid at each location, but randomly perturb it during training. And it's these kind of things. And then we have the steerable feature networks, which I think, sorry, I didn't attend your talk, Tess, but I hope she advocated for this a bit earlier today. And the main difference between this is in the regular case, you're able to just use with scalars. But it means that anything you do, all these pairwise interactions should be invariant. Otherwise, you're breaking equivariant stuff. And in the other case, you're actually directly able to use vectors, force vectors, and whatnot. But then you have to be more careful in the kind of operations that you use. So both have their efficiency and, you know, different routes to efficiency. And personally, I like the top one better because, in my point of view, it's simple because it uses only like scalars. But you can always switch between the two with Fourier type transforms. Yeah, I'm going to skip the examples. I mean, if you want to learn more about tensor field networks and such, I definitely recommend this seminal paper by Nathaniel Thomas and Tess. On the right-hand side, there's a paper that we wrote 2 years ago or so, where we included an overview of all these steerable and group convolution methods, trying to unify it a bit, like I was just trying to do. So sorry for rushing over this, but I hope you get the main point across. So I feel like in the field, there's roughly like somewhat of a divide between regular group convolution and steerable group convolutions, where one talks exclusively about tensor fields and Clebsch-Gordon operators, and the other is almost, yeah, it's steerable, but what is steerable group convolutions and regular group convolution? And also that's a bit complicated, but I just want to show in this slide that it's more or less one and the same. And if you want to learn about this, so I gave this course like now, and for the second time last year, I made videos on various topics from regular to steerable group convolutions to equivariant graph neural networks. And we have updated tutorials there. Yeah, so if you want to find more details, like I made some explicit derivation of regular to steerable group convolutions and some background group theory, you'll find it there. Yeah, and that's it for now. So thanks for listening.
Thanks a lot, Professor Bekkers, for the great talk. So we have time for 1 or 2 questions. I guess one question I have is that on the first part of your talk, in the regular group convolution case, what do you think about the trade-off between the size of the group in the network versus the performance? So you know, when I used the equivalent network before, it seems like the performance is gonna saturate as the set of the group increases. For example, like maybe C4, C8, there is going to be like a big improvement on performance, but when I go from C8 to 618, maybe there won't be like a large improvement.
Yeah.
So what's your thought on that? Yeah.
No, it's definitely the case. It's like it depends on the size of your convolution kernel. Also here you have some sort of Nyquist frequency. Like if you go beyond this frequency, you're not going to pick up on more detail. And in fact, you're only going to introduce aliasing artifacts. And it's the same here. This tiny convolution kernel, I can rotate it maybe with 90 degrees. I see a clear difference, right, in response. If I rotate it 45 degrees still, but if I only rotate it like 10 degrees, because it's such a small locally supported thing, it won't barely be a change. So then the resolution is, or actually the output response of the feature map you see on the right-hand side with this theta axis is in principle a continuous axis because you generate it over the entire group, but it's band limited. The functions are band limited, and the band limit is based on the spatial extent of your kernel, like how much detail does the kernel have in the first place. And that then again establishes a connection between the steerable tensor field networks where you also say, okay, I want to go up to this many frequencies, which says essentially I want to be able to capture this much detail between local rotations. Yeah.
I see. Thanks a lot for the intuition. So, Professor Smidt, you have a question?
Hey, Erik, thanks for the great talk. This is a really beautiful description of the connection of group convolution with steerable filters. So, yeah, it's really, really amazing visuals. I can't imagine how long it took you to put the slides together.
And I've been reusing them for a while, so it wasn't
yeah, no, I hope you are, because they're really great. I had a question about your experience in so teaching these concepts in class, and specifically, how do you typically combine these explanations with explaining, like, in the case of steerable filters, you mentioned about how, you know, you can have scalars, but you can also have other data types. Like, how have you found, like, what's effective in your class for motivating kind of the different types of data types that can appear in the networks? I'm just kind of curious from your experience in the classroom.
Yeah, no, I think I start off with this template. Yeah, so you need both viewpoints really, like the tensor field one and this one, I think, to get a good, you know, grip on what you do. And if I go to what's it? Link is not working. Maybe, I'm not sure if I have it there. So like I have a selection of topics, and for each lecture series, like I have a section of group theory in between, squeezed in between, and then you know, I go over some examples, but I try to push some of the theory a bit more to the back. But yeah, when it comes to these irreducible representations, I think an explanation of Fourier transform helps. But I do notice also with the class that, you know, some students are just really digging this and they dive straight into it, and others, yeah, they just stick to the intuitive part, and that's fine with me as well. But for the Clebsch-Gordon part, for example, I think I took the example from your paper with Thomas. That really gives explicit examples of how we have this dot product, which is turns into two vectors in a scalar, and we have the cross product and these kind of things. And yeah, so my experience is they like the animations. The mathematics is sometimes
I like them too.
Great. Yeah, that's an achievement. No, yeah, so it's that, and so to get some intuition, so it's nice that they get comfortable with the terminology, and that's where it starts, I guess.
Yeah, cool. Yeah, no, it's really helpful just to hear your experience too, because this is definitely something that do you put all the theory in front and then you get to the neural networks, or do you kind of mix it in? And so I'm kind of figuring out in the next iteration of my class how to go about this. So it's really helpful to hear about your experience.
I tried to mix it along the way, but like in last round, we had right after lectures, we had a tutorial where they go over the Colab notebooks, and they're online, by the way, and then there's TAs around that help. And so I think, yeah, as with any course, you need some hands-on experience as well.
Yeah, cool. Thanks, Erik.
All right, you're welcome.
All right, let's thank Professor Bekkers again. Okay, so our next speaker is Professor Wang. Professor Wang is an assistant professor at Peking University. His research interests include 3D vision, robotics, and machine learning. His research objective is to endow embodied agents working in complex real-world scenes with generalizable 3D vision and interaction policies. Professor Wang's IC3 equivalent post-estimation paper is one of the first paper that I ever read in equivalent learning, and it was also one of the pioneer works in using equivalent model in post-estimation. And today I'm very happy to invite Professor Wang to give a talk.
Okay. Hello, guys. It's my honor to present some of my works in this great workshop today. The topic of my talk would be handling and modeling symmetry in post-estimation. I'm from Peking University. Thanks, Dian's introduction. So, again, today, so a lot of topic will be revolving around 60 pose estimation. I believe everyone here should know this concept very well. It's basically 60 pose. It's just a 60 transformation from one frame to another frame. Usually the first frame is the object reference frame, and the second frame is the space, either the camera living or human living, basically the world reference frame. So like in this 60 space, 3 degrees of freedom belongs to translation and 3 degrees of freedom belongs to rotations. The 60 pose estimation things have been widely used in robotic manipulation, object state estimation, camera pose, or odometry estimation, and SLAM. So for example, you know, in robotic manipulation, sometimes we care about object pose estimation or tracking the pose, because this can serve as visual closed loop control and tell us whether you are moving this object correctly, whether the object pose or position are in a good shape. And for grasping, now I think the most successful pipeline for parallel gripper grasping at least is to predict the 6 DOF or 7 DOF, which further include the 1 degree of freedom gripper width, basically leverage this grasping pose estimation to first know the pose and then use motion planning to move the gripper to the desired pose. So my point is like 60 pose estimation is widely used in a lot of robotic applications. And I'm gonna start with an easy case, so which is instance level 60 pose, 60 object pose estimation. This is the most established problem. Basically, you have a small set of known instances, and like you assume every object you has their ground truth CAD model, and this problem has been like leveraged in robotic grasping, especially known objects. So this problem is useful in certain controlled environments. However, definitely, you know, one limitation to this setting is that it's instance specific. So if you have novel objects, then you won't be able to estimate their pose. You even don't have the definition of their pose. So basically, when now people are get more and more interested in handling novel objects, in manipulation, in perception. So this instance level 60 pose estimation fell short in that case. So one thing I established during my PhD is the concept of category level 60 pose. So if you have seen a lot of MOG, you definitely can see their similarities across this object category, right? So when you see a new MOG, actually you don't really need to define the pose of it using a CAD model. You can simply generally talking about its orientation, because there are one unique direction in this object category that can define a category level reference frame. So the idea behind generalizing instance level pose to category level pose is that you need to aligning them in the orientation space, and then you definitely get a category level pose reference frame. Then when you see a novel object from this category, you don't really need its CAD model. You can directly talk about its pose. So this reference frame, I named it after normalized object coordinate space. It's basically in this space, all the objects from this object category are like aligned to one, common orientation, and their translation, their centers are zeroed out, and also their sides are normalized so that every object can be contained within this unit cube, actually with a diagonal length one. Yeah. So basically the first step is align their orientations. The second step is zero out the object center. And the third step is uniformly normalizing the scales. So then you get this, all the objects now are kind of in a canonical like shape, canonical size, canonical translation. So you get this reference frame, and then you can starting talking about category level pose. Basically, we can rigorously define a category level pose as the transformation from Knox reference frame to the world reference frame, which is a 7 degree of freedom similarity transformation involving 60 pose plus 1D uniform scale. And so back to that time, I found a way to, to predict this category level pose. Basically, for a 2D image, and you can, for each pixel, you can actually predict its coordinate in Knox. So this formulate this pose estimation problem as per pixel dense Knox value estimation problem, so that, for example, given this view of a camera, for each pixel, you can directly predict its Knox value. And note that you don't really need its depth because this Knox value is irrelevant of its true scale. It's a normalized value. So you don't really need to know its depth. You can predict its Knox value. And after you predict the Knox value of each pixel, and then you also, at this time, if you want to know its metric size and the 60 pose, you need its metric depth. And for each pixel, given the metric depth and camera intrinsics, you can get its point cloud in camera space. Then you have dense correspondence from each object point to its Knox value. Then you can definitely fit a 60 pose and 30 size between these two. So using orthogonal procrustes or something a little bit advanced, like called Umiyama algorithms. So back to that time, we leverage mask RCN to do this job. Basically, you can detect each object, and inside each ROI, you use the ROI align to extract its feature map, and for each cell in this feature map, you predict its. So basically, it's only add one branch to mask RCN, and you can predict the Knox value, dense Knox value for each pixel inside the object mask. And then you can do this pose fitting to get the category level 9D pose. Now, 9D is basically 60 pose plus 30 size. And why I want to mention this line of work is because this is the first time I'm, I come across the symmetry problem. Think about a bottle, right? So how do you a bottle, you can definitely get what is CAD model from your synthetic data set, and in this synthetic data set, each point on this CAD model has its own Knox value. But when you try to supervise the Knox prediction branch, you need to think about this supervision problem, right? So you when you are the first time to see a bottle, you don't really know which face is its front face, which is its back face. So there is no way you can, directly know, okay, so I know the Knox value of 1 pixel, and basically the underlying problem is symmetry. So that's why, in this work, we find a very, naive but useful approach to supervise the Knox value. So the way we do it is that we can arbitrarily choose one direction as the front face for those rotationally symmetric bottle. And then we generate the ground truth according to this choice of orientation. And then because our neural network actually cannot really know your arbitrary choice of the front orientation, right? So it actually its prediction can be correct whatever under whatever rotation along the gravity axis. So the way we do it is that we rotate the ground truth Knox value along the z direction for 12 times. Each time we rotate it 30 degrees, so that our ground truths actually cover 12 different possible ground truths. And then when we try to supervise this Knox map, we actually find the minimum loss between the network prediction and one of our 12 possible ground truths. So this here, the 12 is just a hyperparameter. You can easily make it 300, like 360, or you can make it even more. But in practice, we find 12 is good enough. And in this case, the neural network will find its fair rate way to predict a consistent Knox map. And then from the many possible ground truths, it will only be penalized to its nearest neighbor. This is how we deal with this symmetry supervision problem back to 2019. And so only with this loss, we find our category level post work on novel object instances. Here you can see there are a lot of can and bottle instances. Our predictions are actually different from the ground truths. Look at the bowl, like the bottle, the can, but it's still reasonable. And in this year, CVPR 2023, we actually take one big step forward. So we want to theoretically give a way to predict the multi-model distribution in rotation space. And one way to do that is modeling give a way to model the distribution in SO3. So we actually come up with a discrete normalizing flow to model arbitrary rotation distribution in SO3. This work is called Delving into Discrete Normalizing Flows on SO3 Manifold for Probabilistic Rotation Model. So just give you guys some introduction if you are not familiar with normalizing flow. So normalizing flow is a powerful tool to construct complex distribution by a sequence of invertible transformations of a base distribution. Rotation, as rotation can exhibit ambiguities if there is symmetry or if there is partial observations, and thus demands probabilistic modeling. So although there are many progress have been made in this field, but accommodate multimodal distribution in Euclidean space, there are it is very underexplored in SO3 because it is like a non-Euclidean space. And so as we know, like all the normalizing flow, if they are in Euclidean space, is very straightforward. And so once we move to the SO3, which for example, rotation matrix is actually just has 3 degrees of freedom. However, it is embedded in a 9 degree of freedom Euclidean space. So we really need to think how we can build like a normalizing flow in such a non-Euclidean manifold and make sure during the flow, every element are always on the SO3, not going out of the SO3 distributions. And so this is basically the problem we want to solve. And our goal is our flow is tailored for SO3, and there is no ambiguity, no singularity involved in this manifold, and there is no many-to-one mapping in this normalizing flow. Make sure it is a bijective mapping. So so this quick visualization shows that our method can actually work for those cone-like thing because it definitely has rotation symmetry around one axis, and the figure like to the right of it shows its like distribution. The distribution of its rotation on SO3, and for this for the cube, you actually have I think 24 symmetry mode, and so this is how it looks like in the visualization. So let's see how we make this happen. So modeling the probabilistic distribution of rotation is actually well established for single model, for single model distribution. For example, we have Bingham distribution for quaternions. We have Wang Mises distribution for Euler angles. We have matrix Fisher distribution for rotation matrices. But the limitation of all of the aforementioned models is that they are single model. And so if you have symmetry, and especially in the case that you do not know how many modes this object, how many symmetry modes this object involves, then you cannot even choose a mixture of model, right? You really need to specify the number of clusters before you build such a model. So it becomes a problem whether we can find a way to automatically adapt to an unknown number of symmetry modes and handle the arbitrary rotation distribution modeling. So that's why we use normalizing flow. And there are actually several works for normalizing flows on SO3 manifold. For example, this work called reparametrizing distribution on Lie groups, and they actually turn rotation into its axis angle representations. And axis angle representations is like a 3D vector in 3D Euclidean space. However, so if you're gonna just use this 3D vector and just use a three-dimensional the Euclidean space to map from the latency space to the axis angle target distribution space, this is fine. But the problem is people may know that this axis angle is not a continuous representations for modeling rotation. There are actually several singularity points for axis angle. For example, when the angle becomes 180, actually there are many-to-one mapping problems. So we really need to find a normalizing flow for the rotation matrix, which is the true compact representations for SO3 and also continuous rotation representation. So this is the motivation of our work. We want to directly build like a SO3, like a normalizing flow on SO3 manifold. And also, for example, this Riemannian continuous normalizing flow and try to find the normalizing flow on the tangent space and map back. So they are not really the normalizing flow on SO3 manifold. So what we have done is we introduce like a module here composed of Mobius coupling layer and affine transformation layer, and you can use multiple this rotation normalizing flow module as the way you use discrete normalizing flow. And then you can map base distribution to an arbitrary target distribution. So I mean, this Mobius coupling layers actually leverage the idea of leverage the similar idea of coupling layers in Euclidean space. Basically, it divide the rotation matrix into two parts. Like one part is fixed and the other transformed part is conditioned on the fixed part. So we actually use a very similar idea. Rotation matrix can be regarded as three orthogonal unit vectors. So therefore it can be divided into two parts. One column is fixed. The next two columns are restrained into a plane vertical to the fixed column lying on a circle. So then we can therefore use transformation on a circle to transform the second column, and the third column can be calculated via cross product of the first two columns. So if you want to transform on a circle, then you will this Mobius transformation would be useful. So for the sake of time, I cannot delve into the detail of this Mobius like transformation in this circle space, but this is basically a tool that we used to find the value of the second column given the first column is phrased. And once we know the first column and the second column, we can use cross product of the first and the second column to find the value of third column. And an interesting we find is that if we only use this Mobius coupling layers, this normalizing flow has very limited expressivity. So we further insert another quaternion affine transformation layer. This quaternion affine transformation layer is basically we apply an invertical 4x4 matrix on the quaternion and project it into the unit sphere via SVD decomposition. And this transformation can be decomposed in three operations: rotation followed by scaling, and normalization, and followed by rotation. So basically, so if we only have coupling layers, we will find that it's really it would be very hard for us to rotate all the distribution on SO3 at the same time. So that's why we involve this quaternion affine transformation layer, which can easily rotate all the distribution on SO3 at the same time, and also adjust their local density, make some region more heavily populated, and some location on SO3 less populated. So in our experiments, we find that this normalizing flow can feed arbitrary distributions from your data set, and also give image observation. We can change this normalizing flow into a conditional normalizing flow, so that the output of this normalizing flow will be the distribution of the observed images. This by far is the first discrete normalizing flow on SO3 that's truly use the matrix, rotation matrix representation, and gain the best performance on ModelNet 10 SO3 dataset, Pascal 3D Plus dataset, and I will skip the ablation study part. So this would be a useful tool for you guys to try if when in robot learning, for example, your action space may involve the rotation, and then there are actually multiple possible actions or rotations in your action space. Then you can try to use this tool to output multiple mode on SO3, and you just need to sample from this normalizing flow by forwarding this normalizing flow. Then you will get one possible rotations from it. I encourage you guys to try it in either grasping pose estimation and reinforcement learning. Yeah. So actually a lot of people before, a lot of speakers talk about equivariance. So today I'm also gonna quickly talk about one work. We use equivariance to facilitate the learning of pose. Why we talk about equivariance is basically pose should be equivariant. When you rotate the object, the output of your pose predictor network should be equivariant with the transformation in the input space. So this is the intuition why we want to use like a equivariant neural network to learn object pose. And in NeurIPS 2021, we have this paper, as Dan mentioned, leveraging SE3 equivariance for self-supervised category level object pose estimation. The idea is if you have a category of objects, they share certain similarities in geometry, probably leveraging the SE3 property of your network, you can unsupervisedly disentangle shape and pose. So definitely the motivation is that we want to get rid of 60 pose annotations from this object pose estimation pipeline. It is very expensive to annotate all the 3D orientations and 3D translations, involving manually move your CAD models in a visualizer, try to align it to its 2D projection and 3D point cloud, very, very time consuming, even compared to labeling a 3D bounding box, way, way, way more expensive than labeling 2D bounding box. So in this project, the key problems, can a neural network unsupervisedly disentangle shape and pose? So for example, given a lot of MOC, it's possible that a neural network can self-supervisedly find a category level aligned reference frame and also leave the transformation from this reference frame to the observation in the world space as the category level pose. If this unsupervised disentanglement can naturally emerge, then we do not really need any label. So again, we find that equivariance would be a very interesting way to try for self-supervisedly disentangle the shape and pose. The idea is like this. So if we have some input point cloud of, for example, airplanes, a lot of point clouds from different airplanes, and then we can level to predict the shape and its pose. And here the shape, we want it to be category level aligned shape, basically the shape without pose, or the shape in its category level canonical reference frame, for example, Knox. In this case, regardless of the pose or the exact pose of your input point cloud, this category level aligned shape would be the same for the same object. And then it also will predict a pose. And we note that there are interesting properties for these two things. The category level aligned shape is rotation invariant, right? No matter how you rotate your point cloud, this shape won't change. But whenever you rotate your point cloud, this category level pose will change equivariantly. So if we can have a neural network, then we can use its rotation invariant branch to predict the category level aligned shape. And we can use its like rotation equivariant branch to predict the category level pose. And then we use this pose, multiply it to the category level aligned shape. We should be able to reconstruct the input point cloud, and we can enforce basically the 3D chamfer distance between that. Hopefully, like because our neural network has this good property, invariance and equivariance, then the category level reference frame will emerge after you enforce this decomposition. So this is how we do it. We actually leverage like equivariant point cloud network. The name of it is just equivariant point network. And so we use its invariant feature to predict shape, equivariant feature to predict pose, and then we like multiply this two and find the loss between those two. So I mean, by now there are so many equivariant network, and so I think there might be some better choice than this equivariant point network. But by the time of 2021, we find all the equivariant network has limited expressivity when we apply it to complex visual data. They might really work really well for few particles, but if you have like a point cloud input with more than 1,000 points, very rich geometry details, then we find those network has like severely degraded performance. So that's why we find this equivariant point network a good choice. Although this network is actually just approximately equivariant. It just equivariant to the I60 group. I60 group is the largest a subgroup of SO3 without those like with arbitrary orientations in this group. And so I will skip how we the mechanism of this EPN, because this is not our contribution, but I encourage you guys to check this paper because we really find this work is good for complex visual data. And so we can do a max pooling among all the subgroup in I60. So this max pooling will give us invariant feature, and then we can use this invariant feature to predict the category level shape. So like surprisingly, this works really well. So basically the left is the input point cloud of the shapes, and our canonical shape reconstruction network is a very small MLP, so it is very lazy. It tried to reconstruct all the chair from this category like similarly. So that's why, although the thing we enforce is that this output shape is invariant with the rotation of the original point cloud, they are emerging to be aligned in this reconstruction space. So that's why if this reconstruction becomes canonical, then I will skip those like details of how this network becomes equivariant. So then the reconstruction loss will make sure the post prediction branch is correct, right? So that's why when you visualize our input output, so for each 3-column, this is one like shape from the category, and the yellow is the input, and the blue is the canonical reconstructed shape, and the last column show you when we like multiply the predicted pose to the reconstructed shape, whether it is aligned with the input point cloud. We find it does a pretty good work. And even if your input point cloud is partial, not necessarily need to be complete. So this reconstruction will be fuzzy along certain region if this object is partial. Definitely this is understandable because this category level reconstruction try to find a canonical shape and in its complete way. So it can be fuzzy when you don't see some part, but overall the alignment still it's still very good. So basically the category level pose, it's still pretty good. And in our experiments, we find either for complete point cloud input and partial point cloud input, this method works really well. And if I need to draw a connection between symmetry and equivariance, I would point out here that for car, those category, the front face of a car and the back face of the car sometimes look similar to each other. So if you use this self-supervised canonical reconstruction, actually, the reconstruction network will mix the front face and the back face, doesn't really distinguish front face and the back face. So your output may have 180-degree errors in the prediction. This is something, when symmetry hinders the equivariance. Yeah. So definitely you can try to add some supervision, some very small amount of supervision, which can greatly improve the performance. We actually compare to other supervised, unsupervised way, for example, ICP or even supervised way, we find our post-prediction error is still low than that, which shows the surprising effect of disentanglement from emerging disentanglement from equivariance. So I will skip the numbers. Yeah. So I think at the end, I want to say, so symmetry and equivariance, those things are have been explored a lot, but for rotation, those non-Euclidean manifold thing, I think is still very underexplored. There are a lot of things can be done, and in robot learning, a lot of case we care about rotation, we care about the orientation of the object, the orientation of the gripper, the orientation of probably like your drone or something. So this is something I encourage people to do more works. Yeah, thanks a lot. This is my talk.
Thank you so much for the great talk. We might have time for one question, a little bit over time. Okay, so I have one. So I'm really interested in like the part when you disentangle the pose and the shape. I think like, when we first proposed this workshop, we were basically thinking about symmetry in terms of pose, but we weren't really thinking about like the inductive bias based on the shape of the objects. Yeah. And I think like recently there are other works that also try to utilize this kind of inductive bias simulation. For example, the new descriptive field paper. I just want to ask you a little bit more on that. Maybe like, can you comment more on like, in the future, how should we better combine those two types of inductive bias together to make more sample efficient?
Yeah. I think this is a good question. I think equivariance is a very good property, and if something you are in nature it is equivariant, make sure your neural network is equivariant, or your method care about explicitly leverage this equivariance, then you can save tons of the data, right? So that neural descriptor things, they show that even with one demonstration, with the consideration of equivariance, they can learn how to put a mug onto a shelf, something like that, if I remember correctly. But what my comment on top of this is more on its possible challenges. So I think 1 year ago, I'm thinking I should do like an equivalent network on Dexter's hand grasping pose estimation problem. So we actually try those EPN and those things. And one problem we encounter is that, first, although when if this object resides in vacuum in the air, then when it rotates, the way you grasp it will rotate equivalently. That's true. But when this object lies on a surface, this is wrong. And you can definitely say, okay, if I know the exact geometry of the surface, I can actually filter out all the grasping poses that violate the constraint. But one more thing is that, when you take visual observations, sometimes it's possible to factorize this object from the environment. Sometimes it's hard. So if you cannot get the exact part of this object point cloud separated from the environment, then you shouldn't use an equivalent network to process it. So we actually try to use EPN in Dexter's grasp synthesis, because Dexter's grasping has a very high degree of freedom and is demanding a lot of data. But we find the performance is less satisfactory than we thought. So I think, along this line, there are still a lot of things we can do. Leveraging 3D is very excited, because those SE3 equivalent things can simply apply to it, but leveraging 2D observations would be very challenging if you want to leveraging the SE3 equivalence. So I think those challenges are probably important topics for researchers to think about. Yeah.
Great. Let's thank Professor Wang again for the great talk. I have a question about the type of data that we should use in manipulation, especially when we consider symmetries in our problem. So I guess a lot of the time, we were using images before, and now we wanna, go to 3D. So a lot of time we wanna consider some 3D data types. And also in the morning session, Professor Su was also showing us that, using point cloud in reinforcement learning might give us a better performance. So I wanna ask you about your thoughts on this. Like, for example, there are a lot of IC3 equivalent point net architectures out there, and there are also voxel-based equivalent networks we can use, and there are also in terms of using this kind of networks, we might have a trade-off on the set of network. For example, like if we use the voxel-based networks, it might easily get very heavy. And Andy, in your talk, you basically, my interpretation of your method is like using languages as kind of like input to the model, right? So I just want to ask you about your thoughts on what is the right type of data that we should use moving forward.
Yeah, I think it depends on the application. It depends on the system too. So if you've got depth sensors on your robot, if you've got LiDAR sensors on your autonomous vehicle, I think you'd be crazy not to use that data somehow. And I think there has been lots of really interesting work showing that when you do have these 3D biases, you can really improve on the capacity for these models to learn something that are a bit more general than what the 2D counterparts could. And I think one example that comes to mind is Mohit Sridhar had a follow-up from Clipport called Perceiver Actor, which was doing this voxel-based representation of figuring out the waypoints that you want to predict where you want to put your gripper next. And that was interesting because it's sort of reducing this, both the path planning problem as well as the manipulation problem of where to make contact down to predicting waypoints in 3D space. And that has lots of interesting benefits because if your model was equivariant, then you have an opportunity to predict waypoints that are mostly based on the local shape and geometry of the objects that you're manipulating. So if you had a shelf, for example, and one of the waypoints you're predicting was the handle, then as you move the shelf around, then the waypoint will sort of follow around the shelf. And that was really cool to see. So I do think that there are places where 3D can benefit. Does it mean that it's the best thing to do? I don't necessarily think so. I think that there could be 2D representations that are just as good. I think multi-view for a while, there's like was a top contender in the object detection or object classification data sets on the 3D benchmarks. So I think, you know, if you've got multiple RGB camera views, I mean, that's pretty good too.
Yeah, I think there is certainly a new work from, I think it's a new work from Dieter's group that basically uses multi-view as input to the transformer instead of using the voxels, and that turns out to be very good.
Yeah.
So we, in this year's eCrowd, we also have a work called Grasp Nerve. Basically, the input to this network is 6 view observations of the objects, and it is a generalizable nerve. So it's like without further training needed, within 0.1 second, it will predict the nerve of the scene, and based on its underlying geometry, SDF, actually more specifically TSDF, it can predict the grasping poses. While I think those multi-view RGB images can also be promising because you know, depth sensors has its fundamental limit when you know, sensing the transparent objects. So if you are familiar with depth sensors, whichever sensor type you use, the TOF or LiDAR or you know, structure light, passive stereo sensors, they don't really work on transparent objects. So if you use depth sensors to look at a transparent bottle on a table, you will find that the depths actually collapse onto the table plane. And so I really, I really want to leverage the good geometric signal from the depth sensors, but for transparent objects, those point clouds you cannot really trust. So in that case, you know, you have to think about signal from RGB if your point cloud is missing or corrupted. Single view wouldn't be enough to obtain metric depths. That's why multi-view RGB, considering the multi-view geometric constraint, can give you the similar amount of information. But again, so in that case, you probably need to reconstruct the one geometric representations from the multi-view RGB observations if you want to leverage the good property of equivariance. So then sometimes you don't really need very high precision in the reconstructions, but if you want to leverage equivariance, probably certain symmetry mode, this reconstruction also need to be aware. So I think at the end, this can still be a tricky problem. Yeah, like probably if you guys know some recent work that have deal with this problem, you can let me know. Yeah.
Another question I have is about symmetries in planning. Maybe this is more of a question for Professor Bekkers and Ruiqi. So, I'm just thinking about what kind of symmetry we might have in the planning problem. I guess Ruiqi, in your talk, you were mentioning like this time symmetry, like basically, or moving from A to B, you can inverse it, that becomes moving from B to A. So can we maybe explore some geometric symmetries in motion planning? I guess what's your thought?
Thank you for your question. Currently in my work, I only consider the statistical environment, and the symmetric is come from the iconal equation. So if we change the start and go and exchange start and go, and the optimal time or optimal path should be the invariant. But if consider the obstacle things, I think it's not a equivariant thing, but an invariant thing. If we translate and rotate the obstacle and the start and go point together, the optimal time, the scalar of the solution of the equation should be keep the same. So I think if in the future the motion planning structure consider this kind of thing, maybe it can be more generalized to multiple environments or dynamical environment. Thank you.
Yeah, can I add something to that? I think that there's still quite some room also to inject equivariance on this motion planning when it comes to solving the iconal equation and its shapes. Like typically this is addressed on position space. So you have a distance map on R2, or you do this on R3 if it's a 3D motion. But the agents, they typically have an orientation attached to them, right? Maybe a robot car can move forward and change orientation, but it cannot move sideways, for example. It could be a constraint. And so this is what I worked on in my thesis, like really this, like a car that can move back and forth and change orientation, but not sideways. And then you end up in a system, a control system, where you have a three-dimensional state space in SE2. I'm talking the 2D case now because the car has this pose, but it only has two controls, like moving forward, backwards, and so this generates like a sub-Riemannian geometry on the space. And now you really have to solve this on the group SE2. So you have to compute distances on the group themselves instead of distances on R2, the plane R2. And we show that this actually has some nice advantages, that now if you solve the iconal equation in this lifted space, just like lifted space, I mean, what we also saw with group convolutions, then you can explicitly also control for curvature of trajectories and these kind of things. And so I think there might be still a lot of room, or a lot, I don't know all the problems, but the room to sort of lift the problem to the group and solve the iconal equations and the trajectory optimization there, because that's also a way of circumventing certain problems, actually. And I would find it exciting to look into this with someone if anyone's interested.
Thank you.
Thanks a lot. I guess another question I have is about the efficiency versus expressivity trade-off. I guess this is a question for all of you. For Professor Bekkers, I guess in the group conf, we always have that problem of if we inject too much symmetry into the neural network, the network can be easily become very large. And I guess for Andy, when you were talking about the last part of your talk, when you were inputting the images to the large language model, you need to kind of decrease the resolution so that the language model can take in those input. I guess my question is, should we do something about that? Because especially, if you are thinking about using symmetries in learning, this is kind of like an inevitable problem. So should we just wait for NVIDIA to give us more powerful graphic cards, or or should we do something like designing more efficient neural networks or more efficient representation of our data to solve this problem? So I'm curious about your thoughts on this.
Yeah, maybe we can start off. Yeah, no, I think there's still a lot of demand for efficient equivariant methods, and we've come a long way actually. Like there's a lot of libraries that implement all of this equivariant stuff, and there's some really nice papers that really leverage maybe separability of group convolutions or other type of tricks to keep things fast. And I think when it comes to practical use, I think there should be at the very least some component that is equivariant simply because the problems require that. But when it comes to tensor field networks, for example, you don't have to go all the way to frequency 5 or 6. Then it gets really computationally heavy and that's intractable. But even just working with scalars and vectors, like with this geometric vector percentile type of thing, maybe a special case of tensor fields, that's already enough. It's enough to have some notion of direction in the data and then let the neural network figure out how to do something more complex with it. So I think generally you can really slim down this method quite a bit and still benefit from the equivariance part of things. And our group is actually still working on efficient point cloud, equivariant point cloud methods, and we got something really, really promising coming up. But yeah, there's constantly a demand for more efficient and good tricks because if it scales, then people use it and you can deploy it.
Yeah, I agree with things that are said so far from Erik, and also specifically on the general pattern machine examples. I think that if we're thinking really far down into the future, like 20 years from now, decades from now, when we do have the compute and NVIDIA becomes huge or something, then maybe I think we could just lean on big models to be able to feed in large images and they would handle them just fine. But in the meantime, if you want to make cool demos and like have systems that actually work using some of what already seems to appear to work in today's LLMs, I think having some version of reduction to a more semantic representation could be good. So example is like, say that on a tabletop setting, we have apple, orange, banana, and now you want to tell a model given banana, orange, what comes next? If you can reduce that problem all the way down to a semantic abstract symbolic representation, then your LLM will probably figure it out. So to get to that point, you could maybe leverage open vocabulary object detectors or segment anything. And I think those segment anything model, and I think if we can use some of the really powerful vision language models that we have today, we might be able to get pretty far in reducing a lot of our problems down to a symbolic representation that LLMs today can work with.
Yeah, can I have one more comment on the computational aspect? Like, I think efficiency is important, but not just because we want to run things fast. It's also about reducing the problem, like you mentioned, maybe in smaller chunks. And I think what equivariants provide is taking away this ambiguity when it comes to geometry and physics. Like at least that part is taken care of correctly, and we still have to go deeper. But even if there's like super powerful GPUs for everyone, very cheap in a couple of years or so, then still you have the problem of data and the challenge of how difficult problems can be. And even if you have very efficient methods, then the bottleneck becomes data and your reasoning capabilities of your neural networks. And so, solving efficiency is one thing, but then being clever about how you design your architectures and your neural circuitry and all that's going to be the next thing. I think still there's a lot of a place where geometry can play a role. You already see that with these equivariant methods that they reduce the demand for data by quite a bit. They are computationally somewhat heavy, but as said, yeah, there's efficiency tricks to it. So I think it's not just data efficiency for on the edge computing, but also for the purpose of being more data efficient.
Yeah, I also want to comment on this front a little bit from the perspective of uncertainty. I think like nowadays, we have a lot of applications driven by data. For example, for grasping, and GraspNet has in total 1 billion grasping labels, and which yield a very successful grasping algorithms. But I think, even if you have 1 billion labels on top of those object surfaces, the neural network is still kind of, overfitting to your labels, because think about like the label tell you that you have to exactly grasp this object from this orientation, this position. But like if you just rotate 5 degrees, I believe the gripper will, in most of the case, still be able to grasp the object, right? So like when we have to deal with a great amount of labels, then we need a lot of computational resources. And if we want to overcome the generalization issues, we need more data. So that's why to, at least alleviate this issue, we probably want our neural network to be aware of uncertainty. And this can be one way to reduce the demand of data and labels. So I think people like have studied the uncertainty modeling problem in Euclidean space for a very long time. People have shown that use Laplacian model, Laplacian distribution, they can learn better, perception modules, like even if the labels is noisy, are noisy. So I think in rotation space, in post space, they are non-Euclidean, no longer Euclidean anymore. So we probably also want to delve into more for modeling the symmetry, modeling the uncertainty, probabilistic distributions on SO3 to alleviate the data issue in that space.
All right, thanks a lot. There were a question from the audience, right? Oh, excuse.
Hello. I think the covariance as a property is very useful, but there's also an extent to which it's actually it holds, and an extent to which it actually breaks down. So if you think about like translational covariance, like at the end of the table, it no longer holds. So you cannot apply the same action to the object and expect the same outcomes. And in these cases, I wonder if there's any approaches to actually figure out until what point equivariance actually holds, and up to which point it's actually useful, beyond which it breaks down.
Yeah, this is a great point. I can maybe start comment on this. Like there's also now more and more works on approximate equivariance, where like you have like a system of interacting particles, or you have a system where you have very well described equivariance properties, but then there's also terms that break it. And typically, so there's some global aspect. When you talk about a table, there's like a global scene, it's fixed, it's there. And then relative to this global scene, you can still operate things. And on a table, it's indeed translation, and at some point it falls down. So there's methods that couple this. For example, I have a recent paper from a group by Miltis Kofinas on neural field discovery, where you do unsupervised discovery of these global factors that may perturb equivariance relations that are otherwise strictly local interactions. Okay, so that's one thing. It's very hard to explicitly model this, right? To do this case by case. Here the table ends, there it starts. There's a chair, and but people are now trying to solve this via neural fields or some sort of global influence parameter that can be learned or inferred from the scene. Thirdly, or I don't know where I am, but I also want to add that when it comes to translation equivariance, I think almost all cases should be thought of as subcases, or at least within the framework of SE3 equivariance, right? Because we live in a 3D world, if you discard time for now. And so also like the 2D planar rotation, translations and rotations are subgroups of SE3. So instead of switching between what kind of group you're looking at, I think it might be often useful to think of things as being either subgroups of SE3 or just the whole group limited to whatever situation you're looking at.
I think one possible and effective approach to address this problem is just let your output space to be equivalent. And so you may have a lot of proposals generated from your equivalent network. And then given the condition from your environment, you can filter out some, invalid outputs while maintaining the equivalent property of your network.
All right, thanks a lot. I guess that will conclude our panel discussion session. Let's thank the panelists again. Okay, so to conclude our workshop today, yeah, I think it has been great. I've learned a lot from all of our speakers and all of the discussions. I just can't really wait to go back to work to implement some new ideas that I have come out today. So first, I would like to thank all of our speakers again. I guess we learned from Andy about languages as another type of inductive bias upon geometric equivariance. So that could be very useful. We learned from Professor Wang about how can we do post estimation, and we learned from Professor Su about the power of point networks in reinforcement learning, and we learned from Professor Ghaffari about the equivariance in locomotion. And moreover, we learned from Professor Smidt and Professor Bekkers about some the insights from the geometric deep learning perspective. And for people that are not very familiar with equivariant learning, I guess that was like a great tutorial for you to actually enter this field and actually use those methods. I want to thank all of our speakers again. That's a great talks. And then I would like to thank all of the organizers, Professor Robert Platt, Professor Robin Waters, Professor Shuan Song, Dr. Alice Vanderpoel, and Cheng. So a lot of them cannot be here due to different reasons. But I want to thank all of them for their help doing the organizing of this workshop. It's not going to be possible without them. And also, I would like to thank all of our program community members, especially Xu who traveled all the way from Boston to help me today in our workshop. Yeah. Okay, so now the Black's Fiffer Award for our workshop, it goes to robotic manipulation learning with equivariant distributor fields. Congrats. Go to stage. It's a great work.
Thank you very much.
Okay, thank you so much for participating in our workshop, and hope you will enjoy the rest of the conference.